Good evening everyone. Welcome to Gate Academy Global. So just confirm me audio and video both quality is perfect or not. Okay, good evening everyone. Just confirm me audio and video both quality is perfect or not. And today we are going to start sequential circuit, and today is the last session for digital, and today we will finish all the remaining topics. Okay, so today I am going to start from sequential circuit. Okay, so most important thing in today's session we are going to discuss. Okay, so everyone please share the session and just comment audio and video both quality is perfect or not. Okay everyone, just comment me. Okay, then I can continue the session. Okay, so now I am going to start a sequential circuit in today's session. Okay, so exactly what exactly you should know in sequential circuit. So you should be expert in first latches. Okay, so you should be expert in latch. Okay, you should be expert in the latch. Okay, then you should be expert in clock the latch. Then clock the latch. Okay, then clock the latch, and clocked latch is called exactly, this is a flip flop. This clock latch is called, this is flip flop. So now again here two kind of clock is possible. One is level triggered and one is edge triggered. So here all the flip flops should be very much clear to you. Next, you should be expert in register. Next, you should be expert in register, and next you should be expert in the counter. Next, you should be expert in the counters. Okay, in counters, asynchronous counter and synchronous counter, and how we can implement the modern counter. All the topics I will revise in today's session. Okay, now be with me. Definitely you will learn so many new things, and that will be definitely helpful you in your upcoming GATE exam. So now first part I am going to start, that is latch. Okay, first part I am going to start, that is latch. Generally, you study, I hope definitely you studied latch, that is NAND latch and NOR latch. But I am going to first, okay, I am going to here first describe NOT latch. So NOT latch can also be possible. So first topic I am going to start, that is latch, and the first is nothing but NOT latch. Okay, NOT latch. Latch is a standard structure, and when you will connect two logic gate in this way. Okay, when you will connect two logic gate in this way, output of first is connect to the input of second, and output of this second is connect to the input of first. And now your NOT gate is only one input logic gate. NOT gate is one input logic gate. So here this two value cannot be different. If this is x, so this will be definitely x. This two value cannot be different. Okay, so here what you have to do, either you have to provide input or you have to provide input at one place only. You can provide input. Just I am going to assume I am going to provide input here. So if you are going to provide input, suppose this input is x, then what will be this output? This is nothing but x bar, and if this is x bar, then x bar complement, you will get here x. Again this is x, then this both values should be same. Are you getting this point? So this value is coming from here, and this value should be same, otherwise you will get some confliction here. So now this circuit is a practically called, this is nothing but a NOT latch. This circuit is a NOT latch. This circuit is a NOT latch. Okay, you should remember. Okay, now if you will ask me, sir, what is the use of this circuit? In last class we have studied, one gate like this, in this way, and here two output was given in this way. If you remember, P, Q and R, the three input has provided. If this is P, so here you will get P bar, and here you will get P. So you can see here, if this input is X, so this is nothing but X, and this is nothing but X bar. So here both, so you can represent this circuit in this way. So you can write, see, this is nothing but X, and you can write here this is nothing but X bar, and you can write here this is nothing but X. Okay, so this is your NOT latch. Now what is the use of this NOT latch exactly? What is the use of this NOT latch exactly? So NOT latch, so what is the exactly use of this NOT latch? So this is nothing but 1 bit memory element. So this is very important. This is a 1 bit memory element. 1 bit memory element. How you can say this is 1 bit memory element? If you are going to provide here X and you are getting here X, you are getting here X. So 1 bit memory element is nothing but this. So already this question has been asked in GATE exam, and if anybody know this thing, then they can handle the question. One question has been asked GATE exam, what is a 1 bit memory cell? So and that circuit is given by the CMOS, and that question come under the logic gate, or you can say semiconductor memory, but that will become under the logic gate. So if you will implement this by CMOS, so here 2 number of MOS is required. For NOT gate, everybody know how we can represent NOT gate by using MOS. This is your PMOS, this is your NMOS. If this is your X, so here you will get this is X bar, and this is your ground. You can say this is power supply. I can write this is VDD. So this is your NOT gate. This is your NOT gate by MOS, or you can say by CMOS. Okay, so this is your NOT gate. So if this is one NOT gate, this is one NOT gate, this output is connected to input here, and this output is connected to input here. So how many here MOS gate is required? For this is 2 MOS is required. So this is 2 and 2 4 MOS. And now if you have studied memory structure, so in memory we will represent in this way. Memory we will represent in this way, and every this block will store 1 bit memory. Now in GATE exam, every year examiner are targeting question from here. One student have asked in last class, sir, will you teach semiconductor memory? Already we have studied PROM and ROM, and one question from PLA in the last class. Exactly, that is actually part of semiconductor memory, and this one is a part of, you can say, semiconductor memory. Okay, this one is a part of semiconductor memory. Yeah, good evening everyone. Please share the session. Today class is going to be very important. Okay, and definitely after this class your marks will be improved in GATE exam. Okay, so now please share the session. Please share the session. Okay, now okay, a telegram link, GATE Academy global telegram link okay, already shared, you can see. Okay, and anything you can post there. Now you can see, just I want to tell you, every this block is a 1 bit memory element. So just I can say this is 1 bit memory M, this is 1 bit memory, this is memory, this is memory, this is memory. Here this is nothing but your address line, here address line, and here data line. Here this is nothing but data line, this is data line. So one more MOS is required to enable or disable. Suppose I want to enable this line, so here one more extra MOS is required, and here if I want to enable this data line, one more MOS is required. Okay, and that will be your NMOS. Okay, that will be your NMOS. So just I want to tell you, if we want to implement 1 bit memory cell, so in real world 1 bit memory cell is represented by 1 bit memory cell is represented by how many number of minimum transistor, and this kind of structure is called SRAM. This kind of structure is called SRAM. So SRAM design we can implement in this way. So this is called 6 transistor SRAM. 6 transistor SRAM. So in GATE exam, one question already has been asked. They have provided you 4 diagram, and they asked which one is correct. So what you have to think only, in which 4 diagram this structure is going to be happen. This structure means this is a one NOT gate, and output of this is goes to the next NOT gate input, and that output is goes to this input like this. Suppose if again I am going to draw here, suppose like this, one NOT gate in this way. Suppose this is again one NOT gate like this, and this is your ground, and suppose this is VDD. Okay, and this both is connected here, and this both ground is connected here. So now the output of this, so suppose if I will say this will be the input of this, so just I can say this is input, this is X. Suppose if this is X, output of this is nothing but, suppose I am writing this is X bar. Suppose for example, the output of this is connected to the next input. It means this is connected to this input, and then again what we can say, output of this is connected to this one. It means this output is connected to here, this one, like this kind of a structure you will get, this kind of a structure you will get, and some two more number of MOS is required to enable and disable this memory cell. So just remember, okay, the questions can be repeated from here. So this minimum 1 bit memory cell is designed by 6 transistor SRAM. Okay, so you should know about this, and you should know about the NOT latch. NOT latch is a 1 bit memory element. Clear this point? Okay, so now the second latch. Second latch, everybody know the second latch, that is NAND latch and NOR latch. Now I am going to take second latch. I hope this thing is clear to all of you, and this is very important. Okay, this is very important. So now come to the next. Sir, what is NOR latch? What is NOR latch? Okay, what is NOR latch? Okay, what is NOR latch? So if I will write here NOR latch, so you will take here one NOR gate, and this is 2 input, and one NOR gate, this is again 2 input. Now this output is connected to the second input of this NOR, and this output is connected to the this second input of this NOR. So now the important thing, sir, what is our main protocol to implement a latch or flip-flop? So in latch or flip-flop, suppose if you are providing a data, suppose just I want to discuss this memory cell. If you are providing me a data, so I will store the data, and now if somebody required that data, then both the data is available in normal form and complement form. Are you getting my point? So just I want to tell you, sir, if this is a data, and if we have 1 bit memory cell structure, then what is our requirement? Our requirement is, if somebody are asking the data, suppose I have stored some data, okay, the data is X, and suppose you are asking me the data, then I have both the possibility to provide you active high data or active low value of that data. Are you getting my point? In digital electronics, so many time normal input is required, and sometime complement of that input is required. So if somebody are asking here data, so I have here both the possibility, data complement and normal form. So data normal form and complement form, in both the form should be available. This is the main requirement of sequential circuit. Are you getting this point? So main requirement of the sequential circuit is if you have any data, so the normal form and complement form both should be present. So now just I am saying this is a NOR latch. So just we can say one output. So here if you have one output, then output should be present in normal form and complement form. This is our target. So just we can consider here this is 2 number of outputs. So what is our target? One output can be Q and second output can be Q bar. Second output can be Q bar. Both cannot be same. Can be same, but that will not fulfill our requirement. That will not fulfill our requirement. So if we will process this circuit, already we have studied in NOR gate or OR gate, if any input is 1, then output is decided. Any input is 1. So what is the name of this latch? What is the name of this latch? So if I will, suppose I am going to write this X and Y. If I am going to write this X and Y, okay, so if suppose we can here write a table, suppose this is X, Y, and if this is 0, 0, so this will definitely depend on this output. Suppose this output I am assuming this is Z, so this is Z plus Y, this is Z plus Y, and suppose both having 0, 0, so what will be the output? Z plus 0, Z. So here you will get Z bar, and here this is Z bar plus 0, again you will get Z. So here output, what output you will get? What you are assuming here? So just I can write here, suppose this is Q. Suppose I can write this is Q bar. So what you will get here as it is Q. So what you will assume here? Same value you will get. So if I am writing here, this is a next output. So what will be the next output for 0, 0 input? Your previous output. So can I write here, this is nothing but Qn. Okay, now suppose for example this is 0, 1. If this is 1, so this second input is not required. If this is 100%, output will be 0. So here this Q bar will be 0, then this 0 plus 0, this 0 bar will be 1. So here this is 1 and this is 0. So here this is, you are getting 1 and this is for 0, 1. And now for 1, 0, and for 1 0 what will be the output? For 1 0, if this is 1, second input is not required, 1 plus anything is 1, so this output is 0. And if this is 0, 0 plus 0, 0 bar, you are getting this one. So both having complement of each other, and you are considering this as a output, so you are getting here 0. Similarly for 1 1, if both having 1 1, then second input is not required. In this case, this will be 0 and this will be 0. And what is you cannot say the circuit is not working. Circuit is working properly. Circuit is working, but your requirement is not going to fulfill. So you can say I want, if here 0, then this should be 1, and if this is 1, this should be 0. It means according to you, circuit is properly working, but your requirement is not going to fulfill. So what you can say, according to you, this is invalid input. So this input you cannot use in the circuit. Are you getting this point? So this input you cannot use in the circuit, and you will write, sir, this is don't care. Already we have studied meaning of don't care. Don't care meaning is, if for any input you are representing don't care, it means that input you cannot provide in that circuit. Are you getting this point? It does not say, you can say, sir, for this input output can be 0 0 or output can be 1 1. No, for this 1 1 input, output is 0. Output is definitely 0. So what is the meaning of this? If output is don't care, the meaning of this, you cannot provide here input 1 1. You cannot provide here input 1 1. So now, sir, what we can write the name of this circuit? So you can say here this is no change. You can say this is 1 you are getting, and this you are getting 0. 1 means set. 1 means set. So what you can write here? What you can write here? So what you can write here? This is Qn. So if you are getting no change, if you are getting no change, so this for 0 0 and for this 0 1. So can I write this switch name is set? So this is nothing but R, this is nothing but S. Can I write this is nothing but R and this is nothing but S? Can I write this? Yes, we can write. So this, if set button is 1, so now we can write this switch is R and this switch is S. Can I write? So if reset switch is 1, then output will be reset, means 0. If set switch is 1, output will be set, that is 1. Okay. So if reset switch is 1, output is 0. If set switch is 1, output is set. So what is a function of this circuit? So in this circuit, first requirement is both the output should be complement of each other. Okay. Now just I can write here, this is Q, this is Q bar. Now we have two input, and the name of that input is R and S. So suppose if you are pressing the switch R, so output will be reset. Output means this Q. Q is the output, and this Q bar is the output complement. This is nothing but output complement. So both the state of output is going to be present here. So if you are going to press reset, output will be reset. If you are going to press set, output will going to be set. Are you getting this point? And if you are going to not press any switch, set or reset, then output will be no change. If you are going to press both the switch, then how it can be possible? So practically you cannot press both the switch, set and reset simultaneously. Are you getting this point? Either you cannot press both the switch, or one switch can be pressed set, or one switch can be pressed reset. So now you don't remember this truth table, so directly you can write. Directly you can write here truth table. Now you don't remember okay, this diagram. Directly you can write for the set reset latch. So for the set reset latch, how you can write? If you can write S here, R here, okay. So if this is 0 0 0 1 1 0 and 1 1, so what you can write here, set and reset both are 0 0. So what you can say, the next output is no change. This is Qn. This is nothing but no change. Everybody, I hope, definitely know this thing, but just I am going to recall this point. This is 0 1, so just you can remember, if this is reset, so you can write here reset, and reset means 0. If this set is 1, so you can write here set, and set means 1. If this is 1 1, it means you can write here invalid. This is invalid, and you can write here don't care. You can write here don't care. Okay, so you can write here don't care. So what is a function of here? So Qn plus 1 function, directly I am going to write, this is S plus R bar Qn. This is S plus R bar Qn. So you remember, this is a characteristic equation. So characteristic equation of SR latch. Later I will discuss SR flip flop. The same thing you will get. So for SR latch and for SR flip flop. So what we can say name of this NOR latch? This is nothing but SR latch. What is it of this NOR latch? This is nothing but SR latch. This is nothing but SR latch. This is nothing but SR latch. Okay, now. Okay, now. Clear this point? Okay, now. So what is the name of this? This is SR latch. So you don't remember truth table directly you can write, and easily equation. You can also find out equation from here. If you will put this value in the K map, you will get this expression. But directly you should remember this is your characteristic equation. This is characteristic equation. This is your characteristic equation. Okay. Now sir, this is NOR latch, and NOR latch name is what you are saying, sir. NOR latch name is SR latch. SR latch. Okay, and what is a NOT latch? NOT latch is 1-bit memory structure. 1-bit memory structure. So here sometime student will remember in NOR latch this R and Q, okay, are in same level, and this Q bar and S are in same level. So you can also remember in this way. Now come to the next point. Sir, is there any representation of the same circuit? The same circuit can I represent by NAND gate? So can you represent the same circuit by NAND gate? Is this possible or not? Yes, definitely it can be possible, sir. How it can be possible? How it can be possible? So you can see here, now we have to play with bubble. So now you can see here this was bubble. So this bubble can I place here, and this bubble can I place here? Because this bubble will, if you will place here, so here one bubble, because there are two paths. So now this bubble can I put here? Okay. This bubble can I put here? Okay. Now this bubble can I remove from here, and this bubble can I put here, and this bubble can I put here. Are you getting this point? Now if I will put here two bubbles, so again this will be same. Can I put here two bubble? Again it will be same. If this bubble I will remove, so here you will get Q bar, and if this bubble you will remove, here you will get this Q. So can I write? So if you want to represent the same circuit, this is NOR latch. So this circuit is NOR latch, and the name of NOR latch is SR latch. This same circuit if you want to represent by NAND gate. So you can see here, this is a bubble OR gate. This is a bubble OR gate. Bubble OR gate is nothing but a NAND gate. So what you can write? If this is R, you can put here one NOT gate. This can be NOT gate. Okay. And here can I write one NAND gate? Okay. Now here this is R. Here can I write S? Here one NOT gate. Here one NAND gate. And now this output is connected to here. This output is connected to here. But this is going to become now Q bar. This is going to become Q bar. And this is going to be Q. Now you can represent in reverse order. Generally Q we write in upper portion, upper side, and Q bar in bottom side. So you can also represent this circuit in this way. This is like this. This is like this. Okay. So you will get in this way. You will get in this way. You will get in this way. Now this is Q and this is Q bar. Now this will be your S. This will be your S and this will be R. Now if I will ask you, what is the name of this circuit? What is the name of this circuit? What is the truth table of this circuit? And what is the characteristic equation of this circuit? So everything is same, because both the circuit is same. Because both the circuit is as it is same. Both the circuit is as it is same. It means this circuit name is also SR latch. Okay, this circuit name is also SR latch. But this SR latch you have to implement by. Now if I will ask you, this SR latch can be implemented by either NOR gate, and we can say that is a NOR latch. In another way, you can say here to NAND gate, and this is to extra NOT gate. This circuit is not a NAND latch. NAND latch is different. So you can say this is a active low NAND latch. So you can write this is nothing but this is active low NAND latch. You can also write active low NAND latch. So SR latch having two names. First name is NOR latch and second name is active low NAND latch. Are you getting this point? So this SR latch can be implemented either by this NOR latch or by active low NAND latch. So how you can remember this SR latch? So SR latch you remember, if you want to represent by this NOR, so you can write here this is Q and this will be R, here this will be Q bar and here this will be S, and here everything will be positive. This will be NOR and this will be NOR. Now if you want to represent SR latch by NAND gate, then this q, okay, here you can write s, here q bar, here you can write r, and here this is NAND, but here this two input will be complement. In another way you can also write in this way, like this and like this. Okay, so don't get confused here. So SR latch is either NOR latch, or you can say active low NAND latch. And what is a truth table this, and what is a characteristic equation S plus R bar Qn? I hope definitely you should know this thing. Now the second important point, then sir, what will be the NAND latch? So already you know the NAND latch means you cannot use here, you cannot use here this NOT gate. So NAND latch will be different. Okay, here the name of this NAND latch is active low, you can say NAND latch. So input is active low. Now the next question is here, sir, what is exactly NAND latch? Okay, so what is exactly NAND latch? So if examiner will tell you, if examiner will tell you NAND latch, if examiner will tell you NAND latch, if examiner will tell you NAND latch, then standard latch structure you have to represent, and just gate will be NAND. So what is a standard latch structure? This is the first gate and this is the second gate. Output of first is connected to second input, and this output of second is connected to first input. And now generally we will represent Q upper side and Q bar at bottom side. This is nothing but NAND latch. This is nothing but NAND latch. This is the active low input NAND latch, and this is SR. This is not a SR latch. This is very important. This is not a SR latch. You cannot write this is exactly SR latch. SR latch is either this one, or you can represent by NOR gate. Are you getting this point? Then sir, what is a function of this circuit? So if I am going to write here x and y, so just if this is x and if this is y, then what will be the next state of this? So if this is 0 0, then you know very well, if NAND gate any input is 0, output will be decided. Already we have studied majority input already we have studied majority input concept. So here if this is 0 0, output will be 1 1. It means it is a invalid. It is a invalid, and you can write this by don't care. It means here 0 0 you cannot use. Now sir, for what will be for 0 1? If this x is 0 and y is 1, so you can process this. If this is 0 0 dot anything 0, output will be 1. So q you are getting permanently 1. If this is 1, this is 1 1 dot 1 1 1 bar 0. It means both are complement. Okay, so you are getting a valid output, and output is a 1. So for 0 1 this is 1, for 1 0 you will get here 0, and for 1 1 you will get no change. This is, so again you are getting here 4 state. Okay, so this state is no change. This state you are getting no change. Sir, here 0 I can say this is reset. Reset, here you can say this is set. This is set. You can say here this is set. So if output is 1, you can say set. If output is 0, you can say reset. Okay, now so here if you can say, sir, if this y is 1, then you are getting set, and here if this x is 1, you are getting reset. Okay, but both are 1, then you are getting no change. It means here 0 is working and 1 is not working. So what we can say, 0 and 0 means you are going to press both the switch. Sir, invalid. This 0 means you are going to press this switch. Okay, so this switch is, you can write here, sir, this is set and this is reset. You can also write in this way, but here this is active low category of SR latch. If this is 0 means this is working. Okay, and if this is 0 means this is set. If this is 0 means this is reset. Both 0 0 means here reset and set, both switches working. Both are 1 1 means both switches not working. So what if you want to write the name of this circuit? So you can write the name of this circuit is this is a active low, this is a active low SR latch. You can write this is active low SR latch, but we don't study this. But we don't study the name of this circuit, active low SR latch. Okay, so you only remember what is SR latch. SR latch either you can represent by this, or you can represent by NOR gate. One thing you remember, by NOR gate Q and here R, and in NAND category this is Q, but this is S bar. Okay, if examiner will provide you NAND latch, so you have to represent this circuit. This is very important. Clear this point? Okay, so SR latch you should know very well, and NAND latch, okay, you remember, and NAND latch name you don't remember. So don't remember the name of NAND latch. This is NAND latch. Okay, it is better don't write here S and R. You can write here X and Y. again you are getting here 4 state. So not latch, NAND latch and NOR latch, all the 3 things should be clear. Not latch is generally you work as a memory element. Sir, what is the use of NAND latch? So generally we don't use NAND latch. Okay, generally right now we don't use NAND latch, but when we will design a flip flop, then this NAND latch will be used. Okay, later I will discuss. Okay, so these 3 basic things should be very much clear to you. Okay, so these 3 basic things should be clear to you. Now I am going to take one good level of question. Okay, now, okay, you are sir, bubble thing not understand. Okay, bubble thing, okay, okay, bubble thing, this is suppose we have NOR gate, suppose, okay, and here suppose we have 2 path. Okay, so if can I write bubble here? Okay, if suppose this one is X, so what will be this X bar? Here what will be X bar? Here this will be X bar. Okay, so what can I write? If you want to remove this bubble in the 2 path, what you can write? Here this bubble, and we have here a 2 path, so this bubble you can remove from here, and this bubble can I put and can I put here? Yes, if this is X, so definitely this will be X bar and X bar. Result will be same. So if we have 2 paths, so you have to divide bubble into both the part. So from here just this bubble we have divided. So this concept only I have applied here. Sir, here this is NOR gate, okay, sorry, and this is connected to here, and here this is connected to here in this way. So what I did here, just this bubble I have removed from here, okay, and this bubble I can put here, and this bubble in this path I can put here. Similarly, this bubble I can remove from here, this bubble I can put here, and this bubble I can put here. Are you getting this point? Can I put here 2 bubble? Result will not change. Can I put here 2 bubble? Result will not change. Previously this was Q, then this was Q and Q bar. So if I will remove this bubble, so can I write this Q bar? And if I will remove this bubble, can I write this Q? So now you can see, sir, this is bubble OR gate, and bubble OR gate already we have shared, this is nothing but a NAND gate. So this is NAND gate, and this one is a NAND gate. This one is NAND gate. So what you are getting, this is NAND gate, this is NAND gate, and here this bubble is representing by this NOT gate and NOT gate. This is R and this is S, and this is nothing but Q bar, and this is nothing but Q. I hope now this thing is clear to you. Okay, so like this you have to play with a bubble. In digital electronics you have to play with a bubble. Okay, so now I am going to take one good question from here. Okay, now, so sometimes students are getting confused between NAND latch and NOR latch. Okay, and what is the SR latch? So SR latch is nothing but exactly, SR latch is practically NOR latch. You can say active high category of NOR latch, but active low category of NAND latch. Okay, and if you will say, sir, NAND latch, so NAND latch is not a SR latch. Okay, but if you want to write the name, so you can say NAND latch is active low category of SR latch. So what is the relation here? How you can remember? Sir, this is SR latch. SR latch is actually, you can say this is NOR latch. But if you want to write in terms of NAND latch, so you can write here active low. This is active low NAND. This is active low NAND latch. Okay, now if you want to write NAND latch, so this active low you can put here. Now if you want to write here, sir, NOR latch, what is the name of NOR latch? So you can say SR latch. Okay, SR latch. Now if you want to write the name of NAND latch, so what is the name of NAND latch? So now you can write active low SR latch. So now you can write active low SR latch. Okay, but here we are interested in SR latch. That's why generally we use either NOR latch or we use active low NAND latch. Okay, so SR latch 2 circuits should be clear to you. Okay, now I am going to take one question. One thing you remember, if we have one circuit, suppose for example this is one digital circuit, and if we have 2 input, and we have here Q and this Q bar. Suppose if this input 1 and this, if this is an input 2, if this circuit is going to provide you 4 state, if one state is set, one state is reset, one state is no change, and one state is invalid. So this circuit name you can call that is a SR latch. Are you getting this point? So any only if you are getting this 4 state, so you can say the name of circuit is SR latch. Are you getting my point? Are you getting my point? So if you are getting for any truth table, so if this is input 1 and if this is input 2, if this is input 2, so here you will get 4, 1, 2, 3, 4 input. So this 4 input can be anything, but if you are getting here 4 number of output, one will be no change, one will be no change, one will be set, one will be reset, and the last will be invalid, and last will be invalid. So this circuit is called SR latch. So what I will call this circuit is SR latch. This circuit is SR latch. Okay, so if you will get this 4 kind of output. Now come to the point. Okay, so we can call this as a SR latch. But standard SR latch definition, if this is 0 0, then no change, 0 1 set, 1 0 reset, and 1 1 invalid. Means set is 1, then output is set. If reset is 1, output is reset. Both is 1, invalid, and both is 0, no change. Okay, an equation you should remember, S plus R bar Qn. Okay, now suppose one question I am going to consider from this, and this is very important topic. You will ask me, sir, why you are investing so much time in this topic? So now you can see, suppose for example, if we have here, suppose for example, if we have here, suppose 2 NOR gate, okay, like this. Suppose we have 2 NOR gate. Okay, now suppose for example, if here this is a 1 switch, and if suppose here we have a 1 switch, this is a push back switch, okay, now, and now if here this is connected with a plus 5 volt, okay, plus 5 volt. So you can write this is output, so this will be nothing but output bar. This is nothing but output bar. Okay, now any switch name is, suppose this switch name is R and this switch name is S. Okay, and this NOT gate is implemented by, this is TTL logic. So this is a TTL gate. This is a TTL gate. So now if I will ask you, what is the operation of this circuit? So this circuit work aise. So the above circuit work aise. Anybody can tell me the answer. Is this circuit work as a SR latch or not? This is my question. So this circuit will work as a SR latch or not? Only yes or no. So this circuit work as a SR latch. Okay, yes or no? Tell me. You have two options. Yes or no? Tell me the answer. Yes or no? Tell me the answer. Yes or no? Tell me the answer. Yes or no? Okay, Akhil, I will solve your problem. Don't worry. Okay. Okay, I will provide you how you can send me the your doubt. Okay, now. But now first focus on this problem. Okay, yes or no? So one answer I received no. Okay, one answer I received no. Any another answer? Any another answer? Tell me. Any another answer? So you can see here, this if you will R is 1 means this is press, if R is 0 this is open. This is a TTL gate. So you can see, if I will write here, this is R, this is S, suppose, and if I will write here Qn plus 1, if both is 0 0 means both switch is open. If both switch is open, so this will be open input and open input, and open input is treated as logic 1. Why logic 1? Because this is TTL gate. So if both this R and S switch is open, so this will be 1, this will be 1, and if this is 1 1, so 1 plus anything 1, 1 bar is 0, 1 plus anything is 1, 1 bar is 0. So both the output you are getting 0 and 0, it means invalid. So in this case your output is invalid. Now if this R is 1 and if this S is 1, so now if this R is 0 means this is open, and if this is closed, if this will be closed here 5 volt means you can write this is 1. If this is open, this is open circuit, again this is 1, so again this is 1 1, then again your output is invalid, again your output is invalid, again your output is invalid. Now again, sir, if this is 1 0, if this is 1 0, If this is 1 means switch is closed, again you are getting 1. If this is open, so again this is open input 1 1, again you are getting invalid. Again you are getting invalid. And if this is 1 1, both switches closed, again you are getting both 1 1, so again invalid. Again invalid. If I can put here one NOT gate and one NOT gate, so always you will get no change and no change. If I will put in the same circuits, are you getting this? So here this circuit is going to not work as a SR latch. So your answer is yes. Sorry, your answer, no, this cannot be possible. This cannot be possible. But sir, this is a exactly SR latch. SR latch already we have studied in this way, but we have not studied with pushback switch. Are you getting my point? We have not studied with push back switch. So here what is going to be happen? If you are going to press the switch, this is going to be 5 volt means 1. If you are not going to press the switch, if this is open, then again open input is stated because of the T-tail, again this is 1. This is very good and very important question. Okay. Now suppose if I will put here 2 NOT gate, then what will happen? Suppose if I will put here 2 NOT gate, then again in every situation this is 1 1, then this is 0 0. If this is 0 0, no change. So if I will provide you this second circuit, so if for the second circuit, so Qn plus 1 will be all the four state will be no change, no change, no change, no change. But all the 4 state you are getting the same states. Now my target, if I want to design this circuit as a properly SR latch, then what we have to do? Then what we have to do in the circuit, if I want to implement this circuit as a proper SR latch, then what we can do? So suppose for example, if this is going to be ground, then what will be the truth table for this? Okay, so in 4 options, one option is given. If this supply is connected with a ground, then what will happen? Now you can see. So if this supply is connected to ground, so here I am going to write the Qn plus 1. So if R and S is 0 and 0, if this is 0 means open, so here you will get 1 and 1, and for 1 and 1 you are getting invalid. So you are getting here invalid. Now the second, if this is 0 1, if R is 0 means open, and if this is 1 means this switch closed, means this is connected with 0. So this is 1 and this is 0. For 1 0, for 1 plus anything, this is 1, this complement you are getting here 0, and this 0 plus this is 0, 0 bar is 1. Output you are getting here 0. So for this you are getting output 0. Okay, no issue. For this 1 0, if this is 1 and if this is 0, if this is 1 and if this is 0, so R is 1 means this switch is closed. If this switch is closed, this will be 0, and if this is open, so this is 1. So 0 1 output will be here, you will get 1, and here you will get 0. This output is 1. So here you are getting output 1, and for 1 1, both the switch is connected. This is 0 0, output will be no change. In this case you are getting no change. So now I will ask you, what is the name of this circuit? For 0 0 you are getting invalid. For 0 1 you are getting 0. For 1 0 you are getting 1, and for 1 1 you are getting no change. For 1 1 you are getting no change. So already I tell you, examiner can provide you in any truth table if you are getting these 4 states. So you can say the name of circuit is SR latch. Either it can be active high, either it can be active low, but this circuit is a SR latch. This circuit is a, because 4 state you are getting. So when both is 1 1, then you are getting no change. It means if you are getting here 0, means this is set. If this is 0, it means reset. So this is nothing but active low SR latch. This is active low SR latch. Are you getting this point? This is active low SR latch. Clear? So this question has been asked in previous year GATE exam. So this thing you should know about NOT latch, SR latch as well as NOR latch, then NAND latch. Okay, now I am going to start a flip-flop. I hope this thing is clear to all of you. Okay, now I am going to start a flip-flop. Okay, now so first flip-flop is, so this, what is the first difference between what is the basic difference between latch and flip-flop? So what is latch? So latch and flip-flop, latch, and here I am writing flip-flop. Flip-flop is nothing but clocked latch. This is a clocked latch. So when you will apply clock into latch, that will become clocked latch. it means that is called flip-flop. Okay, so if suppose I am writing here one block, if I will provide here clock, if I will provide here clock, if I will provide here clock. Okay, suppose here we have two input, but all the flip-flop or latch we should have two output. One should have output and second should have output complement. Output always you have to return at upper portion and output bar always you have to return at bottom portion. Okay, here this is input 1 and this is input 2. This is input 2 and this is input 1. So now this circuit is, you can call this is a clocked latch. This is a clocked latch, and clocked latch is also called a flip-flop. Okay, clocked latch is also called flip-flop. Now here two kind of clock is possible. So this is a level triggered, this is a level triggered, and the second one is as triggered, as triggered. So in level triggered we have only one option, but in level triggered, sorry, as triggered we have two options, positive edge or negative edge. So here we have two options, positive edge and negative edge. Okay, I will discuss later these things. Okay, so first right now you should know this thing about what is a flip-flop. Flip-flop is nothing but clocked latch. So now here already we have studied right now one latch, that is SR latch. So how you can implement SR latch into SR flip-flop? What is a circuit of SR flip-flop? So if I will ask you what is the circuit of circuit of SR flip-flop? What is the circuit of SR flip-flop? So just you have to apply clock. So right now we are going to study, we are going to apply which clock? Level triggered. So right now our clock is level triggered, and generally clock is represented by like this. Clock is represented by like this. This is the time period of clock. So this is a T clock. And what is frequency? F clock is nothing but 1 by T clock. Okay, so now if I will ask you, sir, we want to implement SR flip-flop, circuit for SR flip-flop. So what will be the circuit for SR flip-flop? So already we have implemented by NOR. So just I am going to implement it by first NOR. This output is connected here and this output is connected to here, and now this is Q and this is Q bar. So in NOR circuit, in similar to Q, what you will write? R. So here this was R and here this was S. But here you have to apply a clock. But here you have to apply a clock. So what you can do? Can I write here one AND gate, and can I write here AND gate? Can I write, and here one common input I can apply, this is clock, and this is nothing but R, and this is nothing but S. So this circuit is nothing but SR latch, sorry, SR flip-flop. So if SR flip-flop you want to implement, so how many gates is required? Two AND gates, and two NOR gates, two NOR gates. Now sir, any another representation here? So SR flip-flop, SR latch, in two way you can represent. This is your SR latch, this block is your SR latch. Can I write? This is your SR latch. Now we have one more choice, by a NAND gate. But in NAND gate circuit you have to use two NOT gate. So in NAND gate you have to use two NOT gate here, and this output is connected to here and this output is connected to here. This is Q and this is Q bar, but now this is nothing but your S and this is nothing but your R. This is your SR latch, active, same, this circuit and this circuit both is same. Now you have to connect here clock. Then what we can do? You can do here one AND gate, you can connect here one AND gate, and both are connected with a clock. And now you can write, sir, this is S and this is R. Can I write? Okay. Now you can do here, sir, this bubble, this NOT gate you can remove from here and you can put here. This NOT gate you can remove from here and you can put here. So now if I will ask you which circuit is better, here in this circuit, again this is SR flip-flop, again this is SR flip-flop, and SR flip-flop is implemented by 4 number of NAND gate. So now if I will ask you which circuit is better, so definitely this circuit is better. So in real life always we prefer this circuit. Are you getting this point? So SR latch is implemented by NOR gate, but SR flip-flop is implemented by NAND gates. Why? here 4 number of NAND gate, here 4 number of gate, but here this is NAND gate, here NOR and AND gate. But in SR latch only 2 number of NOR gate, but if you want to implement by NAND, 2 NOT and 2 NAND was required. So if SR latch you want to implement, then you have to go with NOR gate. You have to go with NOR gate circuit. So here only 2 number of NOR gate is required. But if you want to implement, this is SR latch. This is SR latch. But if you want to implement SR flip-flop, so you have to go with this circuit by NAND gate. And here 4 number of NAND gate is required. Okay, so I hope this thing, many students are confused here. And okay, so now I hope your doubt is now clear. Okay, so many students are basically confused, sir, which circuit we have to represent. So the reason is clear to you. SR latch, 2 choices. In first choice, 2 NOR gate. In second choice, 2 NAND gate with 2 NOT gate. So where you will go? Definitely we will go with this one. Now you have to implement SR flip-flop. Okay, you have to implement SR flip-flop. So again you have 2 choice. This first choice, 2 AND gate and 2 NOR gate. Here 2 AND gate, sorry, 2 NAND gate and 2 NAND gate means 4 NAND gate. So definitely you will go with here. Okay, now so what is a SR flip-flop? Always we will use this circuit. Here this is Q, here this is S, here this is Q bar, here this is R. Okay, and clock is here level triggered. Clock is here level triggered. So now I am going to write here truth table for this. I hope this thing is clear to all of you. Okay, now I hope now this thing is definitely clear to all of you. Okay, now come to the point. Sir, what will be the truth table? So this is SR, and if I will write here next state. Now here important point is here, sir, what is the clock? So if clock is 1, if clock is equal to 1, then only this will process. If clock is 0, then what will happen? So here if I am writing, if clock is 0, you can write in this way. Sometimes you represent in this way, otherwise you can write if clock is 0, then S and R can be anything. If clock is 0, then what will happen? If this is 0, 0 dot ending 0, 0 dot ending 0, 0 bar is 1, here 1 and 1, and if here 1 and 1, here output is no change. So if clock is 0, output will no change. So output will not modified if clock is 0. It means this circuit will not work when clock is 0. Now if clock is 1, or you can represent in this way. So if clock is 1, then SR can be 0 0, 0 1 and 1 0 and 1. So 4 options is possible here, 0 0, 0 1 1 0 1, and all the case clock is 1. Either you can represent 1 or you can represent in this way. Okay, generally this arrow we use for the, edge trigger. So right now you don't write this thing. So just you can assume if clock is 0 or if clock is 1. Okay, now so for 0 0, so if this is 0 and 0, clock is 1, so 0 dot 1, you will get here 1 and you will get here 1. So first output is no change. So for 0 0, directly you can write, sir, S is 0, reset is 0. Neither set is working nor reset is working. So output will be Qn. Qn means no change. Now directly you can write, sir, for 0 1, reset is working. So output is 0 and you can write this is reset. Now this 1 0, this set is 1. If mean output is 1, means set. If 1 1, set and reset both are working, practically it cannot be possible. So you can write here don't care, and you can write this is invalid. You can write this invalid, and you can represent this circuit in this way. This is SR. Here this is clock, here this is clock, and always you will write here Q and you will write here Q bar. This is the representation of SR flip-flop. Okay, now the important thing, sir, if I will apply here level triggered and if I will apply here edge triggered, so in both this will provide you the same output. Yes. So for level triggered and for edge triggered, so for both you will get the same output. So all this output you will get for as the triggered clock or level triggered clock, edge triggered or level triggered clock. So for both the clock you will get the same output. So here equation you should remember for the next state. You can call this Qn plus 1 is nothing but next state. So what is the equation of next state here? So same equation previously we have written. Qn plus 1 is equal to S plus R bar Qn. S plus R bar Qn. You remember this characteristic equation for the SR flip flop. This is for flip flop, and previously we have written for the SR latch. Okay, but in gate exam, okay, latch question will be totally different and flip flop question will be totally different. Generally student will merge both the topic. No, both of the topic is totally different. Okay, and question level is also a totally different. Okay, so now, so this is for the SR flip flop. Again here table you can write for 0 0 Qn 0 1 0 1 0 1 1 1. Okay, this is a truth table. Okay, now here we can also write a characteristic equation. This is characteristic equation. What is excitation table? So you should also remember excitation table. What is the excitation table? Excitation table of this SR flip flop. So what is excitation table? Output versus input. So output, if you know present state and next state, Qn and Qn plus 1, then what will be the SR? So this can be present state 0, next 0, 0 1 1 0 and 1. If present state 0, next state is 0, present state 0, next state is 1. So you should remember this. So if present state is 0, next state is 0. If present state is 0, next state is 0. How you can write? So you can also find out value from here. Okay, you can also find out if you can say sir Qn is 0 and this should be again 0. Okay, and this Qn is 0. So here the result should be 0. It means S should be 100% 0. S should be 100% 0. And here sir, what can be R bar? Can be anything. Then R can be anything. So can I write 0 and R can be anything because already this is 0. Now the present state is 0, next state is 1. If means present state is 0, if here 1. So from this 0 you cannot make 1 from here. So S definitely should be 1. S definitely should be 1. Then sir, what will be R bar? Now the important thing, in SR flip flop you cannot apply this input. So if any input is 1, this is understood second input should be 0. If any input is 1, then second input cannot be 1. This is very important thing. So if S should be definitely 1, then R bar can be anything, but you cannot consider R bar anything. R should be definitely 0. So you cannot consider here 1 1. No, this will be wrong because in SR flip flop 1 1 input you cannot provide any way any time in the circuit. If this is 1, so 100% this should be 0. This should be 0. You have two choices, either 1 1 or 1 0. So you cannot go with 1 1 because for 1 1 circuit will not provide you output according to you. Clear this point? Now this is 1 0. If this is 1 and if this is 0, if this is 0, so this should be 0. Then S should be 100% 0. S should be 100% 0. And if this is 1, then R bar should be 0. Then R should be 1. So R should be 1. This is 0 1. Now for the 1 1, if this is 1 and if this is 1. So if you are considering here, if this is 1 and now if you are considering sir R bar is 1, then R should be 0. R should be 0. If you are considering here for the 1 and 1. So how you can make 1? Either you can make 1 from here or you can make 1 from here. If you are considering as SA1, suppose as SA1, if you are considering as SA1, suppose for example, if you are considering as SA1, so sir R bar can be anything. So in this situation, you cannot consider second input 1. Second input should be 100% 0. Now we have second choice. But already 1 0 you have used here. So it is better you cannot use this 1 0. So now you can create 1 from here. So if this Qn is 1 and R bar should be 1, then 1.1 will be 1. So R bar should be 1 means R should be 0. So here R should be 0. R should be 0. R should be 0. R should be 0. Then what can be the S? S can be anything. S can be anything. S anything you can use. So can I write in this way? S can be anything. S can be anything. So you can write in this way. You can write in this way. You can write in this way. Clear this point? Okay, so okay, so just confirm me. So this is 0x10 01x0. Okay, so sometime students are mainly confused in this portion and in this portion. In this portion and in this portion. So it is better you can remember directly this. Okay, because sometime two answer can be possible. Here two answer can be possible. Here two answer can be possible. So you should remember this. And here sometime also student are getting confused. Sometimes student use sir 1x. No, 1 don't care, you cannot use, because one input you cannot provide. Okay, so excitation table should be very important for the SR flip flop. Many students are wrong in SR flip flop. Okay, one more time I can explain this SR excitation table. You can see if this is 0 and if this is 0, so definitely S should be 0. S should be 0. Then already this is 0, then R bar can be anything, and 0 don't care. Can you use? Yes. But 1 you cannot use, means 1 don't care, cannot be possible. So first value is 0x. Now for 0 1, for if this is 0, if this is 1. So from here you cannot create 1. So S should be definitely 1. So if S is 1, R cannot be don't care, or R cannot be 1. So definitely R should be 0. R should be 0. Now if this is 1 and if this is 0, then you have to make here 0. So S should be 100% 0. And already this one. So R bar should be 0. So R will be 1. So this is nothing but 0 1. This was very simple. Now the last one, if this is 1 and if this is 1. So you have two choices. Either you can create 1 from here or you can create 1 from here. So if you will create 1 from here, if S is 1, so 100% R will be 0, and already 1 0 you have used. So don't go with 1 0. So you can create from here. So if this is 1, so R bar should be 1, so R should be 0. R should be 0, and already you have created from here. So S can be anything. So R should be 0 and S can be anything. So characteristic equation, excitation table and truth table should be clear to you. And now one very important point, here for level triggered and for edge triggered, both you will get the same output. So here it is not depending on the types of the clock, you can say either edge triggered or level triggered. In both the clock, SR flip flop will operate. So here two kind of questions examiner can provide you. This is a level trigger. So here clock is level trigger, and if I will write here like this, if I will write here edge, this is edge, this is edge. So this arrow indicate the edge. This arrow indicate the edge. If I will write here, this is S, this is R, this is Q, and this is Q bar. It means this is a level trigger. So here this clock is here this clock is as the trigger, as triggered, and this clock is level trigger. Okay, again here two kind of this as trigger clock they can provide. If they will provide here one bubble, it means this is a negative as trigger. If they will not provide you here this bubble, it means this is a positive as trigger. So directly we can judge the question. Okay, if here arrow is not provided, but and in question they have not mentioned, it means this is a level triggered clock. But if in the question they have mentioned, so according to question you can go. And here if this edge is given, means this is a positive edge trigger. If bubble is given, this is a negative edge trigger. Okay, so first in every flip flop circuit you have to first concentrate on the level triggered flip flop is given, or positive edge trigger is given, or negative edge trigger is given. Okay, so this thing should be clear to you. This thing should be clear to you. Okay, this thing should be clear to you. And here excitation table is very important, because many time many students are wrong. Why students are wrong? The reason is here, because one input you cannot use. One input you cannot use. I hope this thing is clear to you. Okay, now I hope everything is clear to all of you. I hope everything is clear to all of you. Okay, now here one important thing. Okay, and this question is already asked in GATE exam. Can you create a square wave, means 0 1 0 1 or 1 0 1 0 toggle output? Can you create a toggle output by using NAND latch? By using NAND latch. This thing is clear to all of you. Now suppose we have one this NAND latch. Suppose we have one NAND latch circuit like this. Okay, like this. Okay, like this. Now propagation delay of this and propagation delay of this is same. Now suppose this is gate A and this is gate B. Then I can say propagation delay of A and propagation delay of B. Both the delay is same. Okay, both the gate delay is the same. Now I want to create here, and suppose delay you can assume suppose 1 millisecond, and suppose I am assuming this is 1 millisecond, 1 millisecond. And what I want here output like this. I want here output like this 0 1 0 1 0 1 by using this latch. Okay, and this is 1 millisecond. I want this is 2 millisecond like this. For 1 millisecond 1, then for 1 millisecond 0, for 1 millisecond 1, for 1 millisecond 0. So can we create, yes or no? So can we create any input you can use? Input is in your choice. Input is in your choice. Any one input you can provide. So now my questions, can we create a square wave from this NAND latch? Yes or no? So now my question is, can we create a square wave? Can we create a square wave, okay, by this NAND latch? By this NAND latch. By this NAND latch. Okay, yes or no? What you feel, yes or no? This is a previous year gate question from computer science branch. This is a best level of question. Okay, this is a very, very high level, and this is a very, very best level of question. Okay, and this question is from, you can say, latch, because clock they have not used. Because they have not used here clock. Now tell me, what will be the answer of this question? 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 Please tell me. Please tell me. I am waiting for your answer. Please tell me, what will be the answer of this question? I am waiting for your answer. Can we create, yes or no? This is very, very good level of question. Okay, in previous year examiner asking this category of question. Please tell me. Okay, so just I want to explain you here. Okay, you are saying yes, you are saying yes. Okay, how it can be possible? So now you can see how it can be possible. So first I will provide you here this two inputs. So first I will provide you here, if I will provide here 0 and 0, suppose if I will provide here 0 and 0, 0 and 0, then what will be the output? Then what will be the output? So here output will be 0 dot anything, this is 1, 0 dot anything 1, and suppose here previously anything this was, so 0 dot anything, here you will get 1 and here you will get 1 at same time. So at same time is, if I am going to write, suppose initially this was 0 and this was 0, so same time both will be 1 here. Both will be 1 here. So same time both will be 1. Okay. If you have provided here 0 0, if you have provided here 0 0, so this is 1, this is 1. Now this will be 1 and this will be 1. And 1 dot 0, this is 0 bar 1 and this is, both will be 1 1. Both will be 1 1 till you are not going to change. Till you are not going to change the input. So if you will not change the input, you will get this output. Are you getting this one? Now the important is, now suppose we have provided 0 0, then after some time, if I am going to change this 0 1, suppose after some time if I am going to change, this is 0 same and this is 1, suppose for example, then what will be happen? Already this was 1 many time before and this was 1 many time before, so this will be 1 0 and this will be 1 1. If this is 1 0, 1 0 means 0, 0 bar you will get 1, but this is 1 1, but this is 1 1, 1 bar will be 0. So same time, after some time, after 1 millisecond, so when you are going to provide, suppose in this time, suppose here we have provided 0 0, then after some time if I am going to provide here 0 1, then after this delay, this 0.1, 0.1, 0 bar is 1. This is going to become 1 for next 1 millisecond. Okay, now for next 1 millisecond this was 1, but after 1 millisecond this is 1 dot. Already this was initially 0, this is going to be 1, and this was 1, then 1.1, this will become 0. This second input will become 0. Okay, after 1 millisecond. Now you can see it means now at this point this is 1 and this is going to be 0. This is going to be 0. Now again you can see. Now again you can see. Now this is going to be 0, 0.01, and this is 1.10, 1.10. So this is not going to be toggle. How we can create a square wave from here? How we can create a square wave from here? This was my question. So if I will change, suppose input 1 and 1. Suppose if I will change input 1 and 1, then what will happen? Now if I will change both the input 1 and 1, then what will happen? If this was 1 and this was 1, for 0, 0, both the output was 1, 1. Both the output was 1, 1. So now you can see if this is going to be 1, 1, if this is going to be 1, 1, then what will happen? So if I am going to change this 1, 1 at this point, then what will be happen? So if this is 1, 1, previously this was 1 and 1, and now if this is 1, 1, then 1.1, this 1 bar 0, this will be 0, and 1.1, 1 bar is 0, both will going to be 0, 0 after 1 millisecond. So when you are doing 1, 1, both the output will be 0, 0 after 1 millisecond. So this time will be 1 millisecond. Then after 1 millisecond, at same time, this both the output you are getting 0, 0. Then again, this will become 0, this will become 0, 0.1. 0 bar is 1, and this 0.1, 0 bar is 1. Both will be 1, 1. Then again after 1 millisecond, both will be 1, 1, and both will be 1, 1. Both will be 1. Then again both output is going to be 1. Then again 1 dot, this is 1.1, 1 bar is 0, 1.1, 1 bar is 0. Again both the output is going to be 0 and 0. So you are getting this output, and both the output is same. Here the important thing is both the output is same, but circuit is working. You cannot say, sir, this circuit is not working. No, circuit is working, but here both the output you are getting the same value. Okay, but examiner are not asking both the output should be different. Just they are asking, can we create a square wave from this NAND latch? Yes, we can create. So here answer is 1. Here answer is yes. How we can create? So if you will provide, or if you will suppose start from invalid state. Invalid state means if both the output is 1, 1, both the output 1, 1, how you can create? If you will apply both the input 0, 0, both the input 0, 0, it means both the output is same, both the output is same. In this situation, then after some time, if you will provide this 1, 1, then you will get one square wave, and one square wave, and every state you are getting for 1 millisecond, or you can say propagation delay of each NAND gate. So this is a square wave, and this you can say T clock you will get, and this is 2 milliseconds. So frequency will be 1 by 2 milli. 1 by 2 milli means 1000 by 2 kilo. That is a 500 hertz. So here what will be the F clock? F clock will be 1 by 2 milli. You will get this is 1000 by 2, and this is nothing but 500 hertz. This is nothing but 500 hertz. This is the answer. This is very highest level of question. Generally in GATE exam, a student cannot handle this category of question. Okay, so the theory should be behind. What is the theory behind this? That should be clear to you. So what is the theory behind this? First, we are creating both the outputs same. Generally, student will start. Generally, what student will start? Generally, student will assume, sir, initially if this is 0, if then this will be 1. Generally, student will think in this way. But first, if I will create both the outputs same, so if you will apply here 0, 0, then both the output will be 1, 1. And then if you will apply either 0, 0, 1 or 1, 0 or 1, 1, then what will be the output? This is the important point. I hope this problem is clear to all of you. Okay, now I am moving towards next flip flop. Okay, so SR flip flop is clear to you, and this question is also clear to you. Latch, one more question already we have discussed. This question was also clear to you. Now come to the next flip flop. Okay, come to the next flip flop. So in next flip flop, I am going to discuss JK flip flop. Okay, then Then JK flip-flop. So in JK flip-flop, in SR flip-flop are exactly providing two states. But how many? Q is a single variable function. Yes, Q is a single variable function. And how many Q can be possible? So Q can be, sir, 0, Q can be 1, Q can be Q, and Q can be Q bar. So practically 4 number of output can be possible, but by using SR flip-flop only we are getting 3 output from here. One will be Q, no change, one will be 1, one will be 0, but we are not getting Q bar. So what is our target? We have to implement a circuit that will provide you all the 4 state. That will provide you all the 4 state. Clear this point? Okay, so now, and the name of that circuit is a JK flip-flop. So now the second one is JK flip-flop. JK flip-flop. So we can represent JK flip-flop in this way. This is J, this is K, this is Q, and this is Q bar. Okay, and like this. And now this is a level trigger. So first I am going to write this is a level triggered JK flip-flop. Level triggered JK flip-flop and level triggered JK flip-flop. So what is the level triggered JK flip-flop? So level triggered JK flip-flop, or you can say JK flip-flop. Sir, how we can implement? So by using SR flip-flop, we can implement. If this is SR, this is Q and this is Q bar. Here this is the clock. This is level triggered clock. If I will take here one AND gate, suppose this input is J, and again if I will take here one AND gate, and suppose this input is K. And what is the second input? This second input, this J, if I am going to connect from this Q bar, and if this Q is going to be connected with this K, this circuit will become a JK flip-flop. This circuit will become a JK flip-flop. Now you can write, sir, what is S? S can I write, sir, J, and this is nothing but Q bar, sir, J Q bar. And what is R here? Can I write, sir, this is K, K and Q. And what is the equation of SR? Qn plus 1 is equal to S plus R bar Qn. So from here JK equation easily you can find out. So sir, what is the equation for JK? S you can put here JQ bar. This is JQ bar plus what is R? R is KQ. So this is KQ whole bar into Q. You can write all R Qn, Qn and this Qn. What will be here? This is, sir, JQn bar plus K bar plus Qn bar. De Morgan's law you can apply, K bar plus Qn bar into Qn. Qn into Qn bar is 0. So you will get here JQn bar plus K bar Qn. You will get here JQn bar plus K bar Qn plus K bar Qn. You will get like this. So this is a characteristic equation of a JK flip-flop. Okay, so this is a characteristic equation of JK flip-flop, if you can remember this. Okay, so characteristic equation you should remember for JK flip-flop. Qn plus 1 is equal to JQn bar plus K bar Qn. K bar Qn. Answer, what is a truth table? So truth table easily you can remember. Already SR truth table we know. What is SR? This is for 0 0, no change. For 0 1, this is reset. For 1 0, this is set, and for 1 1, this is invalid. This is invalid, and invalid then you can write don't care. Okay, don't say output can be 0 or 1. No, input is invalid. Now then what will be for JK? So these three values are same. So for JK, for 0 0, again this is no change. For 0 1, this is 0. For 1 0, this is 1. And for 1 1, we can write here Qn bar. And for this one, we can write Qn bar. So now one thing you remember, if this is a level triggered JK flip-flop, if this is a level triggered JK flip-flop, so for level triggered JK flip-flop, we will get a race around problem. So for level triggered JK flip-flop, we will get race around problem. We will get race around problem. What do you mean by race around problem? So in JK flip-flop, when we will apply 1 1, you are getting Qn bar, but it is not stable. So in output you will get, so if I will write here, if this is a JK flip-flop, and if this is a level triggered clock, and if this is 1 and 1, so this output Q and Q bar you will get here, output 0 1 0 1. So output you are getting toggling 0 1 0 1 0 1. This is called race around problem. So in JK flip-flop for 1 1 input, your output is not stable, but that is valid. If you are getting 0 1 0 1, so here this is 1 0 1 0 1 0 1. It means when this is 0, this will be 1. When this is 1, this will be 0. But output is not stable. But what we want? we want stable output. So in this situation, and this situation is called race around problem. Then how we can remove this race around problem? There are so many methods. What we can do? First method we can do propagation delay of this flip flop. So propagation delay of flip flop. If propagation delay of flip flop is greater than propagation delay of flip flop is, suppose I am writing here clock. This is a level triggered clock. So if a propagation delay of flip flop is more than this pulse width, so pulse width of clock, then race around problem will be removed. But the important thing, if this propagation delay is more than this time, but greater, it cannot be greater than this time. So one first important point you remember, propagation delay of flip flop should be greater than pulse width of clock. This is the first point, and this should be less than time period of the clock. That should be less than time period of the clock. This is a first condition how we can remove race around problem. Okay, now the second condition, I hope everybody know this thing. Now the second condition, what is the second condition? Here the important thing is, many time examiner can ask question from here. So propagation delay of flip flop is more than, you can remember from here, more than this pulse width but less than this clock time period. Okay, but this method practically generally in real life we don't use, but in GATE exam they can ask question from here. Already they have asked question from here. So first relation should be clear to you. If this is a level triggered clock, and if you want to remove race around problem, or if you want proper operation of this, so propagation delay of this flip flop should be more than pulse width of the clock but less than time period of the clock. This is very important point. Now the second important thing is here. What is the second? Second, by using master slave JK flip flop. Okay, in master slave JK flip flop, generally we use two number of flip flop, first JK and second JK. So in master slave JK flip flop, we will use two number of JK flip flop. We can write this is JK, this is Q bar, and again one JK and one JQ and Q bar, and this is a level triggered clock. But here by NOT gate we will connect this second clock, and this is your clock. Okay, now, and this output is connect to next, and this output is connect to next, like this. This is a master. We can say this flip flop is master and this flip flop is slave. So practically this design we cannot use. Why we cannot use? Because here two number of master slave, two number of JK flip flop we are going to use. Now the third method. So in real life we use third method. Okay, so this three method you should remember. They can ask question from here. Okay, so can I remove this? Now I hope you should know what is a race around problem. Okay, you should know characteristic equation, you should know the truth table of JK flip flop. Okay, and the third method is as a trigger. I can write here, third method is by as triggered JK flip flop, as triggered JK flip flop. So as triggered JK flip flop is, you can say same with this, but here what you are doing, you are increasing this with respect to this. But in S triggered JK flip flop, what we are doing, we are doing pulse width of the clock, pulse width of the clock, we are doing very small. So this we are doing very small. So if this is very small, pulse width of the clock is, if this is very small, so definitely this value should be less than this. So two things is here happening. In first method you are increasing this propagation delay with respect to this. In second method this is fixed, we are decreasing this value. Okay, we are decreasing this value. So how? Sir, we have, this is a level triggered clock. So what is a S triggered clock? This is your level triggered clock. Then what is S triggered? So S triggered just we can represent in this way. But in real life this is your positive S triggered. positive as the clock. This is your positive as clock, but generally we don't represent in this way, we represent in this way. So generally how we can represent this, just we can write here one arrow, just we can write here one arrow. But what is the meaning of this clock? This is not exact clock, actual clock is this one, actual clock is this one. It means for very small duration of time here, this is going to be 1. So this is going to be 1 for very small duration of time. Here this is going to be 1 for very small duration of time. For remaining time this is going to be 0. It means pulse width of the clock is very less than propagation delay of the flip-flop. So your problem is solved. Now here two category of level triggered clock we can use, one positive and one negative. One positive as and one negative as, sorry, two category of as triggered clock. Okay, one positive as and one negative as, one positive as and one negative. So actual flip-flop is, so JK flip-flop always we use as a trigger. So JK flip-flop, if you want to represent JK flip-flop, so don't represent level triggered, always JK flip-flop will be as a trigger, because in level triggered flip-flop you will get a problem race around condition, you will get a problem race around condition. So always JK flip-flop, two kind of JK flip-flop you can get. This is JK, here we can put here as this is your positive edge, this is the positive edge JK flip-flop, this is Q and this is Q bar. And one more we can use negative edge, here we can use negative edge, this is J and this is K, this is JK, this is Q and this is Q bar. And what will be this clock? This clock is negative edge, this clock is negative edge. So we have two number of clock, one is positive edge and second one is negative edge. Then how you can represent negative edge? So here negative edge, how you can represent? So in negative edge clock means only in this time you will get some positive value. So what is the meaning of negative edge? Meaning of negative edge is like this. Many students don't know what is the meaning of negative edge. So this is a negative edge, this is a negative edge, this is a negative edge. So for negative edge clock for very small duration, but in this situation for very small duration we will get a positive value of the clock. But in real life how you can represent this? So this is your actual clock, this is your actual clock. So how we can write? We can write here one arrow, we can write here one arrow. So this represent negative edge of clock and here this arrow represent positive edge of clock. Are you getting this point? But what is the meaning behind this? This thing should be very clear. For positive edge means in this duration only you are getting clock, and for negative edge only in this duration you are getting a clock. Okay, sometimes student this write in this way, this is totally wrong, this is totally wrong, this is totally wrong, this is totally wrong. So don't write in this way. So now we have two category of JK flip-flop, either positive edge or negative edge. Okay, so third one is level triggered. But level triggered JK flip-flop, if you will use, if this is JK, and if I am going to write this is a level, this is a level clock, this is a level clock, and you can write this Q and Q bar. So we have three category of JK flip-flop. In level triggered JK flip-flop we will get a race around problem. Race around problem, how you can eliminate? This three method you should know. Examiner can target question from here, and in real life we will use always positive and negative edge. That's why all the questions from JK flip-flop you will get either positive or negative edge of the clock. And meaning of positive edge, negative edge should be very much clear to you. So positive edge we will represent in this way, positive edge we will represent in this way. We can write here arrow, we can write here arrow. Negative edge we can represent in this way, negative edge we can represent in this way. We can write here arrow and we can write here arrow. Level triggered we don't represent here, any arrow, but sometime if you want you can represent here, but sometime examiner don't represent here arrow. Okay, but every flip-flop will be S trigger. Okay, so in GATE exam first always you can see if question will be provided that is a level triggered or S triggered. If S triggered, positive S triggered or negative S triggered, either they will written in the question or by this diagram. Okay, by this diagram you can easily find out this is positive S triggered or negative S triggered or level triggered clock. Okay, so I hope this thing is clear to all of you. So now come to the point, sir, what is the excitation equation? What is the excitation table? What is the excitation table of JK flip-flop? what is a excitation table of JK flip-flop. So you should know about the excitation table of JK flip-flop. First characteristic equation, Qn plus 1 is nothing but JQn bar plus K bar Qn. This is a characteristic equation, and truth table you know very well. Sir, what is the excitation table? And this is very, very important, excitation table. So what is excitation table? What is excitation table? So excitation table we can write, this is Qn, this is Qn plus 1, this is present state, this is next state, and this is J and this is K. Now this is 0, 0, this is 0, 1, 1, 0 and 1, 1. Now the important thing, sir, all the input is possible in the JK flip-flop or not? Yes. So here no limitation in the JK flip-flop. So here no limitation in the JK flip-flop. So easily you can find out all the value from here, but if possible you can remember. So just I am going to write this equation again. Qn plus 1 is equal to JQn bar plus K bar Qn. Okay. Suppose many students directly remember this, but suppose if you forgot in GATE exam, so this equation definitely you should remember. So by this equation you can write the value. So suppose if this is 0 and if this is 0, so this will be 1. Here you want 0, it means this K bar can be anything, so K can be anything, can I write? And if this is 1, then definitely J should be 0, so this is 0x, easily you can write. Now for the second, this is 0, 1, so Qn is 0, so this is 0, so this will be 1 and this is 1. So if you want 1 from here, and if this is 1, so definitely this J should be 1, J should be 1, and if this is 0, so 0 multiply anything will be definitely 0. So you can assume this K bar can be anything, so K can be anything, so I can write this, don't care. Now the third value, this is 1, 0. So for the 1, 0, if this is 1, so this Q bar will be 0 and this here Qn plus 1 is 0. What you want here 0, so 0 dot anything will be 0, so J can be anything here, okay. And this is 1, so K bar should be definitely 0. If K bar should be 0, so definitely K should be 1. So this is 1. Some student remember 0x, 1x. Then opposite of this, 1x, then x1. Okay, now the last one for the 1, 1. If this is 1, this will be 0. This is 1. So if you want 1 from here, so this 0 dot anything will be 0. So you cannot create 1 from here. So J can be anything. So J can be anything. If this is 1, so K bar should be 1. So K should be 0. So K should be 0. This is excitation table. Sometime how student will remember, this is 0x, this is 1x. Then this is a you can write this 0x, then sorry, this is 1x, then this is 1x. So this left to right, this right to left, and this left to right, this is right to left, like this. Okay, but if you forgot in another way, 0x, 1x, x1, x0, you can remember like this. If suppose you forgot, so from this equation you can find out. So for the JK flip-flop, this thing should be definitely remembered to you. What is characteristic equation, what is excitation table, and what is the truth table. Truth table easily you can remember. Okay, one more time, just I am going to write, sir, this is J, this is K, and this is next state Qn plus 1. So for 0, 0, no change. For 0, 1, this is 0. For 1, 0, this is 1. And for this 1, 1, this is Qn bar. So now can I write Qn bar? Yes, you can write. And when you will get Qn bar, if you will use S triggered clock, then always you will get Qn bar. Now one device you have find out, and the name of that device is JK flip-flop, which will provide you all the 4 states. Which will provide you all the 4 states. 1, 0, no change, and complement of the previous state. Only 4 states can be possible. Now we have achieved our target. Okay, so this thing you should remember. Okay, so now, sir, should we study next flip-flop? No. Now, no, we don't have to study another flip-flop because already we have achieved. Now we can use application of JK flip-flop. So now I am going to start application of JK flip-flop, and application of JK flip-flop is a D flip-flop and T flip-flop. D and T flip-flop is practically not a separate flip-flop. That is the application of. That is the application of JK flip-flop exactly. But generally we write T flip-flop and D flip-flop. You can write. But according to me, how you remember, D flip-flop and T flip-flop is a application of JK flip-flop. So, sir, what is the application of? So here now I can write application of JK flip-flop. Okay, so first in one circuit I want to find out 0 and 1 set and reset. So already set and reset flip-flop you have. Now one circuit I want to design. Suppose from this JK flip-flop you want to design 3 circuit. You want to design 3 circuit. First circuit name is set reset. So this is set reset. And in second circuit, what I want here in second circuit, this is 2 input, this is 2 output. In second circuit, I want no change. So in second circuit, I want no change. And in third circuit, I want always toggle. In third circuit, always I want toggle like this. So this is the 3 application of, you can say, JK flip flop. Now JK flip flop, if you want all the 4 output, you can use JK. But if you want only set reset, you can go with set reset. If you want only no change output, so that will be the D flip flop, and that is called data flip flop. And if you want toggle of the output or previous state, you can say that is a T flip flop. So the name of this circuit is a D flip flop, and the name of this circuit is T flip flop. Clear? So if we are getting only this one output, that is T flip flop. If we are getting only this output, that is D flip flop. If we are getting this 2 output, that is your SR set reset flip flop. Okay, so now I am going to start application of this application of this JK flip flop. Clear this thing? Application of this JK flip flop. Please just confirm me everything is clear till now. Okay, everything will be definitely revised from here. Okay, so this race around problem should be definitely clear to you. Now first I am going to take T flip flop, then I will jump to the D flip flop. First I am going to take T flip flop. Okay, now so my first question, if you want to design T flip flop, so only this thing is required, only one state is required. It means both the inputs should be same. So if I want to design T flip flop, from ZK flip flop, so just I have considered ZK flip flop, this is Q and this is Q bar. Okay, clock, later I will discuss which clock is possible here, level triggered or S trigger. Okay, or both can be possible. So first what I want, sir, toggle. So if you want toggle, then both inputs should be same. How both inputs should be same? So what we can do, just I will connect both the input in this way. So if I will connect both the input, J and K is same, and if I am saying this value is T, so either JK should be 0 0 if T is 0, or JK should be 1 and 1. So only 2 condition is possible, either 0 0 or 1 1. 0 0 everywhere you will get no change. So in every flip flop you will get one output, one state is no change. So if T is 0, output is no change, and but if T is 1, you are getting toggle. So if suppose if you will use level triggered, and if in level triggered, if you will provide JK11, so you will get race around condition. It means here in T flip flop, this clock should be 100% as a trigger. So as a trigger, so this clock should be 100% as trigger. This cannot be level triggered. So this is very important point. If in any questions you will get T flip flop, so you have to concentrate that is a level trigger or S trigger. 100% examiner will provide you as a trigger. Clear this point? This is the first important point. So what we can say here, truth table, sir, this is T and this is next state. If this T is 0, then Qn plus 1 will be no change. So can I write Qn? If this is 1, so this will be Qn bar. Sir, what is the characteristic equation? JK characteristic equation we know, Qn plus 1 is nothing but, sir, JQn bar plus K bar Qn. So from this you remember J and K is same. So here J is equal to K is equal to T. So just you can put the value. Sir, then Qn plus 1 is equal to, this J is T, TQn bar plus T bar Qn. So sir, this is nothing but XOR gate. So Qn plus 1 is nothing but T XOR Qn. You remember directly this. So what is the characteristic equation of T flip flop? This is T XOR Qn. Okay, I hope definitely you remember this value. Okay, this is nothing but T XOR Qn. 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 So now this is the truth table and this is the characteristic equation. Sir, what is excitation table? If you remember my previous classes, already we have studied, sir, A XOR B is equal to C. Then we can write A XOR C is equal to B, and we can also write B XOR C is equal to A. Okay, all the conditions are true. So can I write from here? If you want to find out T, so can I write T is equal to Qn XOR Qn plus 1? Can I write? So if you can write here, so easily excitation table you can draw here. Excitation table means output qn and qn plus 1. Okay, and your input is t. If this can be 0 0, this is 0 1, this is 1 0 and 1 1. So how you can find out? So you don't have to put value in the equation, directly you can find out from here. T is, if this is 0 0, 0 0 XOR is 0, 0 1 XOR is 1, 1 0 XOR is 1 and 1 1 XOR is 0. So directly you can write this excitation table. Excitation table, characteristic equation, truth table, and here the important point. Here level trigger can be used. No, level trigger we cannot use. So this is the T flip flop. Now, sir, where we can use the T flip flop? Why we are studying this? So to design counter. So to design counters, we generally use T flip flop. Okay, so we generally use T flip flop. Sir, what is the use of T flip? If you will use, you can use JK flip flop because JK is nothing but T. Okay, if you are using T is nothing but JK. But if you will represent JK, so the circuit will be looks like say complicated circuit. That's why to design counter circuit, we can represent by T flip flop. Okay, so what is the use of T flip flop? To design counter circuit. Okay, where output should be required change, where output change is required, where output change is required. So we can go with a T flip flop. Clear this point? Okay, clear this point. So now how we are going to design here JK flip flop by using JK flip flop, T flip flop. Okay, now come to the next point. Now come to the next flip flop, that is D flip flop. Now our next target is a D flip flop. I hope this thing is clear to all of you. Now the next target is a D flip flop. Okay, our next target is D flip flop. Sir, what is D flip flop? Sir, what is D flip flop? So next target is our D flip flop. Our next target is D flip flop. Okay, now D flip flop. So D for, sometimes student will say delay flip flop. No, D for the data flip flop. Okay, don't say, you can say but don't say. According to me, always you have to say here data flip flop. Okay, don't say delay flip flop. This is data flip flop. Now, sir, so what is our requirement? So here already you have used this two state from the JK. Sorry, you have used two state from the JK, QN and QN bar. But here I want only, if you are providing input 0, output is 0. If you are providing input 1, output is 1. So I don't want here QN bar state. So if I don't want here QN bar state, so how we can represent D flip flop? If this is J, this is K. So what can I write? If just I am going to write this not. Okay, so if I am going to write this D, wait for that. Okay, now, so what equation you will get? What equation you will get? So here this JK flip flop equation is J QN bar plus K bar QN, and here J you are writing D, and K bar will be again, this K will be D bar, so K bar will be again D. It means J and K bar will be D. So here this is nothing but D QN bar plus again K bar is D QN bar, and here QN, sorry, this is Q, na? This is QN. So D, if you will consider common, QN plus QN bar. So QN plus QN bar, you will get this is D. So this circuit only providing next state is D. Okay, so just you can represent in this way. Now the important thing, are you providing here JK 1 1 in any situation? No. So here J and K is always complement to each other. Here J and K is always complement to each other. So this is very important. Here if this is a clock, if here this is a clock, so here you can use level clock or edge clock. So here both clock can be used. So here both clock can be used. This is very important point. Both clock can be used. Both clock means either level triggered or as a trigger. This is very important point. This is very important point. Everyone, this is very important point. So in D flip flop, never you will get a race around problem. Why never we will get? Because J and K is complement to each other. It means always J and K input will be either 0 1 or 1 0, either 0 1 or 1 0. Never you will get both the input are 0 0 or 1 1. Only you are getting here input either 0 1 or 1 0. Okay, so here race around problem never you will get. Race around problem never you will get. Okay, so just this thing you should remember. Sir, then what will be the truth table? So this is input D and this is Qn plus 1. If D is 0, then output next state will be 0. If D is 1, next state will be 1. Okay, so if D is 0, next state will be 0. If D is 1, next state will be 1. What you are getting in input, you are getting in output. So what will be the Qn plus 1? Already you have written here. Sir, characteristic equation is this is equal to the. So here next state is independent of the previous state. Here next state is independent of the previous state. So if you want to store here the data, if you want to store your data, you can provide 0, you will get 0 here. If you can provide here 1, you will get 1 at output. Sir, what is a excitation table? So if you remember this characteristic equation, easily you can write the excitation table. So what is D is equal to Qn plus 1? So already I tell you Qn plus 1 is independent of the previous state. Similarly, you can also say, if you want to write from here, so D is equal to Qn plus 1. So here D is independent of Qn. So what is excitation table? So here excitation table is, so what is the excitation table here? Excitation table is Qn and this is Qn plus 1 and input is only one input D. If this is 0 0 0 1 1 0 1 1, from here directly you can write is equal to Qn plus 1. This Qn plus 1 you can copy, this is 0 1 0 1. So I hope excitation table is remembered to you for all the gates: SR flip flop, ZK flip flop, T flip flop and D flip flop. Only in SR flip flop you have to concentrate, because we have one limitation in SR flip flop, means one input you cannot provide. Clear this point? Okay. Now one more important thing. Suppose if one student want to make in this way, suppose JK, and suppose if here not gate, and if suppose like this, and this is your clock, and this is D, then what will be the output? In this case, what will be the output? Suppose, so in this case, sir, this is Qn plus 1 is equal to JQn bar plus K bar Qn. Okay, now again here race around condition you will not get, because if this is 0, so this will be 1 and this will be 0, so J and K will be either 0 1 or 1 0. In this case, sir, J is equal to D bar and K is equal to D. So K bar is equal to D bar. You will get like this. So from here, sir, what is Qn plus 1? So Qn plus 1, this is D bar will be common, and this is Qn plus Qn bar, and this value is 1, you will get D bar. So here Qn plus 1, you will get D bar. So sometimes student will do wrong in this way. So be concentrate here. This not get you have to apply here. Okay, not get you have to apply here. So this circuit is not a D flip flop. This circuit is not a D flip flop. Okay, now come to the point, very important point. Now I want to discuss here. So now in D flip flop, so D flip flop, I hope this thing is clear to you. Now D flip flop, how we can remember, or how we can represent this is D flip flop like this. This is Q and this is Q bar. This is Q and this is Q bar. Now here suppose this is a clock. This is a level clock. This is a level clock. And one more D flip flop I am going to write here. One more D flip flop I am going to write here. And if this is D, and if this is D, and here this is clock, here this is clock, and if here this is edge, here this is edge. Which kind of edge? Either positive or negative. I have considered a positive edge. And if this is Q and if this is Q bar. So, sir, will you get both the circuit will work properly or not? Yes, both the circuit will work properly. So, here generally examiner will target question from this topic also. So, now we can write the different name of both the circuits. So, practically this circuit is called D flip flop. D flip flop. Sir, then what we can call this circuit? This is also D flip flop, but you have to differentiate both the circuit. So, we can call this circuit a D latch. This is very important thing. Already we have studied not latch, we have studied not latch, we have studied SR latch, we have studied NAND latch, and NOR latch. Okay, now the last important thing is this is a D latch, but D latch is different. So what is the difference in between in these two? Here no clock, here no clock, but here clock is present, here clock, but which clock? Level triggered. So if I will ask you in which flip-flop you can use level triggered clock, in SR flip-flop, yes, you can use, because in SR flip-flop 1 input you cannot provide. So in SR flip-flop you can use level triggered, in T flip-flop you cannot use, in JK flip-flop you cannot use, but in D flip-flop you can use, and sometime we can use this. SR latch we don't study, already we have studied SR latch without clock. Okay, so now this is a D latch also, but here clock is present. But which kind of clock? Level trigger. So if examiner will provide you D flip-flop with level triggered clock, this circuit is called D latch, and if D flip-flop is connected with S triggered clock, this is called D flip-flop. So now I am asking you one question, okay, and for one question we have to find out output for D flip-flop and D latch. Examiner can target question from here. Okay, so now I am going to take one question from here. Okay, so now I am going to take one question from here, and now if I will ask you, sir, what is the use of this D flip-flop to implement a resistor? So D flip-flop we can use to design counter circuit. D flip-flop is used to design D flip-flop is used to design, okay, resistor circuit. So in resistor we use D flip-flop, not latch. Flip-flop means, if I am saying D flip-flop means as a trigger, okay, and if you want to design counter circuit we can use D flip-flop. Okay, so what is the application of D flip-flop and what is the application of D flip-flop? This thing should be clear to you, why we are studying this too. Okay, so now suppose just I am asking you one question. Suppose we have one input. Suppose we have two circuit. Like this, and suppose this is D. Here this is a clock. This is a as a triggered clock, which has positive edge. And now this is Q and this is Q bar. Okay, now suppose we have one more circuit. Now this is D, and here this is a clock, but this is a level triggered clock. Okay, and now this is not edge, this is level triggered, and this is Q and this is Q bar. Now if same input I am providing you both the circuits, so now suppose for example this is your clock, and this is your clock, and this is the most important thing, this is your clock. Okay, now suppose our input data D is given in this way. Suppose here this is 0, here this is 1 is going to be, here suppose this is 0, this is 1, this is 0 again, suppose here this is again 1, then 0, again 1, like this. Again here this is 0, again this is 1, again here this is 0, again here this is 1. Now again if this is going to be 0, again if here this is going to be 1. Suppose this input D is given, suppose I can write here in this way, this is the first time period, second time period, here this is third time period, like this. Okay, this is the input, this is your clock, clear this one. Now if I will ask you, sir, this is output of this, I can say flip-flop output, and can I say this is latch output. So what is the difference between these two output and what will be this two output? So for flip-flop output, how we can find out? This is a positive edge trigger, just you can write this clock, just you can write here arrow for the positive edge. Now you can see what is the output. So just I am writing flip-flop output. So initially this was 0. When you are providing a clock, just you can see the input D will be read. If input is 0, output will be 0. So if input is 0, output will be 0 till when? Till the next clock. Again in the next clock, again this input is 0, then D is 0, again this will be 0. Again in the next clock, if this D is 1, so again this will be 1 till next clock. So till next clock, again in the next clock, if input is 0, so this is going to be 0. So this is the output of this first one circuit. So we can say this is a D flip-flop output. Then sir, what is a D latch output? So D latch output, what you can do for this positive, this D value you can copy paste. For this positive you can for this positive you can put just copy and paste D value, and for the negative value you know no change, so last state will be copied. So just I want to draw here, sir, what will be the here latch output. So the latch output is initially, just I am assuming this was 0. So this as it is you will copy here. So this as it is you will copy here for the half time period, and then the last state and the last state and this last state will be continue here. So for the positive state, as it is what you have applied in the input, so for the positive level, so when you are receiving the clock, so here you are receiving clock in this time, in this time, in this time, in this time. So what is here at the input, same value you will receive at the output. This is the D latch output. This is very important thing. Okay, now, and this is most important topic of IITs. Generally they will target question from here, but generally a student exactly don't know what is the D latch. Most of the students don't know exactly what is the D latch. So now I hope this thing is clear to you. If you know, that is very good. Okay, but if you don't know, so at least you should remember this. Now again for this, again the same thing you will copy this 0 here, this is 1. Okay, again this is 0, and again this is 1, like this. Okay, now this at the last moment this is 1, so this 1 will be continue for the negative. Now again in this position the same thing will be copied in this way, the same thing will be copied in this way, and now again this is stop at 1, so this 1 will be continue. Now again this you have to copy it. So first this will reach to 0 because this is going to start from 0, and you will get like this. So this will be the output for the D flip-flop when clock is level triggered, when clock is level triggered. So what is latch exactly? So for this point, exact same as is what you are providing input, you are getting the output. So we can say this is one kind of latch output. So latch output, you can say that is independent of the clock. So in this situation, what is the input you are getting at the output? So we can say this is nothing but latch output, or in second way you can say, if in between clock output is going to be changed, that kind of output is called latch output. But in flip-flop output, in one clock time period your output is stable, in one clock time period your output is stable, in one clock time period your output is stable, in one clock time period your output is stable. But in latch output, in one clock time period you can say output can be modified. So if in any time period output is going to be modified, we can say that kind of output is called latch output. Are you getting this point? So just you can note down, and this is very important thing. So what is a D latch output and what is a D flip-flop output? The important point is, in both the cases you are applying here clock. In one time you are applying level clock, in second time you are applying here second time, that is a as a clock, that is a as a clock. So I hope this thing is clear to all of you. So now if anybody have any doubt, just ask me. Now here sometime in GATE exam they can ask question to implement any one flip-flop by any another flip-flop. So suppose if reverse question I will ask you, implement JK flip-flop by D flip-flop, So if you want to implement JK flip-flop by D flip-flop, it means you have D flip-flop. So first you have to create image what they have given. So they have given D flip-flop, they have given, and here this is S triggered clock, because you want to implement JK flip-flop, and this is Q and QR. But here the input should be JK, so here input should be J and K. So J and K. So you have to require one circuit here. So here one circuit is required. This will be connected J and K, and this output will be connected to D. And here you can also use Q bar and Q if required. Which is not necessary, it will be required or not. So here you have to find out this circuit, and that one input will be J, second input will be K, and you can also use here Q and Q bar. So if you want to implement one flip-flop by another flip-flop, what you can do? So if an examiner will ask you by D flip-flop, so by D flip-flop, don't go with truth table or excitation table. Directly by characteristic equation we can design. How? So first you can write JK flip-flop characteristic equation. So this is Qn plus 1 for JK. This characteristic equation, we know this thing, JQn bar plus K bar Qn. Okay, same for the D flip-flop. So this is Qn plus 1 for D flip-flop is nothing but D. You can equate both the equation. So if you will equate both the equations, so you will get D is equal to JQn bar plus K bar Qn. So what you want here, you have to find out D in terms of J, K and Q bar. So you have to find, so just you find it here. This D function. What is D? JQn bar. So just you can write here, sir, 1 AND gate, and this is K, you can also write here 1 AND gate. So K bar Qn, you can write here K bar, and this is nothing but you can write this is Z, and this is nothing but K bar. Now K bar dot Qn. So K bar, this is your first input K bar. You can add the first input K bar, and this K bar is connected with this K bar connected with Qn. So K bar into Qn, and this Z is connected with here, this is a Qn bar, and now both having connected with OR gate. OR gate. So this is the circuit. So this question already asked in GATE exam many times. Same question. Okay, so to implement any flip flop by any another flip flop, so you can equate the characteristic equation, but if you want to implement by D, but if you want to implement by any another flip flop, you have to go with here excitation table and truth table. So by excitation and truth table, how you can handle this question in GATE exam? Just I want to tell you. Then conversion of flip flop easily you can do. Then conversion of flip flop easily you can do. Then conversion of flip flop easily you can do. So how you can implement? So what you want here? So you want here D. D can be a function of J, K, Q, N and Qn bar. Okay. So this you have to find out a function of D. So the last column should be D. Last column should be D, and this should be a function of. So what you have to write here? This JK truth table. So truth table of JK, and for D excitation table. So which table, which flip flop you want to design? That truth table, because you want to design that, and by using which you want to design that excitation table. So just JK truth table, if I am going to write, this is JK Qn bar. So this long truth table you have to write, this long truth table you have to write here, and this is Qn plus 1. So for this 0 0 0, for this 0 0 1, for this 0 1 0, 0 1 1 1 0 0 1 0 1, 1 1 0 and 1 1 1. So what will be the Qn plus 1 for if this is 0 0, no change, so this is 0 1, for 0 1 always 0, for 1 0 always 1, for 1 1 toggle, so this is 1 0. What will be the excitation table? For this is a truth table for JK. Sir, what is excitation table? You can already here Qn and Qn bar is given. So for 0 0, Qn plus 1 you can copy. So this is 0 1 0 0 1 1 1 0. Now you can put this value in the K map. Now you can put this value in the K map. So here variable is JKQN. So this will be J. This will be K. This will be Qn. This is 0 0 0 1 1 0 and 1 1. This is 0 1. You can put the value 0 1 0 0. This is 0 1 0 0. Next triple 1 0 1 1 1 0. Then what you will get exactly? This two group you can form here. This two group and this two group. So what you will get from here? D is equal to, this is a truth, K map for D. So this value is K bar Qn plus, and what is this value? This is J into Qn bar, J Qn bar. And now you can implement the circuit. This is a 2 AND gate, 1 OR gate. 2 AND gate, 1 OR gate. You can also implement the same circuit in this way. This is NAND gate, and you can also write this is NAND gate. Because you know very well AND OR circuit is easily converted into NAND and NAND. Either this is AND or this is NAND. So this is the circuit. So any question easily you can do. So which you want to implement, that truth table is required, and by using which you want to implement, that excitation table is required. So excitation table many time useful in this situation. Excitation table many time useful in this situation. So I hope now flip flop is over from my side. All the theory part, all the concept part from the latch and from the flip flop. Okay, so now our next topic we will start, that is resistor and counter. Next topic we will start resistor and counter. I hope this thing is clear to all of you. So just confirm me. If anybody have doubt till now, please just confirm me. If you have doubt, just confirm me. Okay, so can we take one break, and after break we can continue. Okay. So today right now I will give one break, okay, to 7 to right now 7:30, and from 7:30 okay, so after half an hour 7:30 to 9:30, okay, again, and from 9:30 to 10:30 we will take a break, and from 10:30 then we will continue the classes. Still this topic is not going to be over. Okay, so after I will discuss register is very basic topics. Okay, mainly I will focus on the counters. I will focus on the state diagram. Okay, then I will focus on the especially counterparts. Okay, synchronous, asynchronous. I will also discuss on the propagation delay in the synchronous circuit. I will also discuss here setup time concept and hold time concept. Okay, and I will also try to complete ADC and DAC. Okay, so please just confirm me if anybody have doubt. Okay, please everyone reply. Okay, so after 30 minutes we will meet. So right now the time is your 7:05. At 7:35 we will meet. Okay, if anybody have doubt you can post here. Okay, thank you, take care. Hello everyone, welcome back. So now we will continue the session. So till now we have studied all the flip-flops and conversion of flip-flop also. Okay, and what is D latch? What is D flip-flop? Clear? Okay. So now, so everyone, one just confirm me. Audio is clear to you or not? Audio is clear or not? Just confirm me. Okay, so now what is the application of flip-flop? So you can say, sir, a flip-flop we can use especially to implement register circuit, to first one register circuit, or you can say sir counter circuit. This is a two basic application of flip-flop, and register generally we will represent by any flip-flop. You can represent by any flip-flop, or you can design by any flip-flop, but in general we represent registered by D flip-flop, and here counter by T flip-flop. Okay, that's why, because if you will represent by ZK flip-flop, so definitely circuit will look like a complicated circuit. Clear this point? Okay, so now here first we are going to discuss a resistor. Just I want to revise the resistor part. Okay, a resistor, because sometime examiner can ask you question from the resistor. So here resistor can be, especially generally we will study a shift resistor. So now I am targeting especially a shift resistor. So there are so many operation can be performed: serial in, serial out, serial in, parallel out, parallel in, parallel out, and parallel in, serial out. So first operation, if I will write parallel in, parallel in, parallel out. So in parallel out operation, how many number of clocks is required? So two category of circuit can be designed, but minimum number of, so here without clock, so this is 0 clock. I hope you remember this thing circuit, but sometime one clock is also required. So two category of different design. So in one design 0 clock, in second design 1 clock. So but we can prefer 0 clock. For second category of design, sir, parallel in serial out operation. So in parallel in serial out operation, that is n minus 1 clock, n minus 1 clock. If this is a 4-bit shift register, so 3 clock is required. Okay. Similarly, number third for serial in parallel out operation. For serial in parallel out, n clock is required. And number 4, serial in serial out. So this is this plus this. So you can write, sir, n minus 1 plus n. Okay, this number of clock you can write is equal to 2n minus 1 clock is required. 2n minus 1 clock is required. 2n minus 1 clock is required. This is for standard design. We have one more design. We are here 1 clock is required, but always you have to write this answer. But from resistor, very easy question in GATE exam generally they ask. Okay, so just I am asking one question. So first question just I am going to take from the resistor. So one question I am going to take from the resistor. Examiner will provide you this kind of block. Okay, this is 1, 2, 3, 4. Suppose this is a 4-bit shift resistor. So how you should know, sir, this is shift left or shift right? This is the first important point. And sir, they have mentioned output or input. This is output. So if we have 4-bit shift register, suppose Q3, Q2, Q1, and Q0. Okay, this is a 4-bit output. This we have 4 number of D flip flop. So output of a D3 third number flip flop is Q3, Q2, Q1, Q0. So we have 4 number of flip flops. So this is first flip flop, second flip flop, third flip flop, and fourth flip flop. So we can write this is Q3, Q2, and Q1 and Q0. Okay, this is MSB. This is right, but this is examiner choice. Okay, what they want to write, they can also use Q3, Q2, Q1, Q0, but no worry. What they are providing, just so we can write here. Now the important thing is here, sir, this is shift left resistor or shift right. This is important. If I will write here one arrow, so this is the shift. This is a shift. This is from left to right. So this is shift right resistor. So this is a shift right resistor. If I will apply, this is one arrow will indicate, and I can write like this clock. Okay, now suppose if I will represent in this way. Suppose if I will represent in this way, this is Q3, Q2, Q1 and Q0, and in this way. And suppose this arrow will practically represent this is shift left or shift right. This is a shift this is a shift left operation. This is a shift left register. Clear this point? So one question I am going to consider. Suppose examiner have provided for value. Suppose 1, 0 and 0 and 1. Suppose like this, and suppose this is a shift right register and this is your clock. And now they are asking after how much clock the same data will be repeated. So easily you can write after 4 clock. So after initially this is 1001. This is you can write at initial. After first clock this will be shift here. So what you will get, and suppose if I will connect in this way, suppose like this, then after first clock you will get, sir, this is 1100. After second clock this is this 0 will shift here, this is 110. Then after third clock this 0 will shift here, this is 011, and this 0 you will get here. And after fourth clock this is 1001. So after 4 clock you will receive the data. This circuit is called ring. This is a ring counter. This circuit is a ring counter. Okay, this circuit is a ring counter. Okay, but examiner will not ask you this basic question. So second question just I am going to consider. They will connect here XOR gate, XNOR gate, or anything like this. So second problem just I am going to take here. Second problem. Okay, so anyone can handle question from here. Only some basic things should be very clear. This is shift left or shift right. Okay, and now suppose this is 1001. Okay, now again suppose this is a clock. This is a shift left to right operation. This is shift this is moving from left to right, means shift right register. Suppose this and this is connected with one XOR gate. Suppose this two input is connected with one XOR gate and this output is connected to here. Okay, then initial, you can write initial. This is 1001. Then examiner can ask you after 6 clock what will be the data. So you can write, sir, after first clock. One thing you should remember in the shift register, this is very important thing. This data will be moved, this data will be moved, this data will be moved. The important thing is 3 data cannot be modified. 3 data will be always moved. Always 3 data will be moved. Only this data can be modified in shift right register, and this last data can be modified in shift left register. This is very important thing, because inside of this circuit you cannot modify. Inside of circuit only shifting operation can be performed. So in all the cases you will get this shifting operation here. Only this first data can be modified. So here this is directly connected from here. So this data will come to here, this data will come to here, this data will come to here, and this data will come to here. Similarly here, initially 1001. So after first clock, this data will shift to here, this data will shift to here, this data will shift to here. Now you can see what is the first data, XOR of this. So 01 XOR is 1. So you will get here 1. Then after second clock, this data will shift here, this is 1 and this is 0. Now 00 XOR is 0. Then after third clock, this data will shift here, this is 1, this is 1. 10 XOR is 1. Then after fourth clock, this data will shift here, this is shift here, this is shift here, 11 XOR 0, like this. Then after fifth clock, this 010, this is 0, this is 1, this is 0, and first data will be 01 XOR 1. After 6 clock, this is 101 and 10 is 1. So 1101. So after 6 clock, anything examiner can ask you. So this is the easiest question in digital electronics. So shift register easily you can handle. Anything they can provide, either shift left or shift right, like this. Clear this thing? Now suppose for example, now here one more thing I want to ask you. So if examiner will ask you how many maximum number of states can be possible. So maximum number of states can be possible. Maximum number of states in a ring counter. In a ring counter. So maximum number of state in ring counter is always equal to n. Okay, this is maximum. If all the input is 0, 0, 0, 0, so you will get only one state. Just I am asking the maximum number of state. If n bit, n state. Okay. Now here sometime examiner can ask you maximum number of states in a Johnson counter. In Johnson counter. So in Johnson counter, what is the maximum number of state? Remember, this is 20. This is a maximum. This is not always fixed. It will depend on the input. So like this, if here all the input is 0, 0, 0, 0, only you will get one state. Similarly, in Johnson counter, every time you will not get two n state. Okay. So this is a maximum number of state. What is Johnson counter? If we will put here one NOT gate, so this will become a Johnson counter. So this two thing you should remember. Okay, only this thing you should know about the shift register. Okay, now I am going to start the counter. Now I am going to start counter. Clear? So now I am going to start counter circuit. Okay, so ready for the counter. Okay, so only shift register if you will see, so you can feel, yeah, definitely we will get 1 or 2 marks. Okay, now the next one is a counter circuit. Next one is counter circuit. Okay, so in counter, generally we design two kind of counter, asynchronous counter and synchronous counter. So first I am going with asynchronous counter. So our next topic is counters. Our next topic is counter. First I am going with the asynchronous counter. Asynchronous counter. So in asynchronous counter, only one flip-flop clock will be provided to one flip-flop. Okay, suppose here in general asynchronous counter, generally two kind of counter we will use, generally either up counter or down counter. So here every question you will get from either up counter or down counter, and by using this and by using up counter and down counter we will design modern counter. So here the important thing is all the counters you will get in generally standard up or standard down, and by using this we can implement modern counter. This is a first important point, is a asynchronous counter. This is a first important point in asynchronous counter. So first sir, how we can say the counter is up counter or down counter? So you should know. So just I am going to consider 3-bit counter. So first I am going to consider 3-bit counter 1, 2 and 3. 1, 2 and 3. Okay, so here two possibility can be possible. Either this is connected with a positive edge triggered clock or negative edge triggered clock. Just I am going to consider first positive edge triggered clock. All the flip flop will be T flip flop, T flip flop, T flip flop. This output will be Q and Q bar. This will be Q and Q bar. This will be Q and Q bar. Now first important thing, where you are applying the clock, this will be LSB flip flop. This is very important thing. And where you are this is the last one, this is MSB flip flop. This is very important thing. So now suppose and all the value is here, T is equal to 1, T is equal to 1 and T is equal to 1. This is the first important point for the asynchronous counter. Okay, now suppose if you want to implement up counter, this is positive edge clock. So here if again you are using positive edge and positive edge, so if you are connecting from this up, so this will be up counter. So this will be up counter. So how you can remember? So for positive edge triggered clock, if this is up step is representing, so this is a up counter. So directly you remember this is a 3-bit up counter, and similarly 2-bit or 4-bit same stages you have to connect. Now sir, is there any alternate representation of up counter? Yes, if this is negative edge triggered, then you have to play with bubble. How you can implement? So what is a sir second representation of up counter? So this up counter, again this is T, this is T, this is T, this T will be 1, this T will be 1, this T will be 1, this is Q, this is Q, this is Q bar, this is Q bar, and this is Q bar, and this is Q bar. Now here if you are applying this is negative edge triggered clock. Now here I want to write the name. This is the LSB flip flop T0 Q0 Q0. This is T1 Q1 Q1 bar. This is T2 Q2 and Q2 bar. Clear the thing? So very important thing, where you are applying the clock, that flip flop will be LSB. You can also represent in this way. Okay, you can also represent in this way. So sometime in GATE exam, examiner have represented in this way. Clear? Sometime examiner can also represent this flip flop in this way, this flip flop in this way, and this flip flop in this way. So first you have to concentrate where you are applying the clock. First you have to write this flip flop output is a LSB output. Okay, now so sir, now if I want to, here we have provided clock, so this is 0, this will be 1, and sir this will be 2. Can I write? Now if you want here a negative edge trigger, so how you can implement? So in this diagram you can see, if I will put here 2 bubble, then everything will be same. Yes, if I will put here, everything will be same. If I will put here 1 bubble, so nothing will be happened. So one thing you remember, LSB flip flop is either negative edge triggered or positive edge triggered. it will not be affect to the output, only starting point will be different. So one important thing, LSB flip-flop can be either negative edge triggered or can be positive edge triggered. It will not be affect to this flip-flop. Okay, so LSB flip-flop can be anything. So first important point, here this can be negative edge triggered, this can be positive edge triggered. This will not be affect to the up counter or down counter. If this is up, it will be up. If this is down, it will be down. If you will change this, clear this point. Now if if you are going to put here two bubbles, so this will be a negative edge trigger. Okay, this will be a negative edge trigger. Now this bubble Q1 bar, so can I connect this one from here? Can I connect this one from here? Both the circuit is same, both the circuit is same. So this is the second representation. If you are going to use your negative edge trigger, you can connect in this way. So this is a 3-bit up counter. So again this is a 3-bit up counter. So we have two representation. So we have two representation of up counter. We have two representation of up counter. This one first and this one second. This one second. Clear? So directly you should remember. So if this is a positive edge trigger and if you are going to up, this is up counter. But for negative edge trigger, if you are going to down, that is a up counter. Like this you can remember. Okay, like this you can remember. Similarly, sir, what will be the down counter? So in same diagram, just I want to explain you. Sir, what will be the down counter? So for down counter, opposite of this. So can I write directly? Sir, for down counter, if this is connected from here and if this is connected from here, sir, this is 3-bit down counter. This is 3-bit down counter, and similarly again this will be connected from here and this will be connected from here. So this will be down counter. Now this can be positive edge or negative edge. It will not be affect to counter performance. Clear this thing? So this is nothing but 3-bit down counter. How you can remember? For positive edge trigger, if this is down, this is down counter. For negative edge trigger, if this is up, it means for negative edge trigger, this is down counter. You can also do here same thing. Sir, if this is negative edge trigger, so this bubble you can remove. This is Q bar, so you can connect in this way. You can connect in this way, and if this you can connect in this way, this bubble you can remove. And already I tell you here, either you can use negative edge trigger or positive edge trigger, your result will be same. So this is nothing but a down counter. So directly first directly you can say 100% question till now, 100 not 99%, 100% question in GATE exam till now ask from either standard up or standard down, and by using standard up and standard down they have implemented mod encounter. But in very rare situation, this kind of questions can be possible. Sir, this is going to be down and this is going to be up. Suppose this, but till now nobody has asked question in this way. So you can also assume either question will come from standard up or standard down. So now you cannot say, sir, this is up or down. So in this situation, okay, in this situation you have to solve this counters. Okay, you have to solve this counter. But don't worry, examiner will not ask you. Okay, now come to the point. Now if you want to implement mod encounter, and one more important thing, sometime examiner are interested in frequency. So suppose for example, if here clock frequency, if here this is the clock frequency is f clock, then sir, what will be the clock frequency here? What will be here output clock frequency? So here output clock frequency, can I say f output? What is the f output here? So always this will be nothing but input clock frequency f clock divided by number of output states. Clear this point? You can also say if this is a 3-bit complete up or complete down, you can say this is a mod 8 counter. So this you can also say total state is 8, so you can say mod 8 counter. And you can also write, sir, this is mod n. So n value you can put. So here you can also write this is f clock by n. So what is this last state? Remember MSB state. What is the clock frequency? F clock by, this is n, and here this is nothing but f clock by 8. This is f clock by 8 because for up counter or down counter, total number of output state will be 8 states. Clear this thing? This thing should be remembered to you. Now come to the next point. If I will ask you, sir, what is the frequency here and what is the frequency here? If this is standard up or this is standard down, so here frequency will be, you can write, sir, here f at q1 is nothing but f clock by 4. You can also say, sir, this is nothing but 2-bit up counter or 2-bit down counter. So here total number of states is 2 for 2-bit. So total number of states is 4. So directly you can write here clock frequency f clock by 4. And sir, what is here clock frequency? So here f at q0, this is nothing but f clock by 2. So here this frequency will be divided by 2, divided by 4 and divided by 8. Same here for up or down counter, divide by 2, divide by 4 and divide by 8. Directly you can write. But remember my word, this is valid for complete counter. For complete counter. So this answer is valid for complete counter, means standard up or standard down, which will provide you all the states. So this frequency will be divided by 2 here, this frequency will be divided by 2 here, and this frequency will be divided by 2 here. Sorry, this frequency will be, here you will get half frequency, here you will get, sorry, here you will get double frequency, here you will get double frequency, and here you will get double frequency. Okay, here this frequency will be half, here again half, here again half. Clear this point? Now how we can implement mod n counter? How we can implement mod n counter? So now you can see. Okay, this thing should be remembered to you. This thing should be remembered to you. So now how we can implement mod n counter, and this is mod n asynchronous counter. Mod n asynchronous counter. So mod n asynchronous counter, suppose I want to design mod 5 up counter. So what is a mod 5 up counter? So mod 5 up counter will be nothing but 3 number of counter will be required. This is 1, 2 and this is number 3. 3 number of flip-flop will be required if you are applying clock here. Okay, it can be positive edge trigger or negative edge trigger. Just I am going to use negative edge trigger. This is clock. So you can write this is T0, this is Q0, this is Q0 bar, this is T1, this is Q1, this is Q1 bar, this is T2, this is Q2, this is Q2 bar. All the T value will be 1, 1 and 1. All the T value will be 1 and 1. You want here up counter. So first you can draw here standard up. So standard up counter for negative edge trigger, this is standard up and this is standard up. So this is a 3-bit standard up counter, but you want to implement mod 5 counter. So when you are receiving 5, so for 5 means if I will write, sir, this is Q2, Q1, Q0, and when Q2, Q1, Q0, 101, but you don't want 101. So when you are receiving 101, you have to clear all the flip-flop. So here either this will be active low clear or active high clear. So just I am going to use here, this is clear, this is clear, this is clear, this is the active low clear. So what we can use here? We can use here one NAND gate. We can use here one NAND gate, this NAND gate. And this NAND gate, if this NAND gate output is 0, or you can say if this AND gate output is 1, then all the flip-flop will be clear. When you want to clear, when your output is Q2, Q1, Q0 is this important thing, and when this is 101. So you can connect with like this, when this is Q2 is 1 and when this Q0 is 1. When this Q0 is 1. You don't use this input because if this and this are 1, this is up counter. So initial state, just I am writing, sir, this is Q2, Q1, Q0. Initially 0, 0, 0. After first clock, this is 0, 0, 1. After second clock, this is 0, 1, 0. After third clock, this is 0, 1, 1. After fourth clock, this is 1, 0, 0. After fifth clock, this is 1, 0, 1. But when you will receive here, this Q2 and Q1 is Q0 is 1, 1. Now this will activate. I am assuming delay of this is 0. If this will activate, all the flip-flop will be cleared. So for very small time, this you will get an output, but immediately all the flip-flop will be cleared and all the flip-flop you will get immediately 0, 0, 0. So in same clock, so in fifth clock, first you will receive 101 and immediately all the flip-flop will be cleared and you will get output 0, 0, 0. So number of output state is 1, 2, 3, 4, 5. So total number of output is 5. This is nothing but mod 5 up counter. Similarly, mod 6, mod 4, anything you can implement from here. Okay, so like this. So one important thing you remember, generally up counter is designed by the clear and down counter is designed by the preset. So now one more example I am going to use here. Okay, one more example from the mod n counter. So now I am considering, suppose mod 5 down counter. Suppose if I want to implement mod 5 down counter, then how you can implement? Okay, generally students are stuck in the down counter. Generally students are stuck in the down counter. So if I want to implement mod 5 down counter, okay, mod 5 down counter. So if you want to implement mod 5 down counter, so how we can implement? First you should know what is the output state. So here output state is, first state is 7, then 6, then 5, then 4, then 3, then 3. Okay, total 5 state, then again 7. This is very important thing. So one thing you remember, down counter start from higher state, means 1 1 1, and up counter will start from 0 0 0. This is very important thing. So here what I want to write, this is q2, q1, q0. So initially this is 1 1 1. After first clock this should be 1 1 0. After the second clock this should be 5. After third clock this should be 4. After fourth clock this should be 3, and in the fifth clock if you will get 0 1 0, immediately this should be changed to 1 1 1. Are you getting this point? So this is very important point. Down counter always, okay, I can say 99.99% time, okay, down counter. If you will get confusion in gate exam, always you have to apply this. Don't assume here for down counter it will start from 0 0 0. Okay, so always you have to initialize down counter by 1 1 1. So how we can implement the circuit? Okay, so can I implement in the same diagram? Okay, in a different diagram I am going to implement. So now here just this 3 number of flip-flop we can consider. This 3 number of flip-flop we can consider. Okay, now here I am applying clock. Now I am considering positive edge. Okay, positive edge clock. So this is T0, this is 1, this is Q0, and this is Q0 bar. This is T1, this is Q1, this is Q1 bar, and now this is 1, and now this is T2, this is Q2, and this is Q2 bar, and this value is again 1. So if you want to design down counter, so for positive edge trigger this is down counter and this is down counter, okay, and for negative edge trigger that was up and that was up. Now so here this is a down counter. Now here when you are receiving 0 1 0, means q2 q1 q0 is 0 1 0, in that state you have to not clear, you have to preset. Here you don't have to clear, this is a preset, this is a preset, and here what you have to do, this is a clear, this is a clear. So this is the important thing. So generally preset will be represented here. So here this is preset, this is preset, this is preset. So what you have to do, if this will activate, so your output will be preset, means 1 1 1. So we can write this is preset, this is preset, this is preset. This is your choice, you will write p bar or p, anything you can write. So this bubble is representing, this is a active low category of preset. So if this q2 is 0, this q1 is 0, and this q0 is, sorry, this is 0, this is 1, this is 0, then this will activate. Then how you can, here NAND gate I have used, then which gate you have to use here, so you can see here till now this is 1 1 1 1, but this is going to be 0 first time. So for later states this q2 is 0. So here the thing is different. In up counter first you will start from 0 0 0, then 1, okay. So but here first you are going to start from 1 1 1, then you are reaching to 0. So the thing is going to be different. So first time here this q2 is 0 and this 0 is second time, okay. Now here this q1 is 1 and now here this q0 is 0. Then how we can design? So all the 3 value will be used here, or you can see if this q2 is 0, or can I say q0 is 0, both are 0 0, only in this situation. So can I assume only this two? So if q2 is 0 and q0 is 0, then you have to preset this. So any gate you can use. Suppose for example if you are going to use here AND gate, suppose for example if you want to use here, sorry, NAND gate, suppose if you want to use here NAND gate, then this q2 is 0 and this q0 is 0. So if both are 0 0, so can I put here 2 bubble, and one is connected with your this q0 and one is connected with your here q2. This is the important thing. So if q2 is 1, So if Q2 is 1, sorry, if Q2 is 0 and if Q0 is 0 first time, so this 0 will become 1, this 0 will become 1 and this 1.11 and here you will get 0 and all the flip-flop will be preset. This is the important thing. Now, so here bubble NAND gate will be required and here only NAND gate is required. Here bubble NAND and here NAND. Now you can also replace this gate by, this gate is also replaced by, this is nothing but bubble NAND and bubble NAND is nothing but OR gate. So this is nothing but OR gate. So this is nothing but OR gate. So this is your choice. Either you can represent here OR gate. So sometime this is also replaced by here. This is also replaced by here. This is also replaced by here OR gate. Also replaced by here OR gate. So what we can say here, what you want is 0. So till this situation you can see this value or this value, any one or one, any one or one. Only in this situation both are 0 0. When this is 0 and when this is 0, 0 plus 0 is 0 and all the flip flop will be preset. So this, there are two difference in mod and up counter and mod and down counter. Are you getting this point? So here you have to use here NAND gate and here you have to use bubble NAND gate, or bubble NAND gate is nothing but OR gate. So here this is nothing but OR gate. Here this is nothing but OR gate. So here you are targeting to 0. For down counter you are targeting to 0 and for up counter you are targeting to 1. You are targeting to 1. Are you getting this point? So for up counter you are targeting to 1 and for down counter you are targeting to 0. Clear this thing? So this is a asynchronous up counter, asynchronous down counter and asynchronous mod n counter. Now the next question, if I will ask you here in the first question, sir, what is the frequency here? Sir, what is frequency here? Sir, what is frequency here? And sir, what is frequency here? In this place, what is frequency? So in last state frequency, easily you can write f clock. If here frequency is f clock, so last state frequency is f clock by number of states. Number of states is here 5. So here frequency is f clock by 5. Sir, but what is the frequency here? What is the frequency here? What is the frequency here? You cannot write here f clock by 2.5. You cannot write, because f clock, you cannot write, sir, this double frequency. So 2 by 5 f clock, no. Now this cannot be, you cannot write here. So in gate exam, within 1 minute or 2 minutes, sir, how we can find out this frequency? So just I am going to tell you in gate exam how you can handle this question. So you can write first at least 2 times. 2 times you have to write. Okay. So 2 times you have to write this value. So 2 times you have to write this value. So you know this is standard up, this is standard up counter. Just you have to write, sir, this is Q2, this is Q1, this is Q0. Initially this was 0 0 0, then 0 0 1, then 0 1 0, then 0 1 1, then 1 0 0. Now 1 0 1 you will not get, so 1 0 1 will be replaced by 0 0 0, then 0 0 1, then 0 1 0, then 0 1 1, then 1 0 0. Okay, 2 times you have to write. Now you can check which part is going to be repeat. So here, so this is 0 1 0 1 0 0. No. So if you are considering here, so this is the time period. This is the time period. But here you are getting 0. So no, this cannot be time period. So here time period will be 0. Here time period will be 0 1 0 1 0. Then 0 1 0. So this will be the one part. And this will be the second part. So here time period will be 5t. So here time period will be 5t. So if this time period is 5t, so frequency will be, this Q0 frequency will be again f clock by 5. So here this frequency will be f clock by 5. So sometime if this is standard up or standard down, so here this frequency was f clock by 2. But if this is a mod encounter and this is a mod 5, then you are getting f clock by 5. Sir, what will be the second frequency? So 0 0 1 1 0, this block is going to be repeat. 0 0 1 1 0. It means again this time period will be 5t. So again this frequency will be f clock by 5. And last frequency will be f clock by 5. So here the frequency will be f clock by 5, f clock by 5, f clock by 5. Like this you can write your answer in gate exam. So examiner can target frequency in between any flip flop. Clear this point? Clear this point? Okay. Yeah. Thank you, Abhijit Ghosh. This is very important thing. This is very important thing. Okay. Examiner according to me, now examiner will target this point. Now suppose for example, I hope this thing is clear to you. So if this is a mod 8 up counter, so your frequency will be here f clock by 8, but here f clock by 4, here f clock by 2 for complete counter. But for mod 5 counter, here this is f clock by 5, but here you directly you cannot say, you have to find in this way. Suppose if this is a mod 6 up counter, suppose for example, sir, what will be the frequency for mod 6 up counter? So if we want to implement here mod 6, so this thing will be here changed, but here frequency will be f clock by 6. This we don't know, and this we don't know. So what will be for mod 6 counter? So for mod 6 counter, how you can find out? So in gate exam easily you can handle. How you can handle? Just you have to write q2, q1, q0, and 2 times you have to write. Just complete the sequence 2 times you have to write 2 times. Okay, now you can start from 0 0 0. Sir, this is 0 0 1, this is 0 1 0, this is 0 1 1. Sir, this is 1 0 0 1 0 1. So this is mod 6. Then again you will get 0 0 0. Sir, again 0 0 0. This is 0 0 1, 0 1 0, 0 1 1, 1 0 1, and 1 1 0. Can you write like this? Now you can see here. Sir, 0 1 0 1 0 1 0 1 0 1. You are getting. Okay, here something mistake. Now this is 3. Here this is 4. And here this is 5. Okay, now so you can see here, sir, 0 1 0 1 0 1 0 1 0 1. So this is the time period. So time period will be 2 times, then frequency will be just half. This is very important thing. Then sir, what will be the frequency of this first state q0? So only this is divided by 2. So what I want to tell you, if this is a even mod 6, mod 4, mod 2, if this is a even, so last state always you will get 0 1 0 1 0 1 0 1 0 1 0. But if this is odd, so after completion of one cycle 0 1 0 1 0 1, last state will be repeated. So if this n is even, so you will get 0 1 0 1 0 1. So first frequency will be always f clock by 2. But if this is a odd, so you will get here 0 1 0 1 0, then again this will repeat. So you will get f clock by n. Clear this point? Now for the second. For the second, sir, 0 0 1 1 0 0 0, 0 0 1 1 0 0. Here 0 0 1 1. So only this block is going to be repeated. 0 0 1 1. You cannot consider as 0 0 1 1. Here 0 0, again 2 0. So same block is going to repeat here. 0 0 1 1 0 0, then 0 0 1 1 0 0. So for the second, your frequency will be f clock by 6. And last, your frequency will be f clock by 6. So this is the magic here. So examiner can ask you frequency in between any flip-flop. Now come to this question. This is a down counter. So for down counter, if this is a mod 5 down counter, so if this is a mod 5 down counter, then what will be the frequency? So now you can say, sir, last this is a f clock by 5. This will be f clock by 5. Sir, what will be this and what will be this? This is a odd. But you can check, sir, this is 1 1 1, then 1 1 0, then 1 0 1, then 1 0 0, then 0 1 1, then again 1 1 1, then 1 1 0, then 1 0 1, then 1 0 0, then 0 1 1. You can check here. Last state, this is q0, this is q1, and this is q2. So 1 0 1 0, but here, so only this 5 is repeating. So q0 frequency directly you can write, sir, here f clock by 5. Now, sir, second 1 1 0 0 1. So this block is going to be repeat 1 1 0 0 1, and again 1 1 0 0. It means second block frequency will be always f clock by n, and last will be f clock by n. Here n is 5. Now from here, for up counter and down counter, in between frequency or last frequency, always it will be same. It will not be changed to up counter and down counter. One thing you remember, always last state frequency will be f clock by n. Okay. First state frequency, two answer can be possible. If n is even, then f clock by 2. If n is odd, f clock by n. And in between this second state frequency will be always f clock by n. But according to me, you don't remember like this. In gate exam, this last frequency directly you remember f clock by n, and in between frequency just you can write like this, and just you can find out the what is the frequency, because sometime examiner can provide you random counter, neither standard up or not standard down. In that situation, these things will be helpful to you. I hope this thing is clear. So this was asynchronous counter. In asynchronous counter, remember what is standard up, what is standard down. Okay, by positive S trigger or by negative S trigger, how we can implement mod and counter. Okay, for up counter and for down counter. And now the last point, what will be the frequency at every state? Only this number of question can be asked by the examiner. Now one last question, sir, what can be the propagation delay in asynchronous counter? Sir, what can be the propagation delay? Sir, what can be the propagation delay? Sir, what can be the propagation delay? What can be the propagation delay in asynchronous counter? What can be the propagation delay in asynchronous counter? Okay, so now again I am going to take the last part from the asynchronous counter. The last part from the asynchronous counter. Okay, now, sir, what is the propagation delay in asynchronous counter, and what is the problem with asynchronous counter, and what is the problem with asynchronous counter? So just I am going to again here consider three number of flip flop. Just I am going to consider three number of flip flop. Suppose this is T0, this is Q0, this is Q0 bar. Now second, this is T1, this is Q1, this is Q1 bar. This is T2, this is Q2, and this is Q2 bar. Suppose I am considering, and this is your clock. This I am considering this is a positive S triggered clock, and this is positive S trigger. This is positive S trigger. Okay, it can be up counter or down counter. What is this? This is the up counter. And one more important thing, all the T value is here 1, 1, and 1. Okay, now, and this is first output, this is second output, and this is third output. Okay, now, so if I will ask you, sir, what can be the maximum clock frequency we can provide here? It will depend. Suppose if you want to use this Q2 anywhere, suppose if you want to use this Q2 anywhere, suppose for example, if you want to use this Q2 anywhere, so if I will ask you, sir, what is the delay here? So delay at Q2, so if I will write, sir, T at Q2 means delay, propagation delay at Q2, don't write T, T can be time period. It is better we can write here propagation delay. So what propagation delay? Propagation delay at Q2, what you will get? So when you are applying the clock, okay, when you are applying the clock, when you will get this output, then this will be triggered. When you will get this, then this will be triggered. So propagation delay of this, okay, input is available, all the input is available, but when this will be triggered after operation of this. So when you will receive propagation delay of this flip flop, propagation delay of this, and propagation delay of this. So propagation delay, when you will get this Q2, when you will get first change in the Q2, this is my question. So first change in the Q2, so first change in the Q2, first change in the Q2. So what is the first change in the Q2 after propagation delay of this, propagation delay of this, and propagation delay of this? So can I write 3 into propagation delay of each flip flop? Propagation delay of each flip flop. Are you getting this point? Suppose if I want to represent this complete block, this complete circuit in one block, and if this is your clock and this is your output, and output is your Q2, this is the your output, this is your output. You can write here this is Q2, and you can write, sir, this is your output. So for this complete circuit, if I am considering this is one block, so when you will receive the first output, minimum, what is the minimum time required, okay, to receive first output? The time is, so here this is nothing but 3 into propagation delay of each flip flop. So can I write, we don't know if this is 3, so can I write this is n into propagation delay of flip flop? Okay, now if you want to use this again anywhere, so in that situation we can call here, what can be the maximum clock frequency? So this app clock, at least, so if I will say, sir, this is T clock, so this T clock should be at least more than this. So can I say, so if you are applying here clock, if you are applying here, suppose for example clock, so this is first clock and this is second clock. So when you applied the first clock, first output you will receive at any time, first output you will receive, suppose I am receiving Q1, and after some time after I am receiving Q2, this is you are receiving at first clock, and this you will receive after second clock. So suppose for example, if I have provided first clock and after some time you will receive this output. Suppose you have not received the output, suppose, and again you have applied the second clock, then that your output will be skip, you will not receive that output. So that's why what we can say, what is a propagation delay of this complete block? Propagation delay of this complete block should be less than this time period. So this clock time period, or you can say this clock time period should be greater than propagation delay of this complete block. This is very important point. So what we can say, this T clock should be greater than or is equal to propagation delay. This propagation delay of this complete circuit. So propagation delay of circuit, or you can say propagation delay of asynchronous counter. So we are targeting here asynchronous counter. So if this circuit is asynchronous counter, so we can write here propagation delay of asynchronous counter. Propagation delay of asynchronous counter. Can we write in this way? Yes. So from here you can write, sir, f clock should be less than or equal to 1 upon propagation delay of counter. Which counter? Asynchronous. This is asynchronous. So maximum f clock. What can be the maximum f clock we can provide for the asynchronous counter? This is a most important question. So what can be the maximum f clock we can provide? Okay, you can first find out total delay. First you can find out total delay, 1 upon total delay. So how you can remember what will be the, sir, f clock maximum? So you can write this in nothing but 1 by total delay. 1 by total delay. And what is total delay? Is nothing but total delay is number of flip-flop into propagation delay of one flip-flop. So here f clock maximum, you remember 1 upon, this is n is the number of flip-flop into propagation delay of each flip-flop. Each flip-flop, or propagation delay of one flip-flop. Propagation delay of one flip. So here you can say f clock max, f clock maximum or f clock is inversely proportional to number of flip-flop. So when you will increase the number of flip-flop, your circuit will be slow. That's why in real life we do not use asynchronous counter. So this is only for the study purpose. In real life we don't use asynchronous counter. The reason is, if I will use 4-bit, 5-bit, 6-bit, so definitely here f clock maximum will be less, so circuit speed will be less. You can use for 2-bit, 3-bit, 4-bit, but if you want to use 8-bit, 10-bit, you don't go with the asynchronous counter. So what is a disadvantage, or how you can calculate frequency of asynchronous counter? What can be the maximum clock frequency we can apply it here? Okay, so you cannot say, sir, if I will apply less than this clock frequency, this will operate. Yes, this will operate, but you cannot use this output again in the same circuit. Suppose if you want this output in the same circuit, then you cannot use. That's why always we maintain this thing in asynchronous counter. So now from my side asynchronous counter is completed. Now I am moving towards synchronous counter. Clear? Now, sir, by log pulse solve time, please. Sir, for non-standard counter modern, I am not getting your doubt. Sir, by clock pulse solve time, please. Again please write. I am not getting. Sir, for non-standard counter. Okay, for non-standard counter, just I want to tell you. Suppose this is Q2, Q1 and Q0. Okay, suppose initial suppose this is 0, 1, 0. Suppose after clock you are getting suppose here 1, 0, 0. After clock 2, suppose you are getting suppose, sir, this is 0, 1, 1. Now after clock third, suppose you are getting 1, 1, 1. Suppose after clock 4 you are getting 0, 0, 0. Now again this thing is going to be repeated. After clock 5, this 0, 1, 0 is repeated. 0, 1, 0 is repeated. Then after clock 6, again this value 1, 0, 0. Then 0, 1, 1. Then 1, 1, 1. Okay, and then 0, 0, 0. Okay, so here anything examiner can provide you, but already I tell you in asynchronous counter examiner are not interested. So this will help you in synchronous counter. So the same concept you have to apply if you want to calculate frequency at any state. either this is was synchronous or asynchronous, same concept you have to apply. So you can write this same way for synchronous, and you can also write the same way for asynchronous. So if you know the output state of either synchronous counter or asynchronous counter, so if you want to find out, so what is frequency of Q0, what is frequency of Q1, what is frequency of Q2, so how you can write, so you can see, sir, this is 0 0 1 1, so you can check which block is going to be repeat. So here, sir, 0 0 1 1 0, then 0 0, this block is going to be repeated, 0 0 1 1 0, and again this 0 0 1 1 0. It means this is 1 clock time, 2 clock time, 3 clock time, 4 clock. So this time period is 5t. So if time period is 5t, means frequency will be divided by 5. So this Q0 frequency will be f clock by 5. Okay. Now in second situation, you can see, sir, 1 0 1 1. So 1 0 1 1 0 1, but here 0 1 0, so not repeating. Sir, 1 0 not repeating. Sir, 1 0 1 1, here not repeating. Sir, 1 0 1 1 0 1 0 1 1 0, again this 1 0 1 1 0. So again this frequency will be f clock by 5, f clock by 5. Now again, sir, this is 0 1 0 1 0, here this is not repeating. Sir, this is, but here if I will provide 0 1 0 1 0 1 0 1 0 1, then this clock frequency can be half. So from this table, from this series, easily you can find out. So 0 1 0 is repeating, no. So 0 1 0 1 0 0, no repeating. So 0 1 0 1 0, so 0 1 0 1 0 0 1 0 1 0, again here this is 5, this block is repeating. Again this frequency will be f clock by 5. Clear this thing? So if you know the output state of any counter, okay, so in synchronous we will study in this way. So if you know the output states of any counter, just you have to write 2 times, and you can check here which block is repeating. So you should find out the time period of that. So frequency will be divided by that. So this time period is 5t, this is 5t, this is 5t. So frequency will be divided by 5, divided by 5, divided by 5. Easily you can handle. Okay, and this is most important topic for GATE exam. I hope this thing is clear to all of you. And this f clock here for asynchronous, maximum f clock, and this is a disadvantage of asynchronous counter, and this problem will be removed in, but this problem will be removed in synchronous counter. But the important thing, synchronous counter, you have to concentrate on setup time violation and hold time violation. Here we don't study setup time and hold time. Clear my point? So in asynchronous counter, setup time, hold time violation is not required. Okay, so if you will remove this problem, and this problem will be removed in synchronous counter, but synchronous counter we have one problem, you have to maintain, okay, or you have to remove setup time violation and hold time violation. Clear this point? That's why in real life we will use this synchronous counter, and in synchronous counter you should be expert in setup time violation and hold time violation. Okay, we will study, don't worry. Today I will discuss setup time and hold time. Okay, don't worry about that. Clear this point? Okay, so asynchronous counter is completed from my side. Now I am moving towards synchronous counter. Okay, now tell me if anybody have any doubt. If anybody have any doubt, please tell me. If anybody have any doubt, please tell me. Okay, so asynchronous counter is clear. Definitely examiner, okay, by using pulse diagram. Okay, as you solve in, okay, by using pulse diagram. Okay, if you will draw the pulse, it will take more time. So in GATE exam, you can solve in this way. You can write the table and by using that. So if you are getting, suppose here 1 0 0 1 0, so you can draw, sir, this is 1, this is 0, then sir, this is 0, sir, this is 1, and this is 0. So this total time period is 5t clock, and same block will be repeated again. Sir, this is 1, this is 0, then 0, this is 1, and then 0. So again this same block is going to be repeated. So what we can say, sir, this block is called a you can say this is a one time period, and this will be repeating. So this is a periodic waveform. So what will be this time period? If you are saying this is t is equal to 5 into t clock. So what will be the frequency of this? this will be divided by f clock by 5. F clock by 5. Clear saying you can write 1 upon 5 into t clock. 1 by t clock is f clock by 5. If time period will be 5 times more, frequency will be 5 times less. Clear? So in gate exam, you don't have to draw clock pulse for asynchronous. Directly you should write the table, and by using table you can write the answer. Okay? But if you don't know what is the output, if you don't know, sir, what is the output, then waveform you have to draw in that situation. Okay, now come to the point. Now I am moving towards synchronous counter. Okay, so now I am moving towards synchronous counter. Okay, so now synchronous counter. Okay, synchronous counter and asynchronous counter is totally different. Synchronous counter and asynchronous counter is totally different thing. This is totally different topic. So synchronous counter, generally we will not use standard up or standard down here. Okay, so and here in synchronous counter, one more important thing I want to tell you. In asynchronous counter, in asynchronous counter, you can also represent in this way. Asynchronous counter, sir, this is clock. Okay, sir, here this is Q2, Q1 and Q0. Okay, this is the 3 output. If I am going to use here clear, you can write clear bar or clear anything. Okay, if this is a clear, so definitely this here it will be NAND gate. Suppose if I am going to connect with Q0 and Q2, so how much this is up counter, you can say this is a up counter. If examiner will not provide you this is a up counter, so if this is connected with clear, this will be up counter. Okay, so if this is connected with clear, so you can say, sir, this is a up counter, if this is a up counter, so when this is going to be clear, when Q2 and Q0 is 1 1, it means first time this will be 1 1 at 5 1 0 1. So total states you will get, you can write, sir, this is Q2, Q1, Q0. If this is connected with clear, means this will start from 0 0 0. After first clock 0 0 1, this up counter. After second clock 0 1 0. After third clock 0 1 1. After fourth clock 1 0 0. Now after fifth clock, this will become 1 0 1. And if this is 1 1, this will be clear. So here you will get 0 0 0. So what we can say, sir, this is asynchronous clear or this is synchronous clear. So one thing you should remember, if asynchronous counter and asynchronous which counter? Up counter. So in asynchronous up counter, we use asynchronous clear. So this kind of clear is called asynchronous clear. Means this clear function is not synchronized with clock. So when you will receive here 1 and 1, this will be clear. Now I want to tell you one truth table here for preset and clear. So just you can note down one truth table here. Sir, if this is preset and if this is clear, just I am writing here flip-flop operation, and this is very very important things. Now sir, what is the input? Suppose I am assuming here JK flip-flop. Or you can assume, sir, here this is T flip-flop. Okay, T flip-flop. So if a preset and clear are 0 0, in generally both are active low category. So practically this cannot be possible. In same time preset and clear both cannot be work. This is practically active low. So you can also write, sir, this is preset bar, clear bar. If this is 0 0, so preset bar and clear bar both cannot be 0. And if this is working 0 0, or if preset and clear are working, this T can be anything. This T is not, if this T can be anything. So what I am saying here, this is preset, here this is preset bar, and here this is clear bar. If preset and clear any one are working, then input can be anything. Okay, input will not affect to the output. Preset and clear will only affect to the output. This is very very important point. So this table is very very important. Input can be anything. This is flip-flop, input can be anything. If preset and clear 0 0, this is not possible. So practically this is not possible. So both cannot be work simultaneously. Okay, now if T can be anything, and if this preset is 0 and this is clear, it means preset is operating. So if preset is if preset is operating, so what we can say, flip-flop is a preset. If flip-flop is preset means your Q will be is equal to 1. Can I write now? If this T is anything, if this preset is 1 and clear is 0 means clear is operating. So what we can say, flip-flop is clear. Flip-flop is clear. Flip-flop is clear means the Q is equal to 0. Now if a preset is 1 and clear is 1, in this situation, this can be anything. So in this situation, according to input, flip-flop will operate. So you can say this is a normal flip-flop operation. Normal flip-flop operation according to input. According to input. So this is very important point. This is very important point. Suppose if this clear is activated, or if this preset is activated, in this situation, what can be the input? It will not affect the output. Output will be decided by either preset or clear. This is very important point. It means which is higher priority here. So preset and clear is up. If operated, input can be anything. Here you can input can be anything. Input can be anything. Output will be depend on the preset and clear. Clear this point? So this is very important point. So now come to the point. In the asynchronous circuit, in asynchronous counter, and already I tell you, asynchronous counter, if you are using the clear, it means this is up counter, and here the which kind of clear we will use? Asynchronous clear. So in GATE exam from last 4-5 years, they are targeting asynchronous clear and synchronous clear, and many students are getting confused here. So if this is asynchronous counter, okay, so definitely clear will be asynchronous clear, and in asynchronous clear, when you will receive it here 101, immediately it will be clear. It will not wait to the next clock. It will not wait to the next clock. This is the important point. This is the important point. It will not wait for the next clock. Clear this point? It will not wait for the next clock. Now, okay, this table should be very much clear. Now we are going to start synchronous counter. Okay, now you'll ask me, sir, where we will use synchronous clear? Okay, one more one more thing I want to tell you. One more thing I want to tell you here. Just if you want, you can note down this. Okay, now sir, if this is a down counter, which kind of down counter? Asynchronous down counter. So suppose if I am going to write here, like this, sir, this is a clock, this is your clock, and now this is Q2, this is Q1, this is Q0, and now I am going to use here preset. This is preset. So if I will use preset, it understood this will be a down counter. So suppose, for example, in a preset you can use here OR gate or bubble. So just I am writing here OR gate, and if this is connected with Q2 and if this is connected with Q0, means if this is 0 and 0, first time 0 and 0, if this is 0 and 0 first time, so you can write here, so this is Q2, Q1, Q0. Initially this is 111, after first clock 110, after second clock 101, after third clock, sir, this is 100. When this both are 00, then this will be preset. So after fourth clock, sir, this is 011. After fifth clock, this is 010. So at fifth clock, this is 0, this is 1, this is 0. So if this is 00, this will goes to preset, and you will not receive this state. Immediately this will reach to 111. So if preset is connected or preset is operating, so you can directly write, sir, this is asynchronous. This is asynchronous down counter. This is asynchronous down counter. If examiner will provide, that is good. But if examiner will not provide, so directly you can say, sir, this is a down counter. And now, sir, this is asynchronous or synchronous. Which kind of preset? Here we are not going to use clear. Here we are using preset. So we can say, sir, this is a asynchronous preset. So asynchronous preset and asynchronous clear immediately operate when this will receive the signal. So here if you will receive 0, immediately it will operate. It will not be depend on the input, and it will not wait for the next clock. Clear this point? Similarly for the clear, if you are receiving here 0 signal, so immediately clear function will operate. It will not wait for the next clock, or it will not depend on the input. Immediately flip-flop will be clear. Here immediately flip-flop will be preset. Are you getting this point? So this two thing is very, very important. If examiner will provide you asynchronous clear or asynchronous preset, it is understood the question is came from the asynchronous counter, because in only asynchronous counter we use asynchronous clear and asynchronous preset. Second important point, sir, is this up counter or is this down counter? So if you are using clear, it means this is a up counter, or if you are using preset, it means this is a down counter. Okay, so this thing you should know. Now we are going to start synchronous counter. Synchronous counter is again very easier topic. So synchronous counter is very, very easier topic. Okay, so now come to the next synchronous counter. Come to the next point, that is synchronous counter. Okay, that is synchronous counter. Clear this point? Okay, now. So now, sir, synchronous counter. Synchronous counter, here in synchronous counter, we will not use clear and we will not use preset. Everything will be here designed by the clock. Everything. So in synchronous counter, suppose if you want to implement mod pipe up counter, suppose for example. So in synchronous counter, directly I am going to start from mod pipe up counter. Okay. So mod pipe up counter. Okay, this is not down. Mod pipe up counter. Suppose if you want to implement, and if you are comfortable in this, anything you can design here. Sir, mod pipe up counter. Okay, now by using T flip flop or by using JK or by using any flip flop, I am going to design by T flip flop. So here you have to write the table. Sir, this is the present state, and here this is the next state. This is present state, and here this is next state. Here again we can also use, here again we can also use a clear button and preset button we can use, but that is a bad design, So here again synchronous standard up and standard down you can study, but I am not going to teach you standard up and standard down in synchronous. Only asynchronous you remember, standard up and standard down. Okay, so here two kind of design can be possible. Examiner can provide you standard up and standard down, and now again the clear and preset button they can use. So in synchronous counter, again asynchronous clear and asynchronous preset examiner can be used in gate exam, but in real life we don't use. But in gate exam, here two kind of question can be framed here. So first I want to tell you mod pipe up counter, how you can implement by synchronous counter. So first you can design here standard up counter. Standard up counter, which kind of? Synchronous. Okay, but generally we will not use, but if you can design standard up synchronous counter. Okay, so you will provide here clock, and you will provide clock to all the flip flop. Okay, now here this is 3 output, so if this is standard up counter, and this is which category of? Synchronous category. Okay, sir, this is Q2, this is Q1, and this is Q0. Now if you want to implement mod pipe up counter, so what you will do here, again you will use here clear button, and again you can connect here one NAND gate, and again this is connected with this Q0 and Q2. So you can write, sir, this is a mod pipe up counter. This is a mod pipe up counter. Which kind of? Synchronous. Already they have given synchronous. So this is a synchronous counter. This is a synchronous counter. Now if I will ask you, sir, which kind of clear here? Which kind of clear here? So here in asynchronous, always clear will be asynchronous clear. Means clear is not depending on the clock. Here again, which kind of clear this is? This is asynchronous clear. Asynchronous clear. So here examiner can provide you like this kind of block, Okay, examiner can provide you this kind of block for the synchronous counter. So they will specify here which kind of clear they are using. This is asynchronous clear or this is synchronous clear. So here this is asynchronous clear. Why asynchronous clear? Because this counter is a standard up counter. Now the same question again we can also design in this way. Okay, later I will discuss this. Okay, now here I am going to write suppose if examiner will provide you here clock, okay, and here this is a specific, okay, mod 5 counter. This is a specific mod 5 counter. If this is a specific mod 5 counter, which kind of synchronous? Only in synchronous this is possible, this is synchronous, and this is 3 output. And now if again examiner will write this is clear bar, again this is NAND gate, this is for representation, and now this is Q0, this is Q1, this is Q2, and now this is connected here, and now they are saying this is a synchronous clear. This is a synchronous clear. So if examiner will mention here synchronous clear, it means practically examiner not going to use clear button. This is representation only. I will tell you what is exact circuit for this. I will explain you. But for what is exact circuit for this, first you will here design a standard up counter, then you will use Q0 and Q1, and that Q0 and Q1 will be connected with NAND gate. But here practically this Q2 and Q0 is not going to connected with NAND gate. This is only representation. So if examiner will mention synchronous clear, it means this is not actual circuit. Actual circuit now we will study. Then definitely you should know, sir, what is synchronous clear? Asynchronous clear already we have studied in asynchronous counter. So same thing will be happen in synchronous counter. So you will design a standard up counter, and you will consider Q0 and Q2 and Q0 and Q2 will be connected from NAND gate, and that will be connected to clear. This is asynchronous clear. But what is the synchronous clear? So representation you can use this, examiner can also use this, but the circuit is totally different. So how you can implement this? So first you can write present state, sir, Q2, Q1, Q0, and here this is Q2, Q1, Q0. This next state I can write here plus plus plus. You can write. Okay, so if you want to implement mod 5 up counter, so you can start from 0, 0, 0, and this is sir 0, 0, 1. This is 0, 1, 0. So first you have to complete the table. Now sir, this is 0, 1, 1. This is 1, 0, 0. Sir, this is 1, 0, 1. This is 1, 1, 0, and this is 1, 1. Don't write here till 5. First you have to complete the, always this first truth table for 3 bit you have to write in a standard order. This is very standard protocol. Now this will be the output state. So for 0, 0, 0, what will be the next state for up counter? 0, 0, 1. Sir, what will be for 0, 0, 1 next state? This is the 2. For 2, sir, next state is 3. Okay. Sir, for 3, next state is 4. Okay. Sir, for next 4, next state. So you want here total only 4 state. 0, 1, 2, 3, 4. So after 4, again what you want? 0. So after 4, next state is 0. Sir, after 5, practically 5 cannot be possible. But if somebody will start somebody will start suppose from 5, so you can write next state will be again 0. If somebody will start from 6, next state will be 0. If somebody will start from 7, next state will be 0. How many total output state you are getting? 0, 1, 2, 3, 4. So total number of 5 output state you are getting. Now if you want to implement this by T flip flop, so this you can write, sir, this is T2, this is T1, and this is T0. So here excitation table is required. So you know very well excitation table. This and this XOR. So 0, 0 XOR. This is for 2. So this is present state. This is next state for 2. This is for 1, and this is for 0. So here 0, 0 XOR. This is 0. Sir, 0, 0 XOR. 0, 0, 1 XOR. This is 1. Now, sir, 0, 0 XOR. This is 0. 0, 1 XOR, this is 1, 1, 0 XOR, this is 1. Sir, 0, 0 XOR, again 0. Sir, 1, 1 XOR, again 0. Sir, 0, 1 XOR, 1. Okay, if I will get wrong, so you have to correct or please comment me. Okay, now the next, sir, 0, 1 XOR, this is 1. Sir, 1, 0 XOR, again this is 1. Sir, 1, 0 XOR, this is, now the 1, 0 XOR, sir, this is 1. Sir, 0, 0 XOR, this is 0. Sir, 0, 0 XOR, this is 0. Now, sir, 1, 0 XOR, this is 1. Sir, 0, 0 XOR, this is 0. Sir, 1, 0 XOR, again 1. Now the next, sir, 1, 0 XOR, this is 1. Sir, 1, 0 XOR, this is 1. Sir, 0, 0 XOR, this is 0. Sir, 1, 0 XOR, this is 1, 1, 1. Because this is 1, 1, 1, this is 0, 0. Now you have to find out value of T2, T1, and T0. Now you have to find out value by using K-map. By using K-map, what is the value of T2, T1, and T0? What is the value of T2, T1, and T0? So if I am going to find out, okay, for T2. So for T2, what value you will get? So for T2, T1, T0, You have to find out value. This is Q2, Q1, Q0. This is Q2, this is Q1, this is Q0. Sir, this is 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 1. You can put the value 3, 0 and 5, 1. Sir, this is 0, 0, 0. This is 1, 2, 3, 4, 5. So, which group you will, what you will get here group? So, this will be one group and this will be one group. So, what you will get here? So, this T2 is nothing but from here, this is Q2 plus from here, this is Q1, Q0. Q1, Q0. Similarly, I am not going to complete solve this. Similarly, T1 and T0, you have to find out. So, T1 and T0, you have to find out. So, T1 and T0, again, you will get in terms of Q2, Q1, Q0. Again, you will get in terms of Q2, Q1 and Q0. Okay. So, we will find out T2, T1 and T0. Are you getting this point? Now, you can implement the circuit. So, just I want to tell you what will be the inside of this circuit. This is representation. So, what is the here? Sir, synchronous clear. What is the synchronous clear? So here you are not going to use clear button. Directly you are going to design mod 5 up counter. So just you will write here, this is first flip flop, this is second flip flop, this is third flip flop. Suppose you can write here 2 1 0, or you can also write, so this is 0 1 2. This is your choice. So if I am writing, this is T0, this is Q0, this is Q0 bar, this is T1, this is Q1, this is Q1 bar. This is T2, this is Q2, and this is Q2 bar. Now same clock you have to provide it to all the flip flop, because this is synchronous counter. This is synchronous counter and this is your clock. Now in this we don't use clear and preset button. Okay, we will not use. Now this T0 value you have find it out, this T1 find it out, this T2 you have find it, just you have to connect. So here some logic gate will be present. So if I want to write T2, so T2 is nothing but Q1 Q0. So you can write, sir, this is Q0 and this is Q1, this is AND gate. Q1, Q0 and that OR with Q2, this is your Q2. Okay, I can write here one AND gate. This is AND gate. Sir, this is Q0 and this is Q1. This AND gate and this AND gate OR with, this AND gate OR with like this. This will be your T2. Similarly, T1 and T0, you can find out from here. So some logic gate will be required here. So in most of the synchronous counter, logic gate will be 100% required. Okay, so like this T1 and T0 you can find out. Now you can see here what is the output of this circuit. If you will operate this circuit, so initially this Q2, Q1, Q0 will be, sir, 0 0 0. Then after first clock this will be 0 0 1. After second clock this will be 0 1 0. After third clock this will be 0 1 1. And after fourth clock this will be here, this will be 1 0 0. And then after 5 clock this will be again 0 0 0. So here you are not going to use, okay, you are not going to use preset and clear button. This kind of circuit is called, this is a synchronous clear. Synchronous clear. But if you want to represent this circuit in this kind of block, how you will represent? How we will represent? So examiner will represent in this way, and now they will write synchronous clear. So if this kind of question examiner will provide you, it means when this is going to be clear, when this is 1, when this is 1, when this is 1 and 1. Okay, it means you can write, this can be anything. So first time Q2 and Q0 will be 1 at 5. So this is the last state. So you can write here answer. This is the last state. After this circuit will provide you 0 0 0. Are you getting my point? So here what is the answer of this circuit? This is not mod 5, sir, this is mod 6 counter. So this is a mod 5, this is last state, and after that state in the next clock, circuit will provide you 0 0 0. But what will be the inside of this circuit? This is the actual circuit. Here clear button we are not going to use, but examiner will represent in this way. Are you getting my point? So if synchronous clear they will use, it means synchronous clear will be only possible in synchronous counter. So either they will provide you in this way circuit. So in this way circuit, examiner will not say, sir, this is synchronous clear. Directly they will ask you, this is a mod n counter, what is the value of n? And if they can also provide you in this way, and they will write here, this is synchronous clear. So if they will write synchronous clear, it means the last state you are receiving here, that state you will get, and in next clock cycle the circuit will be clear. So in general, student will write here, if this is a, in general for asynchronous clear, if this is a mod 5 counter, for synchronous clear this is a mod 6 counter. In general, student will write in this way, but meaning should be very much clear to you. This is very important thing. So now anything you can design, okay, like this, any present state right, next state right. Oh, okay, and by any flip-flop you can implement the circuit. If you want to implement standard up counter, so for standard up counter, for 4 you can write, sir, here 5. For 5 next state you can write here 6. After 6 this is next state 7, and after 7 again you will receive 0. So if you will implement circuit for this, so this will be standard 3-bit up counter. This is standard 3-bit up counter. This is the synchronous counter. So I hope what is synchronous clear. What is asynchronous clear? I hope this thing is clear to all of you. I hope this thing is clear to all of you. Okay, so please just once confirm me. The synchronous clear. What is the synchronous clear exactly meaning? But in GATE exam easily you can handle. If they will provide synchronous clear, so you remember this is the last state. That state you will receive. That state you will receive. And your next clock you will get the clear. Okay, and this can also be connected with preset. So what states here you are getting, that is last state will be received, but in asynchronous clear the last state will not be received. What will be the inside of this circuit? This circuit. Okay, this circuit. Clear this thing? But this is mod 5, sorry, this is mod 5 counter synchronous. No, here answer is wrong. No? This is mod 6. Sorry, this is correct. This is mod 6. This is mod 6 because the answer is mod 6. This is mod 6. This is not mod 5. Clear this thing? This is, if you want to implement mod 5, so you have to clear for 4. You have to clear for 4. 1 0 0. Clear this thing? Okay, so I hope now easily you can handle question from here. So now I am going to take some question from this synchronous counter. Some question from this synchronous counter. Okay, clear these points? So now I am going to take some question from here. Okay, so actually if you can see, sir, resistor topic is very easier. Asynchronous counter, something you should remember in asynchronous counter. Okay, now one more question. If you will ask me, sir, what will be the frequency here? So in a synchronous counter, what is frequency here? What is frequency here? What is frequency here? So just you have to write like this. And again, already we have discussed previous methods. In same way, you can write what is the frequency here. So what is the frequency here and what is the frequency here? Clear this point? If you can see the difference between asynchronous and synchronous, in asynchronous, in between two flip-flop, no logic gate is present. But in synchronous counter, 100% logic gate will be present for more than 2-bit. For more than 2-bit. Clear this point? So now I am going to take some question from here. I am going to take some question from here. Okay, now I am going to take some question from here. So, but first please comment. Okay, now come to the point. Okay, now come to the point. Suppose I am asking you one question from synchronous plus asynchronous. Examiner can also ask you question from asynchronous counter, asynchronous plus synchronous counter. Examiner can ask you the question from asynchronous plus synchronous, synchronous plus asynchronous counter. Suppose first problem I am going to consider. First problem I am going to consider, and if you can handle this question, it means easily we can handle any question. Okay, then after completion of this, okay, at 9:30 we will take a dinner break from 9:30 to 10:30, and after dinner break we will start propagation delay in this synchronous circuit, means setup time and hold time. Then we will discuss setup time and hold time. So today I will discuss setup time and hold time. Okay, and after that setup time and hold time, we will discuss some number of problem, and also I will discuss ADC and DAC. So today already we have discussed latches. Latches, not latch is important. You remember 1-bit memory. D latch is also important, and SR latch by NAND gate, by NOR gate. And what is NAND latch and what is active low NAND gate latch? That thing should be definitely clear to you. What is a flip flop? SR flip flop, JK flip flop. JK flip flop, level triggered problem, race around. Race around, how we can eliminate? We have 3 methods. Examiner can ask question from the first method. Remember, propagation delay flip flop should be more than clock pulse time period, clock pulse time period, and less than, sorry, clock pulse width and less than clock time period. So clock that will be more than, clock pulse width, and that will be less than clock time period. Okay, this thing should be clear, okay. Now after that, we have discussed D flip flop and T flip flop. Excitation table, characteristic should be clear to you. Conversion of flip flop should be also clear to you. And then we have started register. Register is very basic circuit. 4 operation can be performed by the shift register, ring counter and Johnson counter. You remember basic maximum number of output states, okay. And then we have started counters. In counter, asynchronous counter. In asynchronous counter, standard up, standard down. This thing should be very much clear to you. How we can find out frequency at any states, this thing should be clear. How you can implement mod and counter, and how you can use preset, and how you can use a preset for up counter or for down counter, and where we are using preset and clear, that is synchronous preset or asynchronous preset, or synchronous clear or asynchronous, that is asynchronous, okay. Now we have started synchronous counter. In synchronous counter, we have discussed first, just you have to write present state and next state, okay. So you will get the circuit, okay. So in synchronous counter, easily we can handle any gate question, but in synchronous counter, you remember two kind of design can be possible to implement mod and counter, but in real world we don't use here clear and preset button. Generally we will use here synchronous clear or synchronous preset. So already I have explained you both the cases, okay. So how you can handle, if examiner will provide you mod and counter, they are asking for synchronous clear. So for asynchronous and synchronous clear, you will get only one clock period difference, okay. So mod n, if in asynchronous clear, suppose mod n, then synchronous clear mod n plus 1 will be the answer, okay, means n plus 1 will be the answer. And now I am asking one question, one circuit from asynchronous plus synchronous, and this is very important, okay. Anybody can handle, I know, but in gate exam within 1 minute, 2 minutes, 3 minutes, how you can handle synchronous plus asynchronous, this is the important point, okay. How you can handle synchronous plus asynchronous in gate exam, this is the important point, okay. So I want to discuss here, okay. Now suppose one question I am considering, suppose this is first flip flop, so at least 3 flip flop is required, yes, definitely minimum 3 flip flop will be required, okay, for synchronous plus asynchronous. Suppose for example, what we are assuming, sir, these two are suppose synchronous. So suppose, sir, these two are synchronous, this is clock, okay, these two are synchronous. I can write, sir, this is suppose T0, Q0, this is Q0 bar. Suppose this is T1 and this is Q1, this is Q1 bar. Suppose this is a T2, this is Q2 and this is Q2 bar. Suppose like this, okay. And now suppose for example, this output is connected to here. It can be positive as triggered, it can be negative as triggered, it can be connected from here, it can be connected any from anywhere, it can be connected. Okay. Now suppose I am going to assume, suppose this output is connected to here, and suppose this value is 1. This value is 1, and suppose this value is 1. Always asynchronous. This is asynchronous, and always asynchronous t value will be 1. Always this will be. So you can see, sir, these two are synchronous and these two are asynchronous. So these two are synchronous, and here these two are, sir, asynchronous. How we can handle this category of question? So first you can find out solution of this. How you can handle this category of question in gate exam? So you can see, you have to write like this, sir, this is Q0 and this is Q1. First you have to write, and sir, this is Q2. First you have to write, first you have to solve this part. Okay. So how we can solve? Sir, initially you can assume 0, 0. Okay, so initially this is, you can also assume this is 0. Initially everything is 0, 0, 0. Now sir, after first clock, so how you can handle here, you can see, so initially this was 0 and initially this was 0. Okay, so before going to apply first clock, you should know the input. This input is 0 and this input is 1. So this will be toggle and this will be no change. So after first clock, this Q0 will be toggle and Q1 will be no change. Okay, so after first clock, don't write here Q2. Okay, now, so what will be output? You are getting here 1. sorry, you are getting here 1 and you are getting here 0. Now before applying the second clock, now this is 1, this will be always toggle. Now at second clock, sir, this is 1. So now at second clock, sir, this is toggle 0 and this is going to be 1. This is going to be toggle, sorry, this is 1 and this is 1, both will be toggle. So this toggle to 0, this 0 toggle to 1. Now after, sir, third clock, after third clock, what will happen? So now this output is, this is 0 and this is 1. So now this is 0 means no toggle and this is always toggle. So at third clock, this first will be toggle, second will be no toggle. At third clock, this will be toggle 0 to 1 and this is same, this is 1. You have to write till the value is not going to be repeated. Now, sir, at fourth clock, now again, before applying the fourth clock, sir, this is 1 and this is 1. So before applying the fourth clock, you can see this will be toggle and this will be toggle. After fourth clock, both will be toggle. So this will be 0, 0. Now this is repeated. Now you can write for the next, you can also write, sir, for the fifth, this will be 1, 0. For the sixth, sir, this will be 0, 1. For the 7, again this will be 1, 1. After 8 clock, sir, again this will be 0, 0. Okay, but you don't have to write. If the value is repeated, you have to stop. So you have to stop at this point. So now come to the Q2. Now you can see here. This is working as a positive edge trigger flip flop. Okay, positive edge trigger flip flop means when this Q1 bar is 1, then you will get here clock. Q1 bar is 1. So Q1 bar is 1. So here what I can write. Now the important thing is, you can see, just I am going to write this flip flop. Here, this is Q1 bar. If Q1 bar is 1, so if this is T, and when Q1 bar you are getting 1, so if I will plot here, you can say Q1. Suppose this is Q1, and what will be, sir, Q1 bar. So Q1 bar will be like this. Like this. So this is a Q1 bar positive edge triggered. It means in this point. So if this is a Q1 bar positive edge triggered, so you can write, sir, Q1 negative edge triggered. So can you write in this time? So in this time you can also write. If you want to write Q1, you can write here in this time. So from Q1 you can also find out. So this is a very, very important thing. So you can also write, sir, this Q1 bar. You can connect from here and you can write here negative edge trigger. Both are same because this is connected with Q1 bar. So Q1 negative edge trigger. So you don't have to find out here Q1 bar. Just you have to check this is Q1 with negative edge trigger or Q1 with positive edge trigger. Those two choices. So if this is a negative edge trigger, means when Q1 are moving from 1 to 0. So when Q1 is going to change from 1 to 0, in that time this flip flop will toggle because this is 1. So you can see how many times Q1 is going to be from 1 to 0. So this is a first point, 1 to 0, and now you can also write, sir, this is second time. Okay, so in this only 1 to 0 one time, this is going to be changed from 1 to 0. So initially if this Q2 was 0, so this will be 0 initially, this will be 0, this will be 0, but when this is going to be 1 to 0, this will be toggle, so 0 to 1 you will get. Now again this one will continue, this one will continue, this one will continue, this one will continue. When this is going to be 1 to 0, this will be toggle 1 to 0. So you are getting this output. So at least 2 times you have to write. You don't stop here. So if this is a 3 bit, so at least till 8 you have to write. So if you have started from 0, 0, 0, this is 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, and then 0, 0, 0. So here all the states you are getting. But this is Q0, Q1, Q2. If you want to write in Q2, Q1, Q0, if you want to read this, so this is 0, 0, 0, decimal 0. Sir, this is decimal 1, this is decimal 2, this is decimal 3, this is decimal 4. Sir, this is decimal 5, this is decimal 6, this is decimal 7, and this is 0. Wow, this is magic. Sir, this is 3-bit up counter. This is a 3-bit standard up counter without any logic gate. So if I will ask you, this speed will be more than asynchronous counter? Yes, this speed will be more than asynchronous counter. But if you will implement by synchronous counter, logic gate is required. Here no logic gate is required. So this is the magic of digital. If you don't want to apply any external logic gate, okay, but if you want more speed, so the synchronous plus asynchronous design sometime it can be better That's why in GATE exam they can ask question from here. Already in previous year one question has been asked from synchronous plus asynchronous. Already one question has been asked from synchronous plus asynchronous. So how you can handle in GATE exam? So if they will provide two synchronous then asynchronous, so first you have to solve this at least for 3 bit till 8 you have to write. Then you have to check for when this is going to be functional. So just you can check when this is connected with negative edge trigger, it means when q1 is moving from 1 to 0, 1 to 0, in that time q1 will be, in that time sorry, q2 will be toggle. So q2 will be toggle, so you can write in this way 1 to 0, 1 to 0. So in these two places only q2 will be toggle, and the remaining place q2 will be continue. This was the first question. This was the first question. Now if I will ask you, sir, what is the frequency here? What is the frequency here and what is the frequency here? What is the frequency? If this is a f clock, suppose if this frequency is f clock, then what will be the frequency here, here and here? You can see this is standard up. So here you can see, sir, this is 0 0 0 0, then 1 1 1 1. So this 4 0 and this 4 1, and this value will be repeat repeat repeat. So q2 frequency will be divided by 4. Sorry, this 4 0 and 4 1 na? Now this complete 4 0 and 4 1. So this is nothing but 8 time period. So here f clock by 8. So here frequency will be f clock by 8. Okay, this is a mod 8 up counter. This is a mod 8 up counter. So this answer is a mod 8 up counter. So that you can write this f clock by 8. Sir, what will be frequency here? Sir, this is 0011. Sir, this is 0011. So you can say 40. It means here frequency is f clock by 4. Sir, what is the frequency here? Already we have discussed for synchronous and asynchronous. This is a mixed question. So again, if you want to find out frequency, just you have to write the table and just you can find out from here. Here, sir, 0 1 0 1 0 1. So this 2, this 2, this 2, this 2. So here frequency is f clock by 2. So here frequency is f clock by 2. This is the answer. This is the answer. Here frequency is f clock by 2. Clear this point? Now, if here examiner will ask you how many design can be possible, here this is two synchronous then asynchronous. Okay, examiner can also provide you first two asynchronous and then two synchronous. Any two will be here synchronous and any two will be asynchronous. Only this can be possible. So this can be synchronous and this can be asynchronous. Second design, here this can be asynchronous, can be here. Asynchronous can be here. Okay, so first two will be asynchronous and next will be synchronous. So now one more question I am going to consider from here. So please just confirm me this thing is clear or not, so that I can continue. Please confirm me. Okay, please confirm me. Okay, so that I can continue the session. Okay, so that I can continue the next question. So please first confirm me. Okay, I am waiting for your answer. Please reply everyone. Na? If you will not reply, how I can motivate? How I can motivate? Okay, no issue. Okay, next question I am going to consider from here. Next question I am going to consider from here. Okay, now the next question. So now here, suppose for example, again this is a first flip-flop, this is second flip-flop, but these two are connected with asynchronous. Okay, now this is your clock, this is your clock, and suppose this output is connected to here in positive, so it can be positive edge trigger or negative edge trigger. So now I am saying, sir, this is T0 and always this is 1. This is 1, suppose I am considering this is Q0, this is Q0 bar. Now here this is T1, this T1 will be 1. So asynchronous, this is asynchronous connected with this one. So here always T1 will be 1, 100%. And this is Q1, this will be Q1 bar. Okay, now, and now one more I am going to considering like this. Okay, now, and this is suppose T2, this is Q2 and this is Q2 bar, and suppose this same clock suppose is going to connect it here like this. It means these two are connected synchronously, and this output suppose I am going to connect from here like this. Okay, and this is your Q2. Okay, so if I will ask you what is the mod encounter this one and what is the sequence, so you can write, sir, this is Q0, this is Q1 and Q2. First you have to write, initially you have to assume, initially, sir, this is 0 0 0, then after first clock, after second clock, after third clock, after fourth, after fifth, after sixth, after 7 and after 8, what will be the output? How you can handle, so you can see here, first flip flop will always do toggle. If this is 1, so always this will toggle. So first flip flop will always do the toggle. Okay, so Q0 you can write 0 1 0 1 0 1 0. Okay, yes, we can write. Now when this flip flop and this flip flop will work, so this is when Q0, if I am going to plot Q0, this, if Q0 is a, suppose I can say this is a clock, so this is a positive edge trigger, this is a positive edge trigger. So if this is positive edge trigger, sometimes this can be negative edge trigger, this can be positive edge trigger, but that will be complicated, but you can handle. How you can handle, sir, this is positive edge trigger, so this flip flop will work when Q0 is moving from 0 to 1. So when Q0 is moving from 0 to 1, in that situation this will work. Again this is connected with this Q0 and this is positive edge trigger, so again this will work when Q0 is moving from 0 to 1. So first you have to find here Q0. So Q0 will be, sir, 0 to 1, then 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0. Then, sir, when Q1 and Q2 will work? Q1 and Q2 will work simultaneously. Q1 and Q2 will work simultaneously. Now here one important thing, both are working at same time. So when this block will get clock, so now this work is completed. Okay, just I am going to remove this. So this work is complete. Now you can say this is clock and this is nothing but Q0. Okay, and this is positive edge trigger. Okay, so now when Q0 is moving from 0 to 1, so this is the first clock, 0 to 1. So here this is the first point, 0 to 1. Now this is second clock, this is third clock, this is fourth clock. So in this situation 0 to 1 you are getting, it means here we are getting clock. So when you will get here clock, initially you can write, sir, this was 0 0 and this is 1. So if you are applying first clock, this will be toggle, always this will be toggle, but this will no toggle. So in the first clock, so this will be first clock here, second, third, fourth. For this block only you are getting fourth clock, So this is first clock for this block. So at this point this will be toggle, this will no toggle. So first will be toggle 0 to 1, first will be toggle 0 to 1 and second will be no toggle, this will be 0. Okay, so now next clock you will provide here. So again this data will copy 1 0, the data will be continue. Okay, now in the next clock this is 0 1. So what is the output? So this output was 1 and this output was 0. So when you are applying next clock, so this will be toggle and this will be toggle, both will be toggle. So directly you can write this 1 to toggle 0 and this 0 to toggle 1. Now again this data will be repeated 0 1. Now in the next clock this is 0 1. So now this is 0 and now this is 1. So in the next clock first will be toggle, second will be not toggle. So first will be toggle from 0 to 1, second will continue. Now again this data will continue 1 and 1. So now in the next clock, now again this is 1 and 1. So now this is 1 and 1. So both will be toggle. So in the next clock both will be toggle. So you will get here 0 0. Again this will be continue. So 0 0 data is repeated. If you want to write this, sir, this is 0. This is 0 1 1. This is 3. Sir, this is 0 1 0. Sir, this is 2. This is 1 0 1. This is 5. Here this is 1 0 0. This is 4. Here this is 1 1 1. This is 7. Sir, here 1 1 0. 1 1 0. This is 6. 0 0 1. This is 1. Again this is 0. So you can say this is mod 8 counter but not standard up or standard down. This is mod at random counter. So you can say, sir, this is mod 8 counter but not standard up, not standard down. This you can say, sir, this is a random counter. Mod 8 random counter. So examiner can ask you question from here. This is very good question. So now if I will write here, here this is a clock, and here this is T0, this Q0, this is Q0 bar, and here this Q0 is connected to here, and this T0 is 1. Now if I will ask you, sir, what is the frequency here? What is the frequency here? What is the frequency here? And what is the frequency? So here you can write, sir, this f clock by 8. Okay, and first will be always toggle 0 1 0 1 0 1. After that again 0 1 0 0. So here, sir, f clock by 2. But what will be the frequency in between? Now you can see for the random counter you have to check. So here, sir, this is 0 1 1 0, again 0 1 1 0. So sir, this 4 block is repeating 0 1 1 0, 0 1 1 0, then again 0 1 1 0 will be repeat. So here time period will be 40. So here this will be f clock by 4. So you have to check like this. So for random counter you can also find out the clock frequency. So here 8, here 4, here 2. But this is not a standard up or standard out. This is a moderate random counter. So this is the second way. So examiner can provide you question in this way. First stages I have consider here two state. First that is your synchronous, then asynchronous. Here first this one is synchronous and this one is asynchronous. Now one more question can be framed. First and last stage will be synchronous and in between state is asynchronous. How you can handle? Or you can say first and last states are asynchronous and in between states are synchronous. So now I am going to take one more question from here. I hope this thing is clear to all of you. Okay, now so now the next question again I am going to consider next question. So 3 flip-flop I have considered here. So now, sir, first and last are synchronous. So sir, this first clock and last are synchronous. Okay, and sir, this one is asynchronous. So this one is asynchronous. So now what you can do, this suppose this output is connected to here, suppose this output is connected to here, and now this is connected with this two asynchronous, and suppose for example we can write suppose this is connected to here like this, in this way. What you can say, so these two are the synchronous and these are the asynchronous. So in GATE exam, how you can handle this? So can you rearrange this? Okay, one more important thing, sir, this is connected with asynchronous. Okay, now you can change this, this output is connected to here, this output is connected to here. Suppose this was the question, how you can handle? So you can see this and this are connected synchronously and this are connected asynchronously. So can we handle this question or not? Can you handle this question or not? So one important thing, sir, this input is going to be depend on this one. Okay. So what you can do here, first you can operate this two. So you can see I am going to write here, sir, this is Q0, this is Q1, this is Q2. Initial state 0 0 0. First, after first clock, after second clock, after third, after fourth, after fifth, after sixth, after 7 and after 8. Sometimes student will be trapped in this category of question. So what you can do here, first you can operate this two. Okay, so later I will operate the last one. So because this will be depend on this input. So first I am going to operate this two. So in first clock, in every clock you can say this is one. So this will be toggle. So Q0 will be toggle every time. So can I write, sir, Q0 will be toggle 1 0 1 0 1 0 1 0. Q0 is going to be toggle. Okay. What will be the clock for this second? Sir, clock for the second one is when Q0 is connected with positive edge trigger, it means Q0 is moving from 0 to 1. So when Q0 is moving from 0 to 1, it means this time, and it means this time. So what will be the Q1? And this Q1 is always 1. It means when you will receive here clock, this will provide you toggle. So in this position, this will provide toggle 0 to 1. Now 1 will continue. Again in this position, this will toggle. And again this 0 will continue. Again in this position toggle. This will continue. Again in this position, this is toggle and 0 will continue. So Q0 and Q1 you have handed out. Okay, so now you can see this third flip-flop is connected with original clock. So again you can operate. So initially this was 0. So when you are providing first clock, you can see what is this input. So if you are providing the first clock, initially what was this Q1? What was this Q1? So if Q1 is 0, if this Q1 is 0, so when you are providing the first clock, this Q1 was 0. If Q1 was 0, it means this will not toggle. This will not toggle. So you can see if this is 0, so this will not toggle. So 0 will continue here. Now again for the next clock, again you can see here Q1 is 1. It means this will toggle. So this 0 to 1. Again you can see Q1 is 1. It means this will toggle. So 1 to 0. Again you can see here this is 0. So no toggle. 0 will copy. Again this is 0. No toggle. 0 will copy. Again you can see this is 1. So this will be toggle. Again this is 1. So this 1 to 0 toggle. 0, this no toggle. So you are receiving this output. You are receiving this output. So here are you getting all the states? Okay, so you can check. Sir, if you will count this in decimal, this is 0. Sir, this is 3. This is 1106, sir. And this is 1. Again, this is 0. Again, this is 3. Again, this is 6, sir. Again, this is 1 and again this is 0. It means 0361, then 0361, then 0361. So this is nothing but 1 state, 2 state, 3 state, 4 state. This is mod 4 random counter. Mod 4 random counter. This is the highest level of question. Okay, very few people can handle this question in GATE exam. Very few people. So always if any kind of question is given, just you have to write like this table. Any question you can handle. Any question easily you can handle. My recommendation, don't write the equation of the next state. Directly you can process in the circuit. Okay, directly you can process in the circuit. Only two category of questions will be provided, either synchronous or asynchronous. So in this question, I am going to deal both the things, synchronous and asynchronous. So I hope this thing is clear to all of you. This is a mod for random counter. Now if I will ask you what is the frequency here, so here frequency will be definitely f clock by 4. But what will be the frequency here? And sir, what will be the frequency here? So you can say at Q0, sir, this is 01010001. So here frequency is, sir, f clock by 2. But what will be the frequency at Q1? You can check 0110. So this 4. Then 0110. So here frequency is again f clock by 4. F clock by 4. So here divide by 2, divide by 4. Here divide by 4. Only examiner can ask you this category of question. Examiner can ask you mod encounter. Examiner can provide you any circuit, synchronous, asynchronous. They will either only synchronous or only asynchronous. They will mix synchronous plus asynchronous, and they can ask you frequency anywhere. Only this category of question can be asked. Okay, so I hope this thing is clear to all of you. Okay, I hope this thing is clear to all of you. Can you handle this? This is not a basic and easy question. This is a highest level of question. Again, I am saying very few people can handle this question in GATE exam. Very few people. Most of the student will be wrong here, because in the question, what I did, this and this are synchronous, these are asynchronous, and this is connected asynchronously with this, but this output is connected to here. So first you have to think which block first, which block I have to operate first. So first I have operated this block. I have not operated this and this simultaneously. Why? Because this block is going to be depend on this one. So first I have operated only this block, then I have operated this block and this block, then I have operated third one. So here 1, 1 and 1, sometime 2 and 1, sometime simultaneously 3 you can also operate. Clear this point? So now we are going to take a dinner break. Okay, dinner break. Sir, will you teach communication also? Yeah, I am planning. Okay, today digital will be finished. Okay, so one day signal and one day communication I am planning. Tomorrow I will discuss something. Okay, because today is 30th. Okay, but I will try to conduct one session for signal and one session for communication. Okay, and in that part directly I will discuss the exam oriented. Okay, I will not discuss much theory part. Directly I will discuss the concept, okay, which can be asked in GATE exam. Okay, but this is, you can say, if you will ask me, sir, if you want to give any question in GATE exam, so definitely I will give you this circuit. You can see the magic in this circuit. You have implemented mod 4 counter, but none of the external logic gate you have connected here. This is a magic of synchronous plus asynchronous counter. Okay, so now can we continue after break? So now the time is 9:32. After 1 hour break at 10:30 we will meet, and 10:30 we will start. Here we will discuss some question, and immediately I will start setup time hold time concept. Okay, immediately I will start setup time hold time concept, and then also I will discuss some part of ADC and DAC. Okay, and already 6 transistor SRAM, how you can implement. One student are asking, sir, semiconductor memory. Already we have discussed, okay, ROM, PROM, and in today at the time of starting, okay, 6 transistor SRAM or 1 bit memory structure, how you can implement. Okay, so all the questions definitely you will get from semiconductor memory from this part, okay. So if time will persist, I will discuss some more thing in semiconductor memory. Okay, so we will meet at 10:30. Okay, if anybody have any doubt, please ask me. Okay, if anybody have any doubt, please ask me. If anybody have doubt, please ask me. Okay, no doubt. Okay, no issue. So we will meet at 10:30. So you can take the dinner, and after dinner again we will enjoy with setup time, whole time concept. We will discuss number of problem. Okay, and also we will discuss ADC and DAC. Okay, thank you, take care. Okay, welcome back everyone. So once just confirm me audio is clear to you or not. Okay, and everyone join now the session. Okay, and now I am going to start to discuss setup time and hold time concept. I hope this thing is clear to all of you and easily you can handle question from synchronous plus asynchronous counter. So everyone just comment me. Okay, now I am going to discuss setup time and hold time concept. But before going to start that part, first I want to discuss. What is a maximum clock frequency we can provide in synchronous counter. So already in asynchronous we have studied, and synchronous how we can handle, and in synchronous counter how we can handle. Okay, now so come to the point. So everyone please join the session. Okay, you was waiting for this topic, setup time and hold time concepts. Okay, now come to the point. Okay, now everyone please just confirm me audio is perfect or not. Okay, so our next topic is here setup time and hold time concepts. Okay, so one important thing you should remember here, this setup time and hold time concept. Okay, this is generally we use this concept in synchronous category of circuit, or you can say synchronous counter. This concept we used in synchronous counter. Okay, this category of this setup time and hold time concept we use in synchronous category of counter, not in asynchronous category of counter, but we can use synchronous plus asynchronous. So only in synchronous counter, or you can also say sir in asynchronous plus synchronous counter. Okay, but not only in asynchronous. Already we have studied in asynchronous. So first I am going to write for asynchronous counter, for asynchronous, what should be the app clock? So app clock should be less than or equal to 1 by total delay. What is the total delay? That is number of flip flop into total propagation delay of, can I say, one flip flop. If only flip flop is connected, if logic gate is also connected, we can also use delay of logic gate, but in general you will not get logic gate in asynchronous counter. That's why then we will not discuss. Now come to the synchronous counter. So now I am going to take here synchronous counter. So now I am going to take here a synchronous counter. Okay, synchronous counter. So suppose we have 2-bit synchronous counter. Suppose for example suppose I am considering a 3-bit synchronous counter here. Suppose I am considering here 3-bit synchronous counter, and like this. Okay, same clock is provided to all the flip flop. This is a synchronous counter. Same clock is provided to all the flip flop. Suppose this is T0, this is Q0, this is Q0 bar. Suppose this T0 I am considering 1. Okay, now suppose this is T1 and this is Q1 and this is Q1 bar and this is T2, this is Q2 and this is Q2 bar. If you have seen our previous design in synchronous counter, so here T1 and T2 in general this is not going to be 1. Okay, T1 and T2 is connected with this Q0 bar or Q1 bar or Q2 Q1 bar. So suppose for example if I am considering this T1 is connected with Q0 in this way, suppose, and here some logic gate is also connected. Suppose here one logic gate is also connected, logic gate. And similarly if this Q1 is connected with some logic gate, and this is moving towards, and this is or you can say coming to the T2, and we can say sir this is again a logic gate, this is logic gate. So in this circuit if you can see, suppose I am providing here clock, this is positive edge trigger. This is positive edge triggered clock, positive edge triggered clock. So suppose first clock I have provided. So here, here and here. So simultaneously same clock is provided to all the flip-flop. Suppose I have provided first clock at this time. Suppose this is time number 1, I can say. So you have provided clock. So same clock is goes to here and same clock is goes to here. Suppose. Okay, so everything is operating. So now when you have provided clock here, so according to this you will get here output, and after this delay you will get input here. So when you are going to apply second clock in this time, so when we are going to apply second clock, so before going to apply second clock, this input should be present, this input should be present, this input should be present. Okay, so what I can say, this delay and this delay, this delay and this delay should be more than, should be not more than this time period. So what we can say, propagation delay of this and propagation delay of this. Similarly you can see here, first clock you have provided suppose here, and second clock if you are providing here. So again you can say this propagation delay and this propagation delay. Okay, so you can say for this path, this propagation delay cannot be more than this time period. This is a clock time period. Can I say this is your T clock? So T clock should be definitely more than the path delay. What we can say, this T clock time period should be more than the path delay. Which path? So this is sender and this is receiver, and for this is sender, this is receiver. So here the important thing, first you have to find out how many number of path, how many number of sender then receiver, how many number of sender and receiver. So here two path. So for path number 1, if I am saying for path number 1, can I say for path number 1 this will be sender? Okay, just I am saying sir, this is flip-flop number 1, this is flip-flop number 2, and this is flip-flop number 3. So what is path number 1? So flip-flop 1 2, flip-flop 1 2, flip-flop 2. So this is sender, so here this is sender and this is receiver, this is receiver. Similarly, what is the path number 2? So here path number 2. So for path number 2, again you can say, sir, this will be sender, this will be receiver. So here this is flip-flop number 2 to flip-flop number 1, and you can say this is sender and this is receiver, this is receiver. So first you have to find out in any circuit, okay, how many number of flip-flop are connected synchronously, then how many number of path you are getting. So here you can say this can be sender and this will be receiver, this will be the first path. Now this will be sender, this will be receiver, this will be the second path. You cannot say, sir, this will be sender, this will be receiver. No, because these two are not connected, this output is not goes to here. Okay, so here only two paths we have. So this is the first path and this is second path. Suppose if this output is connected to here inputs, then only we have three paths. So first, what is the first task? We have to find out number of path, and then what is our target? T clock should be more than, T clock should be more than the path delay. So what is here basic target? So T clock should be more than, this is a T clock should be more than or is equal to path delay. Can I say this is more than or is equal to path delay? This is a basic, this is a very basic formula. But now in GATE exam, here setup time and hold time, this two thing is also included. So how we can handle this setup time and hold time? So now I want to tell you here, how we can handle this setup time and hold time. Now how we can handle this setup time and hold time? How we can handle this setup time and hold time? So first you should know, sir, what is setup time and what is hold time. So in general, we represent clock in this manner, but this is not a actual clock. This is not a, none of the thing can change from 0 to 1, okay, in very sharp way. So in general, always we represent in this way, this is a positive edge triggered clock, but we consider some window here. So what window I will consider? So suppose here this window and this window, suppose I am going to consider. So what this concept are saying, in this window data cannot be changed. In this window, this input data of this any flip flop. So when you are applying clock to any when you are applying clock to any flip-flop, in between this window data cannot be modified. You can assume this is a one train, suppose, and this is a starting time. So before starting time, okay, you can say before that time, before this time, okay, before this time none of the passenger can be board in the train. Similarly for some time that should be on the hold. Okay, so we can say when you are applying the clock in this time, so before this time and after this time, okay, the input data of that flip-flop cannot be modified, then not be modified. So in between this time, here this data cannot be modified, here this data cannot be modified, here this data cannot be modified. So before time is called setup time and after time is called hold time. So we can say this time is actually, this time is the setup time, this time is, I can say, t setup, and this time we can say this is the hold time, t hold. You can say this is a hold time. Okay, so this basic only, if you remember, when you are applying the clock, okay, before applying when you are applying the clock, so just before some time and after them some time, that is a one kind of window, and in this window, or in this time frame, you can say your input data of the flip-flop cannot be changed, and before time is called setup time and after time is hold time. So now come to the point, you are applying first clock at this time and now you are applying second clock at this time. Okay, so suppose you have applied first clock, now after some time you are getting data and you are getting here data, but this data should be reached to here before. Suppose here we have hold time and setup time window, this time frame, suppose we have here this time frame. So what you can say, this is time from here to here. Now, so what you can say, before this time, so before this time this data should reach here, so what I can say, sir, from here to here, this and plus this time, this complete time, okay, can you relate with t clock, or you can say from here to here, this time should be more than propagation delay of this circuit, or you can say propagation delay of the circuit should be less than or is equal to from this to this time. So what you can say here, path delay. So from here now you can say, sir, path delay should be less than or is equal to, this is total t clock minus this setup time you have removed. Now the time frame is less here, so you can write total path delay should be less than or is equal to, can I write, this is t clock minus of t setup time. And now you can also say here, sir, t clock should be greater than or is equal to path delay. Can I write path delay plus setup time, t setup? This formula should be remembered to you. Clock time period should be greater than or is equal to total path delay plus setup time, this is very important thing. Okay, this is very important thing. Okay, this is very important thing. So I hope this first basic concept is clear to all of you. I hope this basic concept is clear to all of you. So just remember, just you have to remember, in between two flip flop, first you have to find out total path delay and which path, this is the data path. So now I can also write this t clock should be greater than or is equal to data path delay, okay, plus setup time, or I can say t setup. This is very important formula. This is very important formula. Okay, this is very important formula. Okay, I hope this thing definitely should be clear to all of you. Okay, so everyone, if anyone want, just you can note down this. Okay, just I am going to take 2-3 minutes of break. Okay, and so that we can continue. If anybody want, you can note down this. Okay, and if anybody have any doubt, okay, just ask me, Okay, ready? So I hope this thing is clear to all of you. Yeah, Akhil sir, will you discuss signal and communication also in this banner, or only important topic? Okay, that will depend, but tomorrow I will decide. Okay, tomorrow I will okay, tomorrow I will decide that part exactly. Okay, how much session we have? Okay, according to that. Now come to the point. So here, what is the first important thing? You should know when you are applying a clock. So one time frame window is required, and that window is set up time and hold the time. Okay, now from here we can say this T clock should be greater than or is equal to, okay, data path delay. Suppose if we have more than one path, so for every path you have to find out. So just this formula should be remembered to you. This formula should be remembered to you. So first you have to find out number of path. First you have to find out number of path. Then you can apply this T clock. Suppose if we have two path, three path, four path. So for every path we have to write here T clock, T clock, T clock. Then which T clock we have to consider, this I will discuss. But before going to discuss that part, what will be included in this data path delay? This is very important thing. Sir, what will be included in this data path delay? So I hope this thing is clear to all of you. Now come to the point. Now come to the point. Can I remove this? Okay, now. So, sir, what will be come into this data path delay? So when you are applying a clock, when you are applying this clock, then after that you can see in between this clock if there are any delay or not. If there are any delay or not. If here there are no delay. If there are no delay. Okay. Now you can see if any delay are in this path or not. Definitely this is a flip-flop. So definitely there will be some propagation delay of flip-flop. So if I am going to write for this path 1, if I am going to write for this path 1, I want to calculate data path delay. So here if I want to calculate data path delay of path 1. So what will be included? So you can see this red line. If there are any delay in this or if there are any delay in this, so this is 0. Here delay is, so can I write propagation delay of this is flip-flop number 1. Can I write? Yes. Now we can write this is a logic gate, and I can say logic gate number 1 plus propagation delay of logic gate number 1, propagation delay of logic gate number 1, or anything extra present in the path. So this thing you should remember. Now here I am writing propagation delay. It means this is always maximum delay. If sometime examiner will provide you here for this flip-flop maximum delay of this flip-flop, and maximum delay is called propagation delay. Okay, and suppose if examiner are providing minimum delay of the flip-flop, suppose this thing if the examiner have provided, suppose, and that is called contamination delay, and we can say, sir, this is the minimum delay. So if examiner will provide minimum delay and maximum delay, sir, then which delay I have to consider? So remember, always you have to consider here maximum delay. And suppose we have here logic gate, and suppose there are so many combination of logic gate, and suppose for example this kind of connection is given. Suppose this kind of connection is given like this. So there are two paths. One path is this and this is second path. So definitely which delay I have to consider, maximum path delay or minimum path delay. So this is the important thing. So here everything is maximum. Okay, remember, if examiner will provide you, but according to me examiner will not provide you maximum minimum. But suppose if they are providing, so you have to consider this path, okay, delay, this maximum delay, this maximum delay. This is a delay of path 1. Okay, delay of path 1. Clear this point? Now if you want to write here, sir, what will be the T clock for this circuit? Sir, what will be the this T clock for this circuit? Or you can say, sir, how much maximum frequency we can provide here? Suppose if you want to find out here, so now first for path 1 you have to find out total path delay. Similarly, if I want to write for the path 2, if I want to write for the path 2, so for path 2, this is sender and this is receiver. This is sender and this is receiver. So path 2 means your sender is a flip-flop number 2 and receiver is your flip-flop number 3. Sender is flip-flop number 2 and receiver is flip-flop number 3. So what is your data path delay? What is your data path delay? What is your data path delay? So data path delay is here, data path delay is here. So now you are providing clock here. So again if any logic gate are present in this path, then this path delay and then this path delay. Okay, so here no logic gate are present, then you have to write here propagation delay maximum. You can write propagation delay of sender flip-flop number 2, and then this is suppose logic gate number 2, then plus propagation delay of this is logic gate number 2, logic gate number 2, and both the value you have to consider maximum. Okay, so first how you can find out data path delay. Okay, so data path delay you have to consider maximum value if examiner will provide maximum and minimum. I hope this thing is clear to you. Now here different T clock, this value will satisfy this condition and this condition. So first you have to find out T clock, what will be the T clock for first path and what will be the T clock for the second path. So here just I am going to write the equation. So just I am going to write the equation T clock. So T clock 1. So for this situation I am writing for path 1 T clock 1 should be greater than or is equal to total data path delay. Just you to write propagation delay of sender flip flop, propagation delay of, and for here sender flip flop is flip flop number 1 plus propagation delay of this logic gate, propagation delay of logic gate number 1 plus setup time. You can see this formula. So 3 delay you have to consider, all the data path delay, and here this is setup time, and in last this is setup time. So propagation delay of flip flop number 1, propagation delay of logic gate number 1 plus this is setup time. But for setup time, which if all the flip flop having different setup time, then setup time of this receiver flip flop. So you can write here setup time of flip flop number 2. This is important thing. So propagation delay of this flip flop number 1, propagation delay of this logic gate number 1, but setup time of receiver flip flop. This is important thing. So this is a first condition. This is a first condition. This is a first condition. Okay, now the second condition you have to again write from the path 2. Okay, from the path 2. So from the path 2, what is a T clock 2? So you can write for the second path. So T clock 2 should be greater than or is equal to, again data path, this is sender and this is receiver. So first this propagation delay of flip flop number 2 plus propagation delay of logic gate, propagation delay of logic gate number 2 plus setup time of 3 plus setup time of flip flop number 3. Okay, so just you have to find out. So two number of T clock we will find out. So which T clock will satisfy the condition? Suppose for example if T clock 1, here we are getting suppose 20 nanosecond, suppose for example, and here we are getting suppose T clock 2, we are getting here this is suppose 30 nanosecond. Okay, so which T clock you have to consider? If you will consider 30 nanoseconds, so definitely this condition will also satisfy. Here T clock 1 should be greater than 20. It can be greater than, but it cannot be less than. So if you will consider 20 nanosecond, then this condition will not satisfy. But if you will consider here this T clock 2, that will be satisfied. So which T clock you have to consider? So here I can write, so T clock, okay, will be is equal to maximum from this T clock 1 and T clock 2. So first you have to find out which T clock will satisfy the whole circuit. So for all the path, first you have to find out T clock 1, T clock 2. Don't find out frequency. First you have to find out T clock. So what will be the answer here for the complete circuit? So T clock should be greater than R is equal to 30 nanosecond. This will be the answer. So what will be the frequency? So here you can write, sir, F clock should be less than R is equal to 1 upon 30 nanosecond. So you can write this is nothing but 1000 by 30 megahertz. So this you can write 100 by 3. This is 33.33. So here F clock should be less than R is equal to 33.33 megahertz. This is the answer. What will be the F clock maximum you can provide in this circuit? So maximum frequency you can provide here. This is nothing but less than R is equal to, sorry, F clock maximum is nothing but 33.33 megahertz. This will be the answer. So examiners are interested in here. This F clock is equal to 33.33 megahertz. So now if suppose for example, here if you will apply here 30 megahertz, then circuit will operate or not. This is the maximum clock. Less than clock you can apply, but suppose if you will apply here more than 33.33, then what will happen? So if you will apply here frequency more than 33.33, then you will get here setup time violation. Here I can write if your F clock is greater than 33.33 megahertz, then what will happen? Then you will get here setup time violation. So we can say this situation is a setup time violation. Okay, so now examiner can ask you, they can provide you any value and they can ask you there are setup time violation or not. There are setup time violation or not. Examiner can ask you this thing. Examiner can ask you there are setup time violation or not. Okay, first you have to find out number of path. For each and every path you have to find out T clock. Okay, then maximum of T clock you have to consider, and from that you can find out circuit clock frequency and you can find out maximum clock frequency. Now I am going to consider one question. Okay, one question I am going to consider from this concept. Okay, now so one question I am going to consider from here. I hope this basic concept is clear to you. Setup time, whole time I will discuss. Wait for that. So first I want to discuss what is a maximum clock frequency, because mainly examiner are interested in setup time violation and examiner are interested in how much maximum clock frequency we can apply in the circuit. Okay, so mainly examiner are interested in here how much maximum clock frequency we can apply here. Okay, so now I am going to take one example and this answer you have to give me. Okay, and this answer you have to give me. So just tell me, are you ready? Are you ready for the question or not? Okay, are you ready for the question? If you will tell me yes sir, ready, then I will wait for your answer. If you will not tell me, then I will solve. Tell me, are you ready or not? Are you ready or not? So here suppose I am considering first flip flop. Here this is clock and one more flip flop I am considering. Suppose two flip flop I am considering here. Okay, now suppose this is your T0, this is Q0, this is Q0 bar. Okay, now this is T1, this is Q1, this is Q1 bar. Suppose for example, and both are connected synchronously. Okay, so this is a synchronous counter. And now here suppose suppose here we have one input like this. Okay, now suppose here some logic gate are given. Just I am saying this is a logic gate and this delay of this logic gate, suppose I am going to assume this delay is suppose 5 nanosecond. This is 5 nanosecond. So delay of this logic gate is 5 nanosecond. Okay, now again if this output is connected with, again suppose I am considering delay of this is suppose 3 nanosecond, and now this is connected with this input. Okay, now this flip flop propagation delay is given. Propagation delay of this flip flop is suppose is this 10 nanosecond, and this setup time is suppose given 3 nanosecond. Okay, so this flip flop propagation delay and setup time is given. Similarly, propagation delay of this flip-flop is suppose 7 nanosecond and setup time is given, suppose here 2 nanosecond. Suppose this thing is given. Now one more path I am going to consider here. Suppose this output, again here one logic gate, and this is connected to this input, and suppose this propagation delay is 4 nanosecond, and this is your clock. All the propagation delay are maximum. So first question, in any question, first you have to find out number of path. So first you have to find out, sir, how many number of paths? First tell me how many number of path in this question, means how many sender receiver, and sender receiver. Suppose if I am saying this is flip flop number 1, and this is flip flop number 2. So first tell me how many number of path. Okay, slowly we will solve. But first tell me how many number of path. I am waiting for your answer. How many number of path here? How many number of paths here? Okay, this is the most important thing. How many number of paths here? Tell me. I am waiting for your answer. How many number of paths here? 2. No, here most of the student can do mistakes. So here you can see, sir, this is sender, this is receiver, path number 1. So I can say, sir, path number 1. Your sender is a flip-flop number 1, and the receiver is flip-flop number 2. This is a path number 1. Now second path. Now path number 2 we have, this is sender because this is connected to here. So path number 2, this is flip-flop number 2 to flip-flop number 1. Now one more path we have. This is path number 3. This is sender and this is again receiver. Sometimes same flip-flop can be sender, and again output of same flip-flop will again connected to the input of flip-flop. So sender flip-flop and receiver flip-flop, same flip-flop can also be possible. So here path number 3. So here sender is flip-flop number 2 and receiver is again flip-flop number 2. So same flip-flop can be sometimes sender and that can be receiver. This is very crucial and very important thing. Clear thing. So first the important thing is how many number of path. Okay, so now you can find out. First solve for the path number 1. So in GATE exam this kind of question easily you can handle in 1 minute. In 1 minute you can handle. So first you can go with path number 1. So for path number 1 you know, so you can write, sir, here T clock 1 you can write should be greater than or is equal to path 1. This is sender, this is receiver. So here what is delay of here? This is 10 nanoseconds. So can I write directly, sir, this is 10 nanosecond plus what is the delay here? Sir, this is 5 nanosecond plus so what is setup time of this? Setup time of this is 2 nanosecond. So first for T clock 1 should be greater than or equal to 17 nanosecond. This is for path 1. Only this is a very basic thing. This propagation delay, this setup time for path 1. Now for path 2. For path 2, T clock 2 should be greater than or equal to. Which one is path 2? Sir, this is sender and sir, this one is receiver. So this sender flip-flop propagation delay, sir, this is 7 nanosecond plus now propagation delay of this logic gate, this is 3 nanosecond plus sir setup time of this setup time of 3 nanosecond. So what will be the answer? Sir, T clock 2 should be greater than or equal to 7 plus 3, 10 plus 3, 13 nanosecond. So which is more? Clock path 1 definitely T clock or delay is more. So definitely you have to consider here 17 nanosecond. But again you have to check for the path 3. So for path 3, what you can write? So T clock 3 should be greater than or is equal to. So this is path 3. This is sender and this is receiver. So you can start from here. If you have provided first clock here and second clock, again you have to provide here. So when you have provided first clock here, propagation delay of this is 7 nanosecond plus now you can see this logic gate delay is 4 nanosecond. So here 4 nanosecond plus now setup time of again this flip flop. This is 2 nanosecond. This is 2 nanosecond. So t clock 3 should be greater than or equal to 7 plus 4, that is 11 plus 2, 13 nanosecond. 13 nanosecond. So now you are getting thin situation, thin condition. So first you have to find out number of path, then you have to find out t clock 1 for path 1, then path 2, then for path 3. Then what will be the t clock you have to consider? So for whole circuit, t clock should be greater than or is equal to 17 nanosecond. This should be answer. This should be answer. Then you can write, sir, f clock for this circuit. F clock for this circuit should be less than or is equal to 1 by 17 nano, or you can write, sir, 1000 by 17 megahertz. Okay, so what will be, sir, f clock maximum? So maximum clock frequency you can provide here 1000 by 17 megahertz. This is the answer. So examiners are mainly interested in this. Suppose if you will apply more than this frequency, then here setup time violation. So examiner can also ask, is there setup time violation or not? But for that they will provide frequency. Clear this point? But mainly examiner are interested in maximum clock frequency. So according to me, only this category of question will be asked. First you have to find out number of paths. This is the important thing. Same flip-flop can be sender and same flip-flop can be receiver. This situation can also be possible. So this is a best question to learn this setup time. Okay, so I hope now you are comfortable in this setup time. I hope now you are comfortable in this setup time. So please just confirm me. Just confirm me. So please just confirm me. This thing is clear to you or not? This thing is clear to you or not? This thing is clear to you or not? Okay, crystal clear. Now sir, if hold time, okay, according to me examiner will not target hold time, but you should know. And one more important thing here, this all the delay you have to consider. Okay, setup time cannot be maximum or minimum. This delay always you have to consider maximum. This delay will be maximum and this delay will be maximum if they will provide maximum and minimum. Now sir, what is a hold time? Hold time, from hold time only you have to check in the circuit there are hold time violation or not. Only you have to check that thing. There are hold time violation or not. In the circuit, hold time violation or not. Only this thing you have to check. Okay, so examiner can only ask hold time violation is happening or hold time violation is not happening. That's why generally from the hold time examiner will not ask you the question. But suppose if from hold time they are targeting the question, I hope this thing is clear to all of you. Okay, this is very easy a topic. If you can handle in efficient way, so this topic will be very easier. Okay, I have studied approximate 6 months to this topic. How much? 6 months. Then I become expert in this part. Okay, but now you can be expert in this topic within a 15 minutes, 20 minutes or half an hour. But there are so many things we can discuss here, but in GATE exam, examiner will not target. Okay, now here, suppose if examiner are interested in hold time. So already we have studied, sir, if we are providing here clock, so this window is a setup time plus hold time, and this time is practically hold time. This time is hold time. So suppose when you receive here input, that input should be constant for hold time. That input should be constant for hold time. So suppose for example, if you have applied first clock, suppose if I will assume this propagation delay is 0, suppose for example, and this propagation delay is 0, suppose for example, if this propagation delay and if this propagation delay is 0, suppose. Okay, and if you have applied first clock, suppose if you have applied first clock, so immediately you will get this output. Immediately you will get here output immediately. Suppose here just I am going to draw one clock. Here I am going to draw one clock. Suppose this first clock you have applied here, and this is second clock. So first clock we have applied here and here. Suppose for example, so first clock we have applied. So here we have applied the first clock. Okay, now okay, this first clock both the place. So here we have applied and here we have applied. Now here suppose input was present and here input was present. So when you have applied both the clock, okay, if this delay is 0 and if this delay is 0, immediately this you will reach at output. But according to hold time, here this input was constant till the hold time. It means for this time, for this hold time, for this hold time, this input from here, this input cannot be come to here. It means what I want to say, this whole time delay, this whole time delay should be less than of this delay. So what I can say, here and here delay cannot be 0. This delay and this delay cannot be 0. Sometime we have to put here extra delay. So this delay plus this delay cannot be less than hold time. So if I have provided here clock, so this input will goes to the output, but according to this hold time, suppose for this interval, this input should not be changed. So what I can say, and same time you have applied here one clock. So this delay and this delay, if suppose this delay and this delay is less than this delay, then this input will be modified. But what we are saying, in this frame, this input data cannot be modified. So sometime we have to put here extra delay to remove hold time violation. So just one formula you should remember for hold time. If you want to check hold time, so for the receiver, if you have sender and you have receiver, so what you have to check here? So if you have, suppose this is sender flip-flop, one is the sender flip-flop and one is the receiver flip-flop, so receiver flip-flop hold time, should be less than, so this receiver flip-flop hold time should be less than or is equal to this propagation delay of this sender flip-flop. So can I write this hold time, or you can say this propagation delay plus this propagation delay should be more than hold time of this flip-flop. So this hold time should be less than, or this delay plus this delay will be more than hold time. So you remember this formula, propagation delay of sender, propagation delay of this sender flip-flop, propagation delay of sender flip-flop plus propagation delay of logic gate. Or you can also write the same thing, propagation delay of data path. So you can say propagation delay of data path should be greater than or is equal to hold time of receiver flip-flop, This is very important thing. Now one more important thing, sir, this propagation delay of data path, what I have to consider, minimum or maximum? Suppose if we have here logic gate, and the logic gate, suppose if you are receiving here input and here suppose you are getting output at 1 second, at 1 millisecond, and again this is going to be change. Suppose some time output can be changed because some time your in logic gate circuit you will get 2 or 3 paths. Already I will explain you. Suppose for example, if we have one logic gate and if you have one path, so when you will receive this input, one output will be changed, but after this delay and this delay, the final output you will get. But what we need here, this input cannot be changed for this interval. So for this interval, here input cannot be changed. It means this minimum delay should be greater than this whole time. This is very important thing. So second formula you remember, you can remember propagation delay of data path. This is a minimum, and this should be greater than hold time of receiver flip-flop. So two formula you should remember. T clock should be greater than propagation delay of data path, that is maximum, plus setup time, and here the second formula, propagation delay of data path, that is minimum, that should be greater than or is equal to hold time, but hold time of the receiver flip-flop, okay. Now I am providing you here some value and you have to tell me, is there any hold time violation or not, and which hold time is violating, hold time 1 or hold time 2 or hold time 3, for which path. So for which path hold time violation is going to be happen. I hope this thing is clear to all of you. So just you should remember here two formulae, okay, only you should remember. So first, T clock should be greater than data path delay, that is maximum, plus setup time of receiver, similarly here propagation delay of data path, okay, and that is minimum, should be greater than a hold time of the receiver. Hold time of the receiver flip flop. Okay, so your setup time is for receiver, and again here hold time is for the receiver. Clear this point? Clear this point? So now in this question we have to change some value. We have considered this is propagation delay, and practically this is not propagation delay. We can call this a contamination delay. But in GATE exam, maybe examiner will not use contamination delay. They can use maximum delay or minimum delay. Okay, so you should remember sometime they can use contamination delay. So contamination delay is minimum delay. Suppose I am considering this is maximum delay. In the same question, suppose here contamination delay I am going to write. Suppose this is 3 nanoseconds. Suppose this is 3 nanoseconds for this. Okay, and for every logic gate I am saying this is minimum. Here contamination delay I am assuming 1 nanosecond. Here contamination delay, suppose this is 2 nanosecond. Here contamination delay, suppose this is 2 nanosecond. And now here contamination delay, just I am writing here contamination delay, suppose this is 2 nanosecond. Okay, so every this flip flop maximum, this is minimum, this is maximum, this is minimum, this is maximum, this is minimum, maximum, minimum, this is maximum, and this is minimum. Okay, so now if I will ask you for path 1, so what should be the minimum, sorry, what should be the th value, so now for path 1, can I write again here? So now for path 1, okay, so what should be the value of th, what should be the value of th 2, and what will be the value of th1. So for path 1, first if we are going to find out, so your contamination delay of data path, so from this minimum delay is 3 nanosecond. So you can write here, so th should be less than or is equal to, or you can also write, first you can write delay, sir, this is 3 nanosecond plus this minimum delay, this is 1 nanosecond, and this value should be greater than or is equal to this hold time. So I can write this is hold time, this is a th2 means this is a hold time of flip flop number 2. So th2 should be less than or is equal to 4 nanosecond. So from here you are getting th2 should be less than or is equal to 4 nanosecond. So suppose if examiner will provide you th2 greater than 4 nanosecond, it means there are violation. Okay, so th2 should be less than or equal to 4 nanosecond. Now come to the path number 2. Path number 2, this is sender and this is receiver. So this is sender, so contamination delay is here 2 nanosecond plus here this contamination delay is 2 nanosecond, and this should be greater than or equal to whole time of this. So this should be th1, whole time of this. So from here, so th1 should be less than or equal to 2 plus 2, 4 nanoseconds. So in the both the case you are getting, but now again you have one more path. So for third path again you have to check. So here this is a sender, so here this contamination delay is 2 nanosecond, and here again this is 2 nanosecond, again this is 2 nanosecond, so this is 2 nanosecond, so this is 2 nanosecond, this is 2 nanosecond minimum, and this should be greater than or equal to again whole time of this, so again this is 2, so ts2, again you can say, so ts2 should be less than or is equal to 4 nanoseconds. So here this flip flop and this flip flop hold time should be less than or is equal to 4 nanosecond. If suppose for this or for this hold time is more than 4 nanosecond, circuit will not work. Circuit will not work. Circuit will not work. This is the important thing. Circuit will not work. Circuit will not work. So hold time only way to check in the circuit hold time violation or not. If in the circuit hold time violation, then what we can do? Suppose for example, if this ts2 is given 5 nanosecond, then what we can do? Then this delay you have to increase. How you can increase? Then I can put here one extra gate. So in general, in practical and in real life, in between two flip flop in synchronous circuitry, in real life we will use synchronous circuit. Why? Because here f clock maximum is independent of the number of flip flop. Okay, and in asynchronous circuit, your maximum clock frequency is inversely proportional to number of flip flop. So when you will increase number of flip flop, your clock frequency will go decrease, maximum clock frequency in asynchronous circuit. But in synchronous circuit, only you have to consider in between two flip-flops. So that's why in the real world, always we use synchronous counter circuit. We don't use asynchronous circuit. Clear this point? And now here the second important thing. Okay, if you will get hold time violation, so just here to put here one extra logic gate. So in real world, generally in between two flip-flop, we will get any logic gate in between that path. Okay. Okay, in most of the time you will get. So I hope this thing is clear to all of you. Okay, so Mr. Akhil, Mr. Naxas, please just comment me this thing is clear to you or not. This thing is clear to you or not. Okay, now I am providing you here, just I am going to change the value, just I am going to change the value in the same question, or if I am going to provide you one question and that answer you have to provide me. Okay, so just I am going to remove this, and one question I am going to provide you, one question I am going to provide you. Okay, and that answer you have to give me. Okay, now that answer you have to give me. What will be the maximum clock frequency, and is there any hold time violation or not? So suppose I am assuming here we have one flip flop. Okay, now, and suppose this is clock. Suppose here this is clock. Only one flip flop I have considered. Okay, and suppose only one flip flop. Suppose this is T, and here this is Q and this is Q bar. Okay, now this output is connected with one logic gate in this way. Okay, now this propagation delay is 5 nanosecond. This contamination delay is 2 nanosecond. This propagation delay is 10 nanosecond. This contamination delay is 3 nanosecond. Only one flip flop. So this is sender and this is receiver. Now tell me, I am waiting for your answer. Is there any hold time? And suppose I am assuming here, sir, hold time is equal to 3 nanosecond. Okay, and here setup time also, this setup time is 4 nanosecond. Is there any hold time violation or not? What is the maximum clock frequency? I am waiting for your answer. I am waiting for your answer. Okay, you have to solve this question. You have to solve this question. Okay, no hold time violation. Okay, what is a maximum clock frequency in this case? What is a maximum clock frequency in this case? What is the maximum clock frequency? The whole time easily you can check. This is very simple question, only one path. This is sender, this is receiver. So here only path number one, only total path one. Which path? Sir, flip flop one is sender and flip flop one is receiver. So here sender and receiver both are same. Here sender and receiver both are same. So what you can say first, if you want to check hold time, suppose hold time. So you can see, sir, this minimum delay 3 nanosecond plus this minimum delay is 2 nanosecond, and this should be greater than or is equal to this hold time, and hold time is this is th, and this th is 3 nanosecond. So there are hold time violation or not. So in every circuit, first we have to check hold time violation or not. Don't calculate first maximum clock frequency. Is there any hold time violation or not? So here no hold time violation. No hold time violation. Can you say now? Now come to the next point. Sir, what will be the T clock? So T clock, and this is only one is given, and this should be greater than or equal to, this is sender and this is receiver. So propagation delay of this is 10 nanosecond plus propagation delay of this is sir 5 nanosecond plus setup time of this, setup time is 4 nanosecond. 4 nanosecond. So 10 plus 5, 15 plus 4, 20 nanosecond. So T clock, and 1 is the T clock is greater than or equal to 20 nanosecond. So what will be the F clock? F clock should be less than or equal to 1 upon 20 nano. So 1000 by 20 mega. 1000 by 20 is nothing but 50 megahertz. So maximum clock frequency, F clock max is here 50 megahertz. This is 50 megahertz. This is the answer. This is 50 megahertz. This is the answer. 50 megahertz. Why you are getting 19 nanosecond? Why 19? Okay, 50. Okay. This is 19. Okay, you can change this 5 nanosecond. Okay, you can change this 5 nanosecond. Just I can change 5 nanosecond. Okay, that's what 19, 10 plus 15 plus 4. I can change this 5. Okay, so this will be 10 plus 5 plus 5. Now answer is correct. Easily we can handle. Now I am going to take two questions from this topic. Okay, then we will start ADC and DAC, and after that we will start ADC and DAC. Clear this thing? Okay, now. So always first you do check in the circuit, sir, there are hold time violation, yes or no. Okay, if there are any hold time violation, then what we can do? Suppose for example, if in this circuit hold time is given, suppose 7 nanosecond, then definitely this 3 plus 2 5 hold time violation. Then what we can do? If there are hold time violation, then what we can do? Then we can add here one extra delay. So if this is so 3 plus 2 5, but this 7 required, so you have to use add here 2 nanosecond. So if suppose in gate exam, suppose for example, if in the any circuit you are getting hold time violation and examiner asking, sir, what is T clock? So you cannot write the answer. Okay, you cannot calculate this will be wrong. If hold time violation, then you cannot calculate the frequency. So what you can do, if in hold time violation in the circuit, you can add extra delay in the circuit. So here I will add 2 nanosecond, then this answer will be again remodified. So this answer will be 10 plus 5 plus 5 plus 2 here to add. So here this will be 22. So 1 upon 22 will be the answer. So if you will add extra delay in the path, this maximum clock frequency will be lesser than that. So you have to concentrate on this point. Hold time violation in the circuit, yes or no? Because till now, examiner in gate exam, they have not targeted hold time. But according to me, they can target the hold time. Because very few people are comfortable in hold time violation. Okay, now I am going to take two problem from this topic. Okay, now, and both answer you have to first provide me. Again, both answer you have to provide me first. Okay, now. Definitely this will give you bonus mark in gate exam. Okay, and according to me, this year gate 2022, definitely you will get question from here. Okay, so just note down first problem. Okay, Yeah, using buffer. Okay, you can add some buffer. Delay how we can provide? By using buffer. Okay, now so this is a gate 2004. This problem is from gate 2004. Now you will ask me, sir, in gate 2004 they have already asked question from here. Yes, in 2004 already question has been asked from here. Just I want to give you, suppose this is a one flip flop. Okay, I have changed in the gate exam, they have mentioned SR flip flop and SR value 1 1, that was mistakes. So here Z and K is given, or if you want to write sir here S and R, so I will not provide here input. Okay, this is SR, input can be anything. Now again one more flip flop, again this is set reset flip flop. Okay, this one the second, and now this output is connected with this clock. This is Q and this is Q bar. Okay, and here okay, now and now again here one AND gate, and this output flip flop. Okay, this Q bar, this is Q, and this Q bar is connected to this AND gate. Okay, now and the second input of the AND gate is from here, this Q bar. Okay, I can write this is Q bar. Okay, so both of the output is connected with the AND gate. And now here again one more SR flip flop. This is S and R. Okay, this is SR flip flop. And now this output is connected to the this output is connected to here, this S. Okay, and now here one clock is given. One clock is given. Just I am considering here clock, and this clock is connected to this last flip flop, this last flip flop, and this first flip flop. So first and last was synchronously connected, and this are connected asynchronously. This is a mixed question, synchronous plus asynchronous. Okay, synchronous plus asynchronous, and here they have provided setup time of all the flip flop to T setup. All the flip flop setup time is same. So setup time is 5 nanosecond. All the flip flop setup time is 5 nanosecond. And worst case delay means propagation delay of flip flop. All the flip flop propagation delay is given, that is 15 nanosecond. And gate delay and gate delay is given, and gate delay is also given, and this delay is given 5 nanosecond. 5 nanosecond. Okay, so here you can say, so this is Q and this is Q bar. This is the final output. Okay, this circuit is given, and here maximum clock frequency you have to calculate is equal to question 1, means you have to calculate f clock max. So maximum clock frequency you have to calculate. 4 options I am going to provide you. First option 21 megahertz. Okay, second option is given here. 2 megahertz, and third option is given here 25 megahertz, and last option is given here 30 megahertz. Okay, 30 megahertz. Anybody can provide me answer of this question. Anybody can provide me answer of this question. So easily you can handle. Well, you can see which one is sender, which one is receiver. Suppose I am saying this is flip flop number 1. Okay, and this is suppose flip flop number 2, and suppose this is flip flop number 3. First you have to find out number of paths. What is your first target? Number of paths. What is your first target? Number of paths. How many sender and how many receiver? These two are connected asynchronous. So you don't have to consider asynchronous. You have to consider here this is S and here this is R. Okay, so these are the inputs. Anything we can assume here now. So here which one is sender, which one is receiver? So you have to concentrate on synchronously connected. So this is sender and this is receiver. This is very important thing. So here only the important thing is which one is sender and which one is receiver. You cannot say sir this is sender, this is receiver, because this is asynchronously connected. You have to apply clock here. So first clock you have to apply, second clock you have to apply. So we have to check in between two clocks. So we have to check between sender and receiver. So number of path is here only 1. So here sender and receiver, this is sender and this is receiver flip flop. So sender flip flop is flip flop number 1 and the receiver is flip flop number 3. This is very important thing. So sender is flip flop number 1 and receiver is flip flop number 3, and they are asking maximum clock frequency. What will be the answer? I am waiting for your answer. Tell me. Okay, I am waiting for your answer. Just tell me Which can be the correct answer here? Which can be the correct answer here? This is very good level of question. This is very good level of question. So in between sender and receiver, now I can say, sir, asynchronous flip-flop can also be connected, or logic gate can also be connected. So in between sender and receiver, sir, what can be possible? Anything can be possible, either logic gate or either flip-flop is also possible, but that should be connected asynchronously. That should be connected asynchronously. That should be connected asynchronously. Okay, so how you can say here? How you can say here? Okay, that should be connected asynchronously. That should be connected asynchronously. Now tell me, that should be connected asynchronously. Okay, so here can I say, sir, T clock, only here one pass, so I can write T clock should be greater than or is equal to. So you have applied clock here, so you can see, is there any delay in this path? No delay. Then delay of this. So what is the delay of here? What is the delay of this path? So propagation delay of this flip flop is given 15 nanosecond. So can I write this delay is 15 nanosecond? Then this is going to the next. Then this is going to the next clock. Then again this output you will get after this delay. You will get after this delay. So what is this delay? So delay up again flip flop, sir, this is again 15 nanosecond. 15, then you will get this output, but this output you will get, at 15 nanosecond. So this is available at 15 nanosecond, but here this is 15 and this is 15, so this second will be available at 13 nanosecond. So this output, 2 times this output will change. When this is receiving at 50, then at after this delay you will get here. And what is the delay of this AND gate is given 5. So this, because of this 15 you will get at 20 nanosecond, but because of this 30 you will get at 35 nanosecond. So this input will be received at 35 nanosecond. So in receiver flip flop, input you are receiving at 35 nanosecond. So what we can say here? So T clock should be greater than or is equal to, can I write propagation delay of flip flop 1, propagation delay of flip flop number 1 plus, then this will move to propagation delay of, sir, this is propagation delay of flip flop 2, propagation delay of flip flop 2, okay, flip flop 2 plus, sir, propagation delay of AND gate, propagation delay of AND gate, can I write plus, setup time of flip flop 3 plus setup time of flip flop number 3, setup time of flip flop number 3. Can I say this thing? Setup time of flip flop number 3. So from here you can say, sir, T clock should be greater than or is equal to, this is 15 nanosecond, and this is a propagation delay of flip flop number 2, 15 nanosecond plus propagation delay of AND gate, this is 5 nanosecond plus setup time of flip flop number 3, 5 nanosecond. So T clock should be greater than or equal to 30 plus 10, 40 nanosecond. So sir, what will be F clock? F clock should be less than or equal to 1000 by 40 megahertz. Can I say? So this will be cancelled out. So you are getting here 25 megahertz. So F clock maximum we will receive here 25 megahertz. This is a very good level of question. So from here one theory we can analysis. Sir, if this is a sender flip flop, and sir, if this is the receiver flip flop, so in between sender and receiver flip flop, what can be happen? So here anything can be possible in this path. So in this path, either logic gate can be possible or flip flop can also be possible, but this flip flop should be connected asynchronously. So in this path, either logic gate or flip flop can also be possible, but this should connected asynchronously. So this is sender, this is receiver. So you can say this is your block, this is your block. First you have to find out maximum delay of this. You can also do the same question in this way. If you are not comfortable in the question, so what you can do in this question, you can also solve this question in this way. Sir, this is sender flip flop and this is receiver flip flop. Okay, you can say this is sender, this is receiver, we are applying, this is the clock. Okay, this is your clock, and this propagation delay is 15 nanosecond, this is required, and this setup time is required, this setup time is 5 nanosecond, this is 5 nanosecond, sir, this is T setup, and this is propagation delay. Okay, in between this two path, first you have to find out maximum delay of this path. So from here to here, you have to find out maximum delay of this path. What is a maximum delay? So maximum delay up, you can say this is 15 and this is this plus 5, so 20 nanoseconds. So you can write so this maximum delay is 20 nanoseconds. Now you can also solve this question in this way. So from again you can write, so this t clock should be greater than or is equal to this 15 nanosecond plus this is 20 nanosecond plus this setup time 5 nanosecond. So this t clock should be greater than or is equal to 40 nanosecond. This is the way to handle any question. So first you have to simplify the circuit. If you are not getting comfortable in this circuit, so you can assume this circuit, you can treat this circuit in this way. So first you have to write one sender, second you have to write one receiver, and in between sender and receiver you have to find out what is a maximum path delay. So here, sir, what is the maximum path delay from here to here? So this plus this. If I will ask you, sir, minimum path delay, suppose for example, so you can see here, so this immediately you will get and after 5 nanosecond you will get. So minimum path delay of this circuit is 5 nanosecond. So from here directly you will get here this output. And if I will ask you maximum path delay, so you can tell me, sir, this is 20 nanosecond. Are you getting? So if you have any path, so in path there are so many delay can be possible, but we are generally interested in maximum path delay, or you can say this maximum path delay is called critical path delay. Okay, so this t clock is exactly called, this is a critical clock frequency, and this delay is totally, this delay is called critical path delay. So critical path or worst case delay or maximum delay, all the three things is the same. All the three things is same. Okay, so just confirm me. Okay, just confirm me. Okay, Mr. Nexus, please confirm me this problem is clear to you or not. Okay, now I am going to take one more problem from this topic, and that answer you have to provide me. Clear? And that answer you have to provide me. That answer you have to provide me. That answer you have to provide me. Okay, now that answer you have to provide me. Okay, just note down the problem. Here data I am going to change from the previous year. Suppose we have two number of flip-flop. Okay, suppose we have two number of flip-flop like this. Okay, we have two number of flip-flop. Here propagation delay of this flip-flop, suppose this is 5 nanosecond. Clear? And here setup time and hold time. Here setup time is also suppose 3 nanosecond, and here hold time of this is suppose 5 nanosecond. Okay, this thing is given. Same clock is provided to both the flip-flop. Same clock is provided to both the flip-flop. Again, if here propagation delay 6 nanosecond, here setup time I am going to assume 2 nanosecond, and here hold time I am going to assume 4 nanosecond. Okay, this I assume. Now output of this flip-flop, this flip-flop is connected with here, one XOR gate, and here suppose I am assuming one input, this is external input. Okay, and this input is again connected with here one NAND gate, and this output is connected to the input of this. This output is connected to input of this, and now this output is connected to input of this. This output is connected to input of this. This circuit is given. So what will be the maximum clock frequency? But first you have to check there are hold time violation or not. But always. But if examiner are interested in hold time, they will provide you minimum path delay. So here there are no any minimum delay they have provided, so you can leave. You don't check the hold time violation. But you have to first find out number of paths. How many number of paths? You can tell me, sir, this is a flip-flop number 1 and this is flip-flop number 2. So what is the first path? This is sender and this is receiver. The total path can I say 2. This sender, receiver, and this is sender and this is receiver. So first path is flip-flop number 1 to flip-flop number 2. So if this is 1, this is 2. So can I write here, sir, t clock 1 t clock 1 should be greater than or is equal to this t clock 1 should be greater than or is equal to, so this is sender, so this propagation delay, can I write 5 nanosecond? Directly can I write answer 5 nanosecond plus this delay, and this delay definitely examiner should also provide it. So here this delay is suppose 1 nanosecond and this delay is 1 nanosecond. So here this 5 nanosecond plus 1 nanosecond plus 1 nanosecond, and now setup time of this is 2 nanosecond. Can I write? So t clock 1 should be greater than or is equal to 5 plus 1 6 plus 1 7 plus 2 9 nanosecond. Can I write? So for the first path t clock should be greater than or is equal to 9 nanosecond. For the path number 2, when flip flop 2 is the sender and flip flop 1 is the receiver, flip flop 2 is the sender and flip flop 1 is the receiver. In this situation, this is the sender and this is receiver, so only here propagation delay 6 nanosecond. So t clock 2 should be greater than or is equal to this propagation delay 6 nanosecond plus this setup time is 3 nanosecond. So here you can say, okay, this value you can change, this setup time you can change 4 nanosecond. Okay, this setup time you can change here 4 nanosecond. So here this setup time is 4 nanosecond. So here t clock 2 is greater than or is equal to 10 nanosecond. So first path condition is t clock should be greater than 9 nanosecond. Second clock condition, t clock should be greater than 10 nanosecond. So which will be the t clock for the circuit? So t clock should be greater than or is equal to 10 nanosecond. So this condition will satisfy and this condition will also satisfy. What will be the f clock? So f clock should be less than or is equal to 1 by 10 nanosecond. So what will be the f clock? Sir, f clock should be less than or is equal to 1000 by 10 megahertz. So this is nothing but f clock maximum is equal to 100 megahertz. This is 100 megahertz. This is the answer, 100 megahertz. Now if I will ask you, sir, all the propagation delay maximum and minimum are same. Suppose for example, this is maximum and minimum same. Sir, this maximum minimum same. Sir, this maximum minimum same. Sir, this maximum minimum same. Then can you check hold time violation or not? So again you can check for the path 1. So if you want to check here hold time, so if you want to check here hold time violation, yes or no, so definitely you will not get, but how you can check? So for first path 1, so for path 1, so if you are considering this is 1, this is 2, so this propagation delay, data path delay, so this is 5 nanosecond plus this is 1 nanosecond and plus this is 1 nanosecond. So 5 plus 6 plus 7, and this should be greater than or is equal to hold time of this, and this hold time is 4 nanosecond. So this should be greater than our hold time. So this 5 plus 6 plus 7, so this is 7 nanosecond is greater than or is equal to 4 nanosecond. Yes, this condition is true. It means no hold time violation in this path. Now you can check path number 2. Now you can check path number 2. So for path number 2, this is sender and this is receiver. So this propagation delay is 6 nanosecond. So 6 nanosecond and there are no any extra, but here hold time is 5 nanosecond. If I will change this hold time, you can change to 7 nanosecond. So this is 6 nanosecond should be greater than or is equal to 7 nanosecond. If you can change here 7 nanosecond, then what will happen? If you can change here 7 nanosecond, then what will happen? Means in this circuit here hold time violation. Here hold time violation. Hold time violation. Then what you do? Suppose if this question is asked in GATE exam, suppose for example, and if examiner are interested in calculate T clock, so this answer will be wrong. You cannot write this answer because circuit having hold time violation. Because circuit having hold time violation. So if in the circuit we have hold time violation, then what we can do? So what we can do? So if I will add here suppose one buffer. If I will add here one buffer, how much here difference here 1 nanosecond. So 1 nanosecond buffer I can use here. If you will use here 1 nanosecond buffer, so this will be nothing but this 6 plus 1 7 nanosecond. So this is 1 nanosecond. So 6 plus 1, so no hold time violation. So this will be removed. But now come to the question. So this answer will be same or this answer will be different. At least this thing you should know. What I feel sometime Examiner can ask you this category of question with hold time. Okay, they will ask to calculate a maximum clock frequency but circuit having hold time violation. Okay, so this is the best question, and from this easily you can learn. So now come to the point, which thing is going to be changed. So from flip-flop 2 to flip-flop 1, this path will change. This path will change. So from flip-flop 2 to flip-flop 1, what thing is going to be changed? So this is 6 nanosecond plus 1 and then setup time. So what is going to be changed? Here you have to add 1 nanosecond. So now this answer will be 1 nanosecond. So this answer will be 11 nanosecond, which is more here. So now what will be the answer? In this case, so T clock should be greater than or equal to 11 nanosecond. Then F clock will be reduced. If you will add delay in the circuit, then definitely your clock frequency will be reduced. So F clock will be reduced to, you can write, sir, this is 1000 by 11 megahertz. So this will be reduced to, this will be reduced to 100 megahertz. So this value definitely lesser than 100 megahertz. So I hope now hold time and setup time easily you can handle. Okay, if in the circuit hold time violation, then what you can do, you can add. Okay, how much difference? So if this is 6, this is 7, so 1 nanosecond extra delay you have to add. If you will add extra delay, then this T clock for that path, this T clock will be modified, and then F clock maximum can be modified. If suppose you have to add a delay in this path, and so this path will be modified, this path will not be modified, this path will not be modified. Clear this? So this path will not be modified. So I hope this problem is clear to all of you. So just confirm me. Okay, so only you are only attending the class only. Okay, so just confirm me, this thing is clear to you or not. Okay, everything is crystal clear. Okay, so just tell me which topic you also want to study. Okay, so now according to me, we have discussed. I hope easily you can handle state transition diagram. That is very easier part. That is not that is equal to, I can say, truth table. Okay, so now according to me, we have discussed all the parts: number system, logic gates, Boolean algebra, K map, okay, and combinational circuit, and then sequential circuit, and this whole time, and you can say setup time and hold time. Okay, so now the next remaining part is ADC and DAC. Next remaining part is ADC and DAC. Okay, so can you complete by yourself that part, ADC and DAC? Okay, can you complete, or I have to again take that part? Please tell me. Okay, please tell me. Okay, can you complete that ADC and DAC by yourself? Okay, or I have to conduct classes for that? Okay, because only you are. Okay, sir, again. Okay, so one more time this topic is required. Okay, okay, so can we conduct tomorrow that ADC and DAC separate topic, but tomorrow signal and system or communication system also I will start. Okay, and 1 hour, only 1 hour of classes I will conduct for ADC and DAC, and I will discuss all the things in ADC and DAC. Okay, so I will conduct one session for ADC and DAC, because some students are demanding right now only you are attending the class, so it is better. Okay, tomorrow one session we can conduct, okay, for separate only for ADC and DAC. Okay, now if you will ask me, sir, semiconductor memory, so in semiconductor memory, examiner can be interested in like this 6 transistor SRAM. Already I have discussed. Okay, and generally they are asking question from RAM and ROM. Okay, already we have okay, so they cannot ask any question from the RAM, so only they can ask the question from the ROM. One thing you remember from the ROM, what is the size of ROM? 2 raised to power n cross m. This is a decoder, so number of address line is n, m is the number of data line, and the basic structure which we have studied in the ROM and PROM, that you should know. And if you are comfortable in this, you can solve all the previous question, all the previous year question definitely. Okay, all the question easily you can handle. Okay, so one more session tomorrow I will conduct for ADC and DAC. That is only for ADC and DAC. Okay, none of the other thing I will discuss in that. Okay, and logic family, CMOS already, I hope CMOS easily we can handle. That is a very easier topic. And okay, and this basic semiconductor memory and the floating point representative, I hope you can do that part. Okay, floating point, that is only in electronic syllabus. And is there any another topic? No, only this topic is in your gate exam. Okay, so tomorrow 1 hour of session I will conduct. Okay, so tomorrow maybe we will start either signal or communication, and 1 hour of classes for ADC DSC I will conduct. Okay, sir, is DTL is called STL. DTL is diode transistor logic. Okay, STL is different. Okay, but STL generally, STL I don't remember the STL name. Okay, the logic family, if you will ask me, the logic family is started from diode transistor logic. Okay, then TTL, main VLSI, or you can say fabrication, is started from TTL. So TTL is transistor. In transistor we have two logic. One transistor is operated in a active region, and in second transistor is operated in a saturation region. So in TTL, transistor is operated in saturation region, but in ECL, emitter coupled logic, or you can also call CML, current mode logic, in that is also transistor, but in that transistor is operated in a active region. That's why that is fast. So fastest logic is ECL. So basically ECL and TTL, and then by using TTL we design NAND gate, and by ECL we design NOR gate, but in real life generally we use NAND gate. That's why generally we studied, or examiner are interested in TTL. But now in your syllabus, examiner will not ask you question from TTL, DTL or ECL. Only examiner can ask you question from the CMOS logic family, and in only electronics engineering. So only CMOS you have to study. Okay, so only CMOS you have to study. Okay, this remaining thing for gate exam just you can leave. Okay, so only CMOS you have to study. Okay, so this you can search in over the net, sir, what is STL. Okay, I don't remember. Okay, I don't remember. Okay, wastage log it. Okay, definitely this is STL. I hope there are definitely there are some reason can be possible here. So practical logic was diode and transistor, then transistor and transistor. Okay, then transistor replaced by the MOS. Okay, then MOS we are using CMOS, one NMOS and PMOS. That is a, you can say, CMOS. So today practically we are using a CMOS logic family. So this is the only family. Okay, in between that there are so many different names actually we can use, but real world generally we don't use that. So in real world, DTL after DTL, that is TTL, TTL and TTL after the region we have changed saturation region to active region. Okay, that is ECL. Then we have jumped to the MOS. First we have used NMOS. Okay, NMOS. PMOS logic is not possible, only NMOS. Then we have jumped to the NMOS plus PMOS, that is called CMOS. This is the basic logic family, and today we are doing some research in the MOS transistor, different. Okay, so leakage current we are reducing, many things we are doing. Okay, so you don't have to study logic family in detail, only you should remember past transistor. Okay, if you can see my crash course, digital crash course in global channel, so in last lecture I have discussed past transistor. So you should know at least past transistor. Okay, because examiner can target a CMOS question from the past transistor. Okay, so that thing you can do by yourself. Okay, so tomorrow we will meet either with signal and system or with communication system, and 1 hour of classes I will conduct for ADC and DSC. Okay. Okay, so tomorrow we will meet. Okay, now the time is your 12. Okay, thank you, take care. If you have any doubt, ask me. Okay, so that we can conclude the today's session. If you have doubt, just ask me. Okay, no doubt. Okay, so now I am concluding today's session. Okay, uh, if any doubt, you can ask me. Okay, so tomorrow we will meet again. Okay, thank you, take care, bye bye, good night, and Jai Hind.